where great professors teach you. My name is George Wilson, and I'll be your host. Today we begin a course entitled Astronomy, Earth, Sky, and Planets. Your professor is James B. Kaler of the University of Illinois. Professor Kaler received his B.A. in astronomy from the University of Michigan and his Ph.D. from UCLA. He has taught at Illinois for over 40 years. His research area, in which he has published over 120 papers, involves dying stars. But Professor Kaler's interests reach far beyond this topic, and he has published widely in the area of popular astronomy. Among his many critically acclaimed books are Stars and Their Spectra, The Little Book of Stars, The Ever-Changing Sky, The 100 Greatest Stars, and Extreme Stars, which was the American Association of Publishers' choice for Outstanding and Scholarly Title in Physics and Astronomy for 2001. Professor Kaler also served as a consultant for the Time Life books Voyage Through the Universe series, and he appears frequently on various radio and television programs to discuss topics in astronomy. Currently, Professor Kaler serves on the board of directors of the Astronomical Society of the Pacific, and as one of the world's greatest living astronomers, he continues to be a much sought-after speaker. For almost as long as human history is recorded, man has looked to the heavens with wonder and amazement. Indeed, astronomy is among the most accessible of all sciences, for at a primal level, all one needs to do is look up. In the daytime, there is the sun, our closest star. Sometimes we see the moon, while at night we can feast our eyes on planets and myriad stars, not to mention the occasional interloping meteor or comet. But beyond this basic level, a world of fascination exists as we explore how over the centuries mankind has come to a better understanding of his place in the universe by gazing at the heavens. And that is what this course is all about, not just the natures of astronomical sights, but how they all fit together, how they were created, how they affect us back here on Earth, and what their fates, and perhaps ours, are likely to be. For more information on this lecture, please visit the course's webpage at www.modernscholar.com, where you'll have access to links to related sites, a seminar room to share your thoughts with other students, and, yes, of course, a final exam. And now we begin Astronomy, Earth, Sky, and the Planets. And now, Professor Kaler. Astronomy, Earth, Sky, and the Planets. Lecture 1, We and the Universe.
I'd like to welcome you to the first of 14 lectures in this course on the astronomy of the solar system. We will look at everything from the sun out to the most distant reaches of the planetary system and beyond, going almost halfway to the nearest star. The lectures here are going to cover the motions of the Earth around the sun, the spin of the Earth and the effect that it has for those of us upon it. We're going to look at the physical natures of the planets. Why is Mercury different from Pluto? Where is it? Why is Jupiter different from the Earth? We're going to look at all the planets of the solar system. We're going to look at the debris of the solar system. We're going to look at how this whole system was put together. In this first lecture, however, we're going to look at the big picture, not just the planetary system, which is going to be introduced, but at the grand scheme of things, where we look not just at the sun and at our local area, but we look at the stars around us. We look at how these fit into the entire galaxy. We look at how the galaxy fits into the universe at large, and most important, get some idea of the scale of things. I like to think that I've been an astronomer for over 50 years, since the time I was 8 years old when I first got interested in this subject. I got interested really because of the beauty of the nighttime sky. I was walking with my grandma, and I said, "Stars have points, don't they?" And she said, "No, they don't have points. Look up and take a look." And I looked up. Sure enough, there's a star up there. It's kind of orange in color, and it didn't have points. It was kind of roundish and sparkly, and that orange color just fascinated me. And I kept looking at it. And a year later, there it was again. And I looked at it again, and I was gone. I knew at that point that all I wanted to be in life as a professional was an astronomer. It goes to many things that are very personal to me. It goes to the beauty of the nighttime and the daytime sky. The daytime sky is, the astronomer is equally at home in the daytime sky. We have the sun, we have the moon, we have the blueness of the sky. We have all manner of phenomena that we can see. In the daytime, we can see the Earth in the daytime, which of course is an astronomical body as well. Why do we want to study astronomy? For a variety of reasons. Astronomy is a very good example of how a science works. It's exemplary of all sciences, for that matter. But it's the science, in a sense, of everything. We study not just the planets. We study not just the stars. We study the universe as a whole. And to understand the universe as a whole, we have to understand the very small, going down to the very atoms that make us. We are looking outward from an astronomical body. We are one planet of many in our planetary system. Maybe one planet of hundreds, maybe millions in our galaxy. We still do not know. We need to understand our own Earth. We can't experiment on our Earth. We would like to understand our Earth better. How do we do that? We understand our Earth better by looking at the other planets and getting some idea of what they're like and why they are as they are, and feeding that information back to understand our own precious planet. The stars have a great deal to do with us. We live because of sunlight upon the Earth. We live because the sun is a stable star that will shine for billions of years into the future. Not only that, the sun reaches out to touch us with its matter, with a wind that it blows, that hits us, forms the northern lights, perhaps deposits more energy into the Earth. We came from out there. All of what is out there fed back into us. We came from out there because of the accumulation of material from the galaxy that wound up forming our sun and forming our planets. We are children of the galaxy. We are not isolated. If we are to understand our Earth at all, we have to understand our environment. And that means not just near space, the inner part of the Earth. It means understanding the moon, and it means understanding the planets and the origin of all of this system. And that is what this course is really all about. Let me tell you a little about what we're going to do over the course of these 14 lectures. We're going to start with the Earth, with the rotating Earth, with the Earth going around the sun, so we can get some idea of how things appear to move in the sky, why the stars rise in the east and set in the west, why the sun appears to move against the background of the stars, why the seasons exist. We're going to look at inner space. We're going to look at the atoms that construct everything. We're going to look at the light that allows us to learn something about the natures, the compositions, and even the origins of the planets that are out there. We're going to begin to look at the physical natures of the planets, from the Earth through the moon, beginning and sweeping through the planetary system from Mercury on out all the way to the distant planet Pluto. And then begin to look at the debris of the system, and finally at the end in Lecture 14 put it all together and see how it was all made. And see how our Earth was created and why our Earth is so special within this marvelous planetary system. So let's take a look at the planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto. Most school kids learn these things in order. And that sort of gives you the idea that all the planets are the same, that they're all alike, and they aren't. They're all natural experiments. And by looking at the other planets, we can tell something about ourselves. They are all formed under different conditions and different distances from the sun, different sizes, different masses. In an experimental science, you go into the lab, you change, you tweak the input, see what happens to the output. We can't do that to the Earth. We don't want to do that to the Earth. But nature's given us several other experiments that we can use. We can see what happens to Mercury. Why is Mercury the way it is? Why is Pluto the way it is? What conditions have changed them? And that leads us back once more into understanding ourselves. So look at the planets now in order outward from the sun in a little bit more detail. We'll keep increasing the detail until we begin to understand them better and better. Mercury, Venus, Earth, Mars. They're all rather similar. They're all made out of rock and metal. They're unusual bodies. We know of no other bodies in the universe quite like ours. There's a strong feeling of people who begin to learn astronomy that we are insignificant on this little rock way out on the edge of an anonymous galaxy. And one of the other themes of this course is that that is simply not true. We're in a very special place, on a very special body, a very unusual one, that is unlike anything else that we know anywhere. Mercury, Venus, Earth, and Mars, the terrestrial planets, after Terra, ourselves, we're all similar, yet we're all different, we're all individuals, and I don't mind throwing the moon into that as well, making 5 terrestrial planets. If you were walking on the moon, you would feel very much like you're walking on the Earth, a little lighter, you'd bounce around a little bit more because the body is less massive than we are. But if it looks like a planet and it feels like a planet, as they said about the duck, if it quacks like the duck, it's probably a duck, and that's what we have here. If it looks like a planet, it's probably a planet. So let's count the moon in on that as well. So now we've got 5 in the inner part of the planetary system. And then you look out farther, and you see these 2 giants, Jupiter and Saturn, enormous bodies that are terribly similar to each other. Jupiter, Saturn, Uranus, and Neptune are often put together as the Jovian planets. That's really not quite true. Jupiter and Saturn are very similar to each other. What we say about one, you can pretty much rely on being true about the other. Giant bodies, 10 or more times the size of the Earth in dimension. And then you move out farther to Uranus and Neptune, and they're smaller. They're very different from Jupiter and Saturn. They're rather unusual bodies in their own right. We don't understand them very well. In fact, we understand things less and less, really, the farther away we get. So now we've got 3 kinds of planets. We've got the 5 in the inner solar system, and we've got the 2 giants a little farther out, and then we've got Uranus and Neptune, which are farther out yet. And then there's little Pluto, about which everybody argues. Is it a planet? Is it not a planet? It's one of the most common questions I get from people. Is it a planet? People seem to be very concerned about the fact, well, in some ways it is, yes, and you can, some ways, well, maybe we should exclude it. I kind of like to include it. So now we've got 10 planets. We threw it out, and we threw out the moon, we'd have 8. You see what I mean? There's no strict definition, and that gives us a lot more freedom. And then we can take the little bodies in between Mars and Jupiter that everybody's heard about or maybe read about in science fiction stories, the asteroids. And we could collect them all together. We could call them a planet too if we really wanted to, and that gives us 11. So the definition is free and floating, and I'll continue to use it, free and floating. Remember when you were in first grade, maybe 4th grade, elementary school, and the teacher had, your classroom had this panel up on the wall of the planets. This huge sun and the big planets all in a line outward from the sun. I hate to tell you this, but they lied. It's not true. It's not the way they look. We have to deal with scale in this business. And it's important at the outset that we try to set the sizes of these planets in the context of the distances between them. Because almost everything is empty space, or at least filled with, even if it's empty, nothing is truly empty, of course. But the separations between things in astronomy are enormous compared to their sizes. A truly, truly underappreciated fact that is rendered a falsehood by the cartoon images that you generally see in classrooms. And sometimes we really have no choice because it would be impossible actually to draw a scale model of the solar system in a classroom. By the time you make the sun big enough to see, or the separations big enough, the Earth is so small you'd need a microscope to see it. So let's really start this particular lecture off after this introductory material by trying to put things into some kind of scale and into some kind of context. The sun is by far the biggest body in the whole planetary system, in the whole solar system. It is called the solar system for a reason. The planets are the satellites of the sun. They're the moons of the sun. The sun dominates everything. 1,000 times more matter in it than all of the rest of the planetary system put together. It's almost 1 million miles across. 1.5 million kilometers across. Its mass is 300,000 times that of the Earth. It's 1,000 times more massive than the largest of the planets, Jupiter. We're separated from the Sun by about 100 solar diameters. The distance between us and the Sun is a standard unit, which I'm going to refer to a lot, and I'll try to remind you of it off and on as we proceed through the course. Standard unit called the astronomical unit, with a capital A and a capital U, the AU. It's 93 million miles. It's the average distance between the Earth and the Sun. Average, yes, the distance between the Earth and the Sun does change a little bit. It has no effect on us at all, no effect on the seasons, as you'll see later, but it is a minor change by a few percent. So we use the average. and called that the astronomical unit. 93 million miles, almost exactly 150 million kilometers. And then we scale everything else to the astronomical unit. It's the fundamental distance unit that is used in all of astronomy, not just from the planetary system, but ultimately through distances to the stars, distances to the most distant galaxies. The distance is out, and we can get pretty boring just listing off statistics, so we'll try not to do that too terribly much. Mercury is 4/10 of an AU out. Venus is 7/10 of an AU out. So we're kind of nice and symmetrical, 0.4, 0.7, and then us at 1.0, and then Mars out at around 1.5. And close into us, the Earth is something of a double planet, really. We have the Earth and the Moon is 250,000 miles away. We won't even deal with that in terms of the astronomical unit. It's very close. And it's kind of interesting to think when we look at all these distances, and we are so proud of ourselves for getting from here to the Moon. That's all we've gotten, 250,000 miles. That's it. The Sun is almost 100 million miles away. The Earth is, as large as it seems to a human being, is a terribly small body. 8,000 miles wide, 13,000 kilometers wide. It's only 1/100th the size of the Sun. The Sun is 109 times, actually, if you want the real numbers, 109 times the diameter of the Earth. The Sun is 1/100th of an astronomical unit across. That makes the Earth 1/10,000th of an astronomical unit across. If you had the Earth a marble, say a 1 centimeter marble about this big, the Sun would be a wagon wheel about a football field away. And you'd see it off there in the great distance. Let's use this scale for a little while, and we'll start looking at where the other planets are, because where Pluto is, you couldn't even see to it. It would be so distant, even on this scale. And eventually we'll have to shrink down the scale to even begin to put the galaxy on, our home, our collection of stars. From here on out, we go to Mars at 1.5 astronomical units. And then we make a tremendous jump to Jupiter. It's 5 astronomical units away, 5 times farther than we are from the Sun. And on our Earth is a scale of about this big. Jupiter would be about the size of a, good-sized softball, perhaps a little bit larger. Located, this is 500 million miles from the Sun, 5 astronomical units away. That's 5 football fields away, if you like, on this scale. And then we make a tremendous jump out to 10 astronomical units to see Saturn. And then we make a farther jump out. We almost double it again to 19 to get to Uranus. We just keep going farther and farther away. Now we're taking ourselves all the way out to Neptune, which is 30 astronomical units away, which some people think is the sort of the end of the planetary system, because, again, Pluto sometimes is included, sometimes it isn't. It's a curious, strange transition body that is eventually going to tell us a great deal about the planetary system if we can ever get to it. It's the only planet we have not yet visited by spacecraft. We will eventually. It's a long, long journey. It takes about 10 years for a spacecraft to get out there from here. Moving even fast enough to break free of the gravitational field of the Earth and the gravitational field of the Sun, so it can float forever out there, moving off into the galaxy. Pluto averages 40 astronomical units away. Now, there's a lot of consistency in these planets. They all go around the Sun in pretty circular orbits. The Earth, quite circular. There are a couple that are a little bit off center, Mercury and Mars, but not terribly much. Pluto is way off center. It goes from the orbit of Neptune all the way to 50 astronomical units out. One of the things that we thought makes it not quite in the same category as the rest of the planets. It's also a highly tilted orbit. It takes us out to the outer fringe of the planetary system, where we find an enormous number of icy bodies that are called comets. There's a lot of misconception in this business, and people are constantly confusing comets with meteors. A meteor is a small rock, actually a little asteroid for the most part, or a little piece of comet fluff, as we'll see, that hits the Earth's atmosphere and goes streaking across the sky. Comets do not go streaking across the sky. They're orbiting bodies that orbit the Sun on long, skinny orbits that take them way out to the outer part of the planetary system and then close to the Sun. They're made mostly out of ice. We have found and can see now a huge reservoir of these cometary bodies out beyond the orbit of Pluto. In fact, many of them share the orbit of Pluto, which means that we could put Pluto out there in this band of icy bodies, which actually has a name. It's called the Kuiper Belt, after Gerard Kuiper, an astronomer of the mid-20th century, who first postulated it. A few of these things work their way in. They're ice balls that get heated up by the sun. Sunlight then Got the pressure of sunlight, the pressure of the wind from the sun. The sun is blowing a wind from its surface, pushes the gas and the released dust and dirt particles in the comet away, and you see this long streaming tail that very slowly works its way around the sun, visible night to night, very much as the planets are. So now we've expanded the planetary system into the region of the comets, out beyond Pluto. And it turns out that Pluto is one of them. It's not a comet. Don't get confused on that. It's not a comet. It's a transition body. It's a body that, in a sense, tried to be a planet, but because of lack of raw material, couldn't quite make it. And then we've got another huge reservoir that takes us almost halfway to the nearest star surrounding the sun. It's called the Oort cloud, O-O-R-T, after Jan Oort, another astronomer of the mid-20th century, who postulated that one too. And that's a reservoir of very long-period comets that were created in the planetary system eons ago, were tossed out, that still belong to the solar system. So the solar system is vastly larger in scale than the planetary system. So now we've got the planets. Well, you can count Pluto, you can count the moon. Doesn't matter. We know what they are. It's what they are that counts, not exactly what you call them and categorize them. And we've got this band of comets outside the orbit of Pluto and this huge reservoir of comets around the sun. And then we've got a whole bunch of little bodies in between Mars and Jupiter called the asteroids. The biggest one is not terribly large. It's considerably smaller than the moon. You roll them all together, you might have gotten an Earth or something like a terrestrial planet. It's kind of fair to call them a terrestrial planet collectively, and if you were walking on one, kind of the biggest one, certainly named Sirius, certainly feel like you were, except you'd be a lot lighter. So we now have at least something of an inventory here of the planetary system, and we will, over the course of this course, over this set of lectures, be looking at all of them in fine detail, beginning with the Earth in the middle, looking outward into the sky at the context of the orbits of the planets around the sun, how they move, and then in detail about their physical natures, and eventually where they all came from, and eventually where they're all going to go, too, because nothing is permanent. Everything is born and everything dies. And part of astronomy is learning how things are born and how things die, where we came from and where we're going to go. But we have to put the solar system and the planetary system make no sense if you can't put it into a broader context. The sun is a star. Now, generally, the common phraseology is to talk about the sun and the stars, and we talk about stars particularly. You're talking about all the other ones out there, but keep in mind always that the sun is just one of their number. You go outside on a nice clear night out in the country with no moon. The average human eye can see maybe 2,000, 2,500 stars over the course of the entire sky, the entire night. If you go around the globe, there are probably around 8,000 that are visible to the human eye, depending upon how old you are and what your level of light pollution is. This is just the beginning. They all look pretty much the same when you stand outside at night and look at them. They just appear as little points of light, but look carefully. Look very carefully, and you see colors. There's some that are a little reddish. There's some that are kind of orange. Even some take on a little bit of a blue tint that reflect their temperatures. The blue star's hot, the red star's cool. The sun is often considered as kind of a yellow-white star. It has that kind of cast to it. And temperature of about 6,000 degrees Kelvin. I hate to introduce a new temperature scale to you because in this country, in the United States, we have to deal with Fahrenheit and Celsius or centigrade. And in Europe and Canada and the rest, people stick with centigrade. It's a pretty simple system. Centigrade, it goes from 0 at freezing, water 100 at boiling. But then you go down and down and down to negatives until you get down to a point that's called absolute zero. It's minus 273 degrees centigrade. So we just start at 0 and work our way up. That's all. In centigrade units. And the sun in that scale is about 6,000 centigrade degrees above absolute zero. It puts things in sort of a context for you. Stars range in temperature from not much hotter than that of a self-cleaning oven, believe it or not, about 1,000 degrees or cooler. So cool you can't even see them with the human eye, to a maximum of close to 1 million. It's a spectacular range. In dimension, there are stars about the size of Manhattan. And there are stars the size of the orbit of Saturn, another spectacular range. Stars little light things, perhaps not much bigger than Jupiter in mass. If you want to stretch the definition of a star, which it really requires, you see at some point we have difficulty in even defining what a star is sometimes. I like to define it as a body that at some point in its career goes through this nuclear fusion process. And you have stars that are 100 times as massive as the Sun. The Sun, we know, is going to die out as a little body the size of the Earth sometime over the next several billion years. You go to stars that are much more massive than the Sun, they blow up, they explode. The Sun can't do that. One of the nice things that we have learned, the Sun cannot explode. But some of them do. And the ripples of the exploding stars spread throughout the universe help create new stars. They provide the chemical elements that created us. That's getting a little bit ahead of the story, however. Let's look back at the stars and a little bit at the scale. The nearest star, as close as it looks, this star called Alpha Centauri. And here you get into another argument, because Alpha Centauri is a triple star. Two of them go around and orbit about every 80 years, very close together. The brighter, very much like the Sun. Rather curious, an interesting coincidence. And then there's a little one a little bit farther away, a couple of maybe 10,000 astronomical units away from the double, which is called Proxima Centauri, and that's a little bit closer to us. But let's not quibble about this. Call it Alpha Centauri. How far away is it? It gets difficult to use astronomical units at this point. The star is about 270,000 astronomical units away. We need a new scale. You want to match your distance scale to the things being measured. Otherwise, you wind up with little bitty numbers, or you wind up with enormous numbers. So let's introduce the light year. And we'll scale it back to the astronomical unit in a minute. The light year is the distance, not a unit of time. It's commonly taken as a unit of time. No, it's a unit of distance. It's the distance a ray of light will travel in 1 year. Oh, is that hard to appreciate? Light moves at a speed of 186,000 miles per second, 300,000 kilometers per second. That's 8 times around the Earth, 1 second. Here to the moon in a second and a half. From the Sun to here in 8 minutes. We could say the Sun is 8 light minutes away. Pluto is several light hours away. Interesting aside, if you visited Pluto and you want to talk to the folks back home, you start talking and your telephone message doesn't reach back home for another 4 hours. Long way to go. That is, we see things as they were in the past. You do not see the Sun as it is now. You see it as it was 8 minutes ago. The nearest star is 4 light years away. It's about 270,000 astronomical units. So the light year and other units similar to that become the standard for interstellar use, and even for use across the whole universe, for that matter. One of the more common questions that I will get is, doesn't that bother you? You're looking at stars. The nearest star is 4 light years away. You're seeing as it was 4 years ago. What's it doing now? It could blow up, which it can't. It can't. Relax, it can't. It could blow up, and you wouldn't know it for 4 years. And yes, that's absolutely right. And I don't care, because I can't know anything until light gets to me anyway. So my now is when the light gets to me. Now, if you want to walk around your house or your office in a daze, think about this. You're looking at your colleagues or at your family. Light travels about a foot in a trillionth of a second. You see everybody around you as they were a few trillionths of a second ago. You don't see them as they are now. And the people farther away from you, you see more farther into the past. So you're not looking at anything in that context, that sense of now. Now is when the light arrives. So none of this bothers us very much. We simply ignore the fact that there's a light travel time. We see things as they are when they get to us. And we're looking at all the stars in the sky at different distances, and we see them as they were in the distant past. All at different different stages in their ages. And that's really not a problem, because stars live for far longer than that little light travel time anyway. They live for millions and billions of years. Who cares about a few thousand here and there? Just like when you're looking at your colleagues, a few trillionths of a second in the lifetime of a human being doesn't mean anything at all. So it really matters not. And we can forget the whole thing, otherwise we wander around like this wondering, you're looking at everybody in the past. It can drive you crazy after a little while. So we forget about it. 4 light years, it's a long way to go. It's why we haven't gone to the stars and why it's going to be very, very difficult to go. The distances are spectacular. You can't even use this Earth as a marble scale. Let's take the sun as a marble now. We'll shrink it down from the wagon wheel down to the marble, and the Earth is about that big. It's about as big as a grain of sand on that scale. The nearest star is 170 miles, about 250 kilometers away. The scale is really to take small marbles and put them in the major cities of our country. Now start them rolling around, because stars move relative to each other. The sun moves about its own diameter in a day. So you have these marbles shifting a diameter in a day, and they're separated by 100 miles, 200 miles, maybe more. Do you think they're going to crash into each other? I don't think so. We're very safe out here. The separations are spectacular compared to the sizes. We live in a very safe part of the galaxy. Nothing terribly dangerous around us. Stars aren't going to collide into us as thick as they look in the nighttime sky. It is a grand illusion. The space between them is not empty, by the way. The space between them is filled. Filled is perhaps a bad word because it's almost a vacuum, but not quite. But it is filled with a thin, dusty gas. You can see that in the Milky Way. We've lost the Milky Way in our time. You go into any city, almost any village for that matter, and the lights are so bright that you can't see the dark skies anymore, but your grandparents saw them. Could walk out in the backyard and see this wonderful band of light going across the sky. Milky Way is the disk of our galaxy. All of the stars that you see at night, and 200 or more billion others, are spread into a thin disk that is 100,000 light years across. Now we're not talking 3 or 4 or 10 light years. We're talking 100,000. The sky is really in 3 dimensions. You lose that sense entirely when you look up there at the heavens. All the stars look at the same distance. All the planets look the same distance away. No, the planets are close, shining by reflected light. The stars are self-illuminating, shining by thermonuclear reactions, all at different distances. Some of the brighter ones that you'll see are only a few tens of light years away. Others, like the great star Deneb, many of the others that you see are maybe 1,000 light years away or more. You use telescopes, you can see them vastly farther than that. And we've learned how we're structured, this thin disk. And we're sort of out at the edge. Now, the disk doesn't have a real edge on it. It just gradually fades away. But the majority of stars are in this disk about 100,000 light years across. And we're roughly 2/3 to 3/4 of the way out to the edge. Now, imagine yourself in the middle of this disk, and you look around and you see the disk around your head. You can only see the individual stars within a few hundred light years, maybe 1,000 light years of you, and all the rest gradually blend into a thick band of light that surrounds you. The Milky Way, which is a thick mythology, a wonderful mythology about it. The pathway of the souls on their way to heaven. Celestial rivers bringing the water to irrigate our crops. And Galileo, when he put his first telescope on it back there in 1609, 1610, it's stars. It's just stars. 200 billion of them in a disk 1,000 light years across. And we're just one of them. Very special one, because we are part of it. And we can look out and see it. We can look out and comprehend it. Up until 1920, we thought our galaxy was the only one. There were inklings that maybe we weren't really alone, that go back a couple of hundred years before that. Astronomers began to see little fuzzy things. It tells a technical term, little fuzzy thing, little fuzzy blobs out there in space. And some of them showed structure, some of them had spiral arms, which our galaxy does, in fact. We didn't know that they were other galaxies until Edwin Hubble, after whom the Hubble Space Telescope was named, was able finally to resolve one of these things in individual stars. And if they were anything like the stars in our own galaxy, these things had to be terribly far away. In northern autumn evenings, you'll see the great constellation Andromeda rising up above the eastern horizon. And if you've got sharp eyes, you can see a little faint fuzzy blob in it. That fuzzy blob is the Andromeda Galaxy. Just friendly name, M31. It goes by a variety of names. Most distant thing you can see with the naked eye, without a telescope, 2 million light years away, a galaxy very much like our own. And then you look out farther and you see more and more and more of these. Several years ago, the director of the Hubble Space Telescope said, let's look at a blank area of sky and see what turns up. Now, the Hubble Space Telescope burns up money at a pretty fierce rate. It is very difficult to get time on the Hubble Space Telescope. And here the director wants to take 100 hours worth of this precious time and look at something that's blank. He figured he'd get something. Oh, he did. In that little dot, which is only a tenth the angular size of the full moon. Hubble Space Telescope has a very small field of view. 3,000 galaxies showed up. 3,000. If you could replicate that across the sky, it would be possible to see over 1 trillion galaxies from the Earth, each one similar to our own, with maybe somewhere around 100, 200, 300 billion stars. Not all of them are alike. Some of them are big, some of them are small. If you want to count the smaller ones, they're vastly more than 1 trillion within the scale of the universe we can actually see. Vast numbers of them, clustering together, all of them coming out of a concept that we refer to as the Big Bang. We look at the velocities of these galaxies, which we can easily find. We've been looking at this over the last century or more. And we find that with the exception of a couple of galaxies that are close to us, they're all moving away from us. And more remarkably, they're all moving away from us with speeds that are absolutely and directly proportional to their distances. You double the distance, you double the speed. And the speeds go up and up and up till they approach the speed of light. Some of these things are going away at enormous velocities from us. And the only explanation that seems to fit all of the data is that at some point, number's been pretty well pinned down to about 13 billion years. Somewhere around 13 billion years ago, the universe was in a hot, dense state. You can't say it was out there. You can't say it was like a pea. You can just say that all the matter was crushed together into a hot, dense state from which it began to expand. It's not an explosion. It began a sudden and violent expansion. And within that expansion, the galaxies, which accumulated into clusters of galaxies, which formed stars, all of this expanded away, and we're seeing the remnants of the expansion. Where did the Big Bang start? It started right here. It's in this room. Everything is growing. Now, don't get the wrong idea. It doesn't mean that the Earth is expanding or that we're expanding. All this is held together by the glue of gravity, which will be the subject of a whole lecture. This wonderful concept of how things are put together. It means the separation between large-scale things. It's actually an expansion of space. It's not an explosion. It means that space itself is getting bigger and bigger, and the galaxies are just floating along with it. The separation is increasing. Why it happened or how it came together, nobody knows. We can speculate, perhaps, but there is no hard data on how all of this began. We're seeing the aftermath of it. And we're one part of it. We're a very important part of it. Everything affects everything else in this system, not just through gravity, but through radiation, through light. We're all tied together. The whole universe, one. It means one thing. And we're not separated from it. We are the third planet out from the sun, from an ordinary star. It's a very special star in our view because it's ours. It keeps us alive. Everything that we have comes from the sun eventually. After the Big Bang, galaxies formed. Stars formed within the galaxies. As stars age, they create chemical elements within them. After all, the sun is making helium out of hydrogen. Eventually, it'll make carbon and oxygen out of helium. More massive stars can go farther yet. They can even create iron in their cores. Stars like this explode. Even stars like the sun will create additional chemical elements, launch them to the surface, perhaps out into interstellar space. Stars recycle themselves. The sun will lose about half of its matter back into interstellar space, and more massive stars will lose even more. All of that becomes fodder for the creation of new stars. New stars are born from the gases of interstellar space, but these gases have been contaminated by heavy elements from the deaths of previous generations of stars. The galaxy is around 13 billion years old. It didn't take long to form galaxies after the Big Bang. It happened very, very, very quickly. Reasons we still don't entirely understand. And then the deaths of stars began to increase heavy element content within the galaxies because the Big Bang created nothing but hydrogen and helium, the lightest of the things. The sun came along 5 billion years after, 5 billion years ago, some 7 billion years or so after the creation of the universe, 8 billion years. So we had about 8 billion years worth of stellar death to populate the gases of interstellar space with heavy elements. The sun and the earth were born from that. The earth is a distillate, then, of the deaths of exploded stars. So all of these little points out there are not just, it's not just to beautify the sky. They all have to do directly with us. And through the course of these lectures, we'll look more and more and more at what they are and at our place among them. Thank you.
This ends Lecture 1. Astronomy, Earth, Sky, and the Planets. Lecture 2, Reflections of the Spinning Earth.
We ended the last lecture with the Big Bang, with the concept of the whole universe over billions of light years. And now we're going to bring it back to home in this lecture called Reflections of the Spinning Earth. We're going to look at our placement on it and how things appear to move in the sky as a result of where we are, how we're moving on the Earth, and the spin of the Earth. We'll look first at its shape, and then at its size, and then at its rotation, how it's moving. And as the Earth spins, how the sky appears to spin above us, at the risings and settings of stars, and how we use the stars to determine where we are on Earth, because we don't know. We can't navigate this body unless we use the stars. Even in the modern day and age, we still need the stars. And finally, at proving that the Earth actually spins. Not an easy thing to do, something that was done only in relatively recent times. So let's go right back to the beginning at this point. And what's the shape of the Earth? The Earth is round, you say. Everybody knows the Earth is a sphere. How do you know the Earth is a sphere? Well, your kindergarten teacher told you the Earth was a sphere, and you believed everything she said, and you still believe the Earth is a sphere, right? Go on out on a boat into the ocean. Stand out on the Great Plains sometime and look off into the distance. It sure looks flat as can be, far as you can see out to a horizon, where if you go far enough, clearly you will fall off the edge. But you know that's not true. You drive along the highway, you look out to the horizon where the sky seems to come down to meet the land, and you can't get there. You don't go off a cliff where there's a big pile of cars down there at the bottom. You can never get to the horizon. As you walk, as you drive, it recedes in front of you. That was known to the ancients. You go back a couple of thousand years. This was one of the first tips that the Earth is really round, or at least it's curved. What else? Well, as you move along the surface of the Earth, the stars appear to move in the other direction. There's a reflection in the motion. One of the themes that we have over the next couple of lectures especially is that as you move one way, everything in the sky appears to move the other way. I don't think there's anybody who hasn't had the experience of driving. You're parked at a red light, and there's another car next to you, and your foot's on the brake, and gradually the car next to you starts to move up a little bit, and you feel, oh my goodness, I'm moving backwards, and you stop harder and harder on the brake, and it does no good at all. Reflexive motion. As something moves this way, you appear to move the other direction. You're driving off into the country, you're going this way, the cows are going in the other direction. It's exactly the same thing with the Earth. As you move one way, things in the sky appear to move in the other way. So as you are walking this way, and if I were to walk this way, the ceiling would appear to move this way. But if you're walking on a flat Earth or on a round Earth, the motion is different. If you're walking on a round Earth, the motion is extremely smooth in the opposite direction. That was known to the ancients as well. The Earth must be curved in some way or another. The real tip-off, however, came with eclipses of the moon. Commonly confused with the phases of the moon. We'll talk all about this in a later course. I have a sun. I have an Earth. I have a moon. Shine the flashlight on the Earth. I'm illuminating this hemisphere of the Earth. But the Earth is casting a shadow into space. The moon is on the other side of the Earth over here. If the moon goes in back of the Earth, it goes into the shadow of the Earth and disappears. It doesn't entirely disappear, but it gets very, very dark for a period of time. The Earth must cast a circular shadow into space. As the moon goes around the Earth and back here and loses its source of sunlight, its illumination, the outline of the Earth is projected onto the moon as a circle. This is known to Aristotle. No matter what the configuration of the eclipse, how the moon goes in back of the Earth, the shadow is always a circle. Therefore, the Earth must present a circular outline, and no matter in which direction the moon appears, the Earth always has a circular outline, and the only body whose outline is always a circle is a sphere. We've known this for 2,000 years. How big is it? Well, even that we have known since the 3rd century BC. A man named Eratosthenes, over 2,000 years ago, who lived in Alexandria in Greece, right here. And he knew that down here in what we now know as the Sudan, there was a town where on the first day of summer, the sun shone directly overhead like this. Went right down to the bottom of a well. But he knew where he was up here in Alexandria that never happened. On the first day of summer, the sun was a 50th of a circle off the overhead point. Well, if going from the Sudan and this place in Egypt up to Alexandria, far to the north, you move the sun by a 50th of a circle, the circumference of the Earth must be 50 times that distance between the 2 points. Just multiply one number by another. We don't know how big the Greek system of units, of measurement units were, but the best we know, Eratosthenes had it right to within about 10% or so. We have known for over 2,000 years that the Earth is a sphere and how big it is. Columbus knew that the Earth was a sphere. Maybe the crewmen didn't know, but anybody who was educated knew the Earth was a sphere. They had the wrong size by that point, but that's sort of irrelevant. They knew they could go all the way around and come back to the beginning. And then, of course, Magellan demonstrated it again by going all the way around, and now we can take pictures from space, and we see the Earth actually turning, rotating around, always presenting its circular outline. There's obviously no doubt at all that the Earth is a sphere. The proof is there. This illustrates an interesting point about science. You know, not everybody believes it. There's an organization known as the International Flat Earth Society. It consists of people who think that the Earth is flat. This is not a hoax. They really believe it. There's a North American branch as well, and they will do almost anything to convince you that the Earth is flat. Now, don't bring up arguments about going all the way around. Apparently, instead of going all the way around, you're going in a circle and coming back to your starting point, which you kind of are in 3 dimensions if you go all the way around. But it's not like this knowledge is universal, and this is true of a lot of the concepts that we're going to be talking about over this course. And it doesn't have to do just with the sphericity of the Earth. It has to do with going all the way to the concept of the Big Bang. You can't convince everybody. I think most of us, however, are convinced that the Earth is a sphere. Unfortunately, that's not true. The Earth really isn't a sphere. It's close, but it is not a perfect sphere. It's not a perfect sphere because it's rotating. The spin of the Earth causes it to bulge out a little bit at the center. I'll bet there isn't anybody who, when they were, say, 8 years old, didn't like to spin. You stand there and you spin slowly around in one direction, then you spin faster and faster and faster, and your arms come out at the side, and your body is flattening. The same thing happens to the Earth. The same thing happens to all rotating bodies. It's nothing unusual at all. The Earth flattens at the poles, and that causes it to bulge out at the equator. The difference isn't very much. It's only about 40 kilometers or so. It was measured in the 1600s. Causes pendulum clocks to tick slower at the equator than at the pole. Because the pendulum clock, the pendulum swinging back and forth as a result of the Earth's gravity, and the Earth's gravity is actually a little bit weaker at the equator than it is at the pole because you're farther away from the center. So you can actually measure it by time differences from the equator up to the pole. You couldn't tell if you actually saw the Earth from space. And if you look at the pictures made by the Apollo astronauts, you really can't tell. It's such a small amount. It has some interesting effects, which we can look at later. But you can look at some of the other planets and see the same thing. Saturn's polar flattening is very noticeable, even through a small telescope. So the Earth, technically speaking, a little more technically speaking, is not a perfect sphere. It's an oblate spheroid. It has the interesting effect of making the Earth wobble a little bit on its axis, something we can talk about when we look at the orbit of the Earth as it goes around the sun. And then if you want to be even a little bit more technical, It's not even a prolate spheroid. That is, the flattening at the poles causes the Earth to be in the shape of what is called a prolate spheroid. If you look at it carefully, it's got all kinds of little lumps and ripples on it, which affect the gravity. It affects the motion of the moon around the Earth, affects Earth satellites as they go around the Earth. It all depends on how closely you look at it, and this is true of most sciences. You go by series of approximations. So a good approximation, yes, the Earth is a sphere, and we can talk about it as a sphere. If we want to look at it a little bit more closely, not quite a sphere, it's something else, and we want to look at it more closely yet, no, it's really something else. This sort of thinking affects all of science. The closer you look at it, the more detail you see, and you have to have names for these particular shapes and sizes and all manner of different detail. But we can go back and be reasonably friendly about it over the rest of this talk. Unless we need to deal with the Earth as a prolate spheroid, we can still call it a sphere. And now we at least all know what we mean by the term. This is how science actually works. We take a lot of data, we construct some kind of modeling theory, and that, in principle, allows us to predict new observations we can make. And if all of these new observations support the idea, then the theory is probably correct. You can't actually prove a scientific theory, not really, not absolutely. You can just hope never to disprove it if you think one is correct, and that is the case of the sphere of the Earth. The Earth is a sphere because we've never proven it not to be a sphere, so obviously it is. And we know how big it is, and we've known how big it is for over 2,000 years. The spin is different. The Earth rotates on its axis. If you look down from the north, there's an axis running right through the middle, and it punctures through the sphere at the North Pole and the South Pole. Again, something that goes back to early childhood learning. It rotates in the counterclockwise direction as looking down from the north. That means stars in the sky appear to move in the clockwise direction, in the opposite direction. It's rather amazing the number of people who don't realize that the stars rise and set just like the sun. The sun comes up more or less in the east, it sets more or less in the west. Everybody's familiar with that. But watch the stars. They'll do the same thing. They take 360 degrees, go around 360 degrees in 24 hours. That's about a degree in 4 minutes. So you see a little shift. Go on outside some night, go look at a star. Wait 4 minutes, you'll see it shift by a full degree. You don't even have to sit around and wait. Go in and watch television, come on back and look, and it will certainly have shifted its position. Reflections of the spinning Earth. Aha, but is it the Earth that's spinning, or is the sky this crystal globe around us? And is it the sky that's spinning? That's a little harder to determine. Pythagoras, in ancient times, suggested that maybe it was the Earth that was spinning, and we actually saw the motion in the sky as the reflection of the Earth, but he wasn't believed. We actually didn't nail it down until the 1600s, surprisingly enough. Although there were inklings of people, but Aristotle, the great thinkers, it's too big to move. Look at the size of it. Go on outside. How can it move? Besides, the argument was that if the Earth were spinning, think of the wind that would be blowing out there. It would knock you down, without, of course, realizing that the atmosphere is spinning at the same speed as the Earth, and consequently, you don't feel this tremendous wind. Everything is moving along together. We can prove it now, as far as you can prove any scientific theory, of course, but the Earth is spinning in this direction. And what does that have to do with the sky? Well, let's go back to the Earth first and define a few points and circles on it. We've got the North Pole, we've got the South Pole. In between, we've got the equator. The equator is where the Earth is spinning fastest. We know that it's 8,000 miles across, 13,000 kilometers across. That's 25,000 miles around in 24 hours. The equator's spinning at around 1,000 miles an hour, about 1,600 miles an hour. You don't notice that because we're all moving together. We have to find out where we are on this planet. As you drive from New York to Chicago or from any 2 points, it's not hard. You follow a map, you follow guidelines, but try to do that out here in the middle of the ocean. There's no X marks the spot. How do you know where you are? The only way you know where you are is by looking at the stars, by looking at their locations at a given time, and that will tell you where you are. It's a very dangerous place because there's no guidelines, there's no streets, there's no markings. And if you go in the wrong direction, you and your crew could easily die. So we have to have a way of marking position on the Earth, and we do it with a very simple grid of latitude and longitude? Very simple. You start at the equator. You call that 0 degrees. You go up to 90 degrees, a quarter of the circle, up to here at the North Pole, and you call that 90 degrees north. And you go down in this direction, you call that 90 degrees south. And then it's 10, 20, 30, 40, 50, and so on right on up. Most of the central U.S. Ranges from about 30 to 50 degrees north latitude or so. You go down South America, 30, 40, 50 degrees south latitude. Very simple concept. Longitude is measured in the other direction, is measured around the equator, like so. Latitude, the beginning is easy because you start at the equator and you go north and you go south. You've got a physical reference, the spin of the Earth. Longitude, you don't. You've got to, where do you start it? Where do you start it? Well, to get a longitude, what we do is draw a circle from the North Pole. Pick a city, Kansas City, perhaps. Draw a circle through Kansas City, crossing the equator to the South Pole. And you see where it crosses the equator. Now what you do is you need a 0 point on the equator. And what are we going to use? Well, we could use a mountain, I suppose, but we have to find something that everybody agrees on. And what we have agreed on is to take a circle that starts at the North Pole, goes through Greenwich, England, and crosses the equator, the South Pole, and where you have that intersection, you call that 0, and you measure the angle along the equator from this so-called Greenwich meridian to the meridian, the north-south line, through your location at home. Why Greenwich? Well, England was the big sea power when all of this was being set up. You don't have to use Greenwich. The French used Paris, but England was the sea power, and they said, it's going to go here. And it went there. Completely arbitrary. And we've used it for the last few hundred years that way. Latitude is easy to measure. Longitude isn't. How do you measure latitude? Well, you have to look at the orientation of the sky to get that. Take the Earth in your imagination and take the axis of the Earth and run it outward. As you stand out on a country evening, it looks as if you're standing in the middle of a giant sphere. It's called the celestial sphere. It's an illusion. It's not real. It looks gigantic, and it looks like it's rotating around you, making everything rise and set. You can do the same thing on a nice, clear, sunny day. You have this blue dome over your head. The celestial sphere. It is an illusion. But let's make use of the illusion. As you stand in any location, there's a point directly over your head. The world's most venerable tool is a plumb bob. It's a weight on a string. Points directly downward. And it points to the center of the Earth. If you run the string back in the other direction, it points to a point directly over your head. The point over your head is called the zenith. It's yours. Nobody else has your zenith. You simply point directly over your head away from the center of the Earth, away from where gravity is directing you downward, and you locate your zenith in the sky. Then you take the axis of the Earth and you point it out in both directions and see where the axis of the Earth punches through the sky. As the Earth turns on its axis, the sky will appear to turn around its axis and around 2 points in the sky called the celestial poles. The one above the north pole of the Earth is the north celestial pole. The one under the south pole of the Earth, or above the south pole of the Earth, if you like, is called the south celestial pole. And as the Earth spins around on its axis and its poles, the sky appears to turn around its own axis and around its poles, carrying everything along with it. Now remember, it's an illusion. We know we're on the Earth, and we know that is the cause of the apparent spin of the sky. So we'll still make use of the illusion. Now, if you stand on any point of the Earth, it looks as if you're standing straight up. Doesn't matter where you are. We're standing straight up here in, say, North America, and if you imagine your globe, well, the people in South America and Australia must be hanging on for dear life, trying not to fall off. But everybody feels that way. It's because gravity is pulling us all down toward the center of the Earth. So we'll stand on, wherever you live, it appears you're standing on top of the Earth, and that causes the axis of the Earth to be oriented such that the elevation in degrees above the northern horizon, if you're in the northern hemisphere, always equals your latitude. It's the fundamental first rule of celestial navigation. If you look to the north and you look up by an angle equal to your latitude, you will find the north celestial pole, that point of zero rotation of the sky around around which everything appears to be moving. If you look down in the other direction, of course, you would see the south celestial pole. But if you're in the northern hemisphere, the south celestial pole would be below the horizon by that much, and you can't see it. So the sky is spinning around these 2 points here, carrying everything along with it. Stars rising in the east, setting in the west. The stars, sun and moon, wherever they happen to be, if they are north of the celestial equator, they will rise in the northeast, set in the northwest. If they're south of the celestial equator, they'll rise in the southeast, set in the southwest. Only things that are exactly on the celestial equator will rise exactly east and set exactly west. Now, if you don't know your latitude, and if you know your stars, you can then locate the position of the north celestial pole by its position among the stars. You can then measure the elevation of that point above the northern horizon and determine your latitude. You can find your latitude simply by looking at the sky. Know where you are north or south. If you look at old maps, you often find that they're very distorted, and it looked like the map maker just wasn't very good. That's not really true. It's because they knew how to get latitude. Look at all the proportions in antique maps. They're fine in latitude. They couldn't get their longitudes. Longitudes are much more difficult to get than just the elevation of something. The longitude requires the use of a clock. Longitude differences always equal time differences. So if you want to get your longitude at any given location, you must know your time here and your time at Greenwich. Subtract the two and make the conversion from hours, 15 degrees per hour, from hours to degrees. That's a difficult thing to do because if you're in a wooden sailing ship and you set your clock at Greenwich and then it takes you 2 years to go around the globe, your clock isn't going to keep very good time. We couldn't get longitudes until we had good seagoing clocks, which we didn't have until toward the end of the 1700s. Back to the spinning Earth. We're lucky in the northern hemisphere because we have a star that's very close to the north celestial pole. It's called the North Star, Polaris. Goes by a variety of names. Not the brightest star in the sky. It's kind of a modest middle brightness star. But you'll always see it elevated above your horizon by an angle equal to the latitude. It's at the end of the handle of the Little Dipper, which we'll look at a later lecture. And it's easily locatable by anybody who knows the stars. It's not exactly on the pole. It's about 3/4 of a degree off the pole, but it's close enough so you can get an approximate latitude. And it's not hard as you go around the globe. Once you understand your stars, if you go north to Alaska, south into Mexico, down into Argentina, into Australia, you will see the sky change its aspect. By the time you get down to the equator at 0 degrees latitude, the north celestial pole is sitting right on the horizon, the south celestial pole comes up, and when you get into the southern hemisphere, you're now looking at the south celestial pole and the north celestial pole is down. Come back to mid-northern latitudes and look up, and you'll see the pole up here. Now, everything is going to be spinning around the pole in the direction opposite to which the Earth spins. Northern hemisphere will be going around in this direction, in the counterclockwise direction, looking at the North Pole. And Polaris can't set. It's always 40 degrees above the northern horizon. Consequently, since Polaris is 40 degrees above the pole, no star within the latitude, let's say you're 40 degrees north latitude, Polaris will be 40 degrees up. No star within 40 degrees of the pole can set. So we have a whole bunch of what are called circumpolar stars that will never set. These include for most mid-northern latitudes such things as the Little Dipper, most of the Big Dipper, and so on. But there are a whole bunch of stars around the South Pole here that can't rise. And they're never visible from mid-northern latitudes, the Southern Cross, the nearest star to the Earth, Alpha Centauri, a whole group of them. The only way you can see the whole sky is to stand on the equator of the Earth when the two celestial poles are on the horizon. Then the whole sky is rotating about these 2 points here, and over the course of the day, presuming you can see the stars in the daytime, which you can't. If the sun weren't there, you would be able to. Certainly over the course of the year, you can then see the entire sky. That's the only point on Earth where the entire sky and all the stars are visible to you. If you travel to the North Pole of the Earth, the equator is going to sit on the horizon. The North Celestial Pole will be directly overhead at your zenith. And the stars will appear to march around the sky like this, parallel to the horizon. The entire aspect of the sky will appear to change. If you're on the south pole of the Earth, the north celestial pole is down and the south celestial pole is up. So you see different things in the sky at different latitudes. It's entirely latitude dependent. How do you really know that the Earth rotates? Well, in your mind, use your plumb bob again. Just a weight on a string, that's all. And let it swing. Pretend it's a pendulum, swinging back and forth. Go up to the North Pole in your mind and hang the string from a frictionless bearing. You see a remarkable thing. As you watch, the plane of the swing, the direction in which the pendulum is going, will appear to change its directions mysteriously, as if there's some odd force out there that you don't understand. What is really happening is that you're swinging the pendulum free in space, and the Earth is turning under it. If you swing it toward a star out on the horizon, the pendulum will simply follow the star and will take 24 hours to go all the way around, showing that the Earth is actually turning underneath the pendulum. This experiment was first run a long time ago by Léon Foucault in Paris, who swung an iron ball from the top of the Pantheon in Paris. It became a sensation. Now, it only works with this 24-hour motion at the North Pole of the Earth or at the South Pole. At the equator, it doesn't work at all. At mid-latitudes, it takes longer for that pendulum to appear to go all the way around. They're fascinating to watch. You watch them swing, and gradually it changes the direction. You find these things in most good science museums around the world. And if they're set up right, again, they're mesmerizing. People will just stand there and watch it slowly change. You can see the Earth turning beneath your feet. It is the first proof we had, in fact, that the Earth does rotate on its axis. Or I should say the first piece of evidence that we have that the Earth rotates on its axis. There are others. Concept known as the Coriolis effect. If you were to shoot a cannonball north from your location toward, say, a city up north, that cannonball would appear to curve to the right because it's moving at a faster speed around the Earth than the target farther to the north. So you have this mysterious force that makes all projectiles turn toward the right if you look toward the north, in the opposite direction if you look toward the south. This force isn't really a force. It's caused by differing rotational speeds of the Earth. You're moving faster at the equator. You're moving zero at the North Pole. The effect the Coriolis effect is visible in weather patterns. It's largely what causes the circular weather patterns that you see in the fronts in the northern and southern hemisphere. So the knowledge is ancient. We know how the Earth spins. We know its size. We know its shape. We have evidence and proofs of all of these. And at this point, we have to put it into some kind of context with the rest of the planetary system, because the Earth is also going around the sun. It has not just one motion, but two motions. And in fact, when you look at it in even more detail, it has many more motions than that. So the next step is to watch the Earth orbit the sun and see what effect that has. As the sun appears to go around the Earth, it doesn't. It's the Earth going around the sun. The appearance of the sun going around the Earth, the tilt of the Earth's axis, and the origin of the seasons, which we'll do next. Thank you.
After listening to Lecture 2, a student posed this question to Professor Kaler. Can you explain what a nautical mile is? Let's listen to the professor's response.
It's an interesting question. The Earth is 25,000 miles around in circumference on a great circle, which is the largest circle that will take you all the way around the Earth, where the center of the circle is equivalent to the center of the sphere. In ordinary statute miles, that amounts to about 70 miles per degree if you're going north and south. So if you go from 40 degrees north latitude to 41 degrees north latitude, you've roughly gone about 70 miles. And you divide degrees up into minutes of arc. You use the same words you use for time, except they're not time units. 60 minutes of arc in a degree, 60 seconds of arc in a minute of arc. And that amounts to about 1 mile, slightly over 1 statute mile per minute of arc. Now, you can actually use the minute of arc to define the mile, and that defines the nautical mile. So if you've gone a nautical mile at the equator, for example, you've gone about a minute of arc, and it makes it very convenient for navigation. You always have to, of course, scale the physical units, miles, kilometers, for any planet relative to the angular units. The angular units, you can measure longitude and latitude on the moon, on Mars, as long as you have your fundamental reference points. But the sizes of the planets are different, of course, and then that amounts to a different size per degree. And very closely on Earth, it's about 1 mile per minute of arc, or in nautical terms, about 60 nautical miles. Actually 60 nautical miles per degree.
This ends Lecture 2. Astronomy, Earth, Sky, and the Planets. Lecture 3, Sun and Seasons.
We left off the last lecture with the spinning Earth. The rotating Earth causes us to watch the stars rise in the east and set in the west. We're now going to add a second motion. This lecture is called The Sun and the Seasons. And we're going to look at the orbit of the Earth around the Sun and the consequences that it has for life on Earth. The orbit of the Earth and the tilt of the Earth on its axis is responsible entirely for the seasons, for the fact that summer comes in the northern hemisphere, winter comes in the southern, winter in the northern, southern in the summer, that the air temperature, the ground temperature goes back and forth, all as a result of the tilt of the Earth's axis. And the point of this lecture is to show why, and to show that it has nothing whatever to do with the distance between the Earth and the Sun. The Earth's orbit, the Earth orbits the Sun over the course of 1 year. Not actually all that common knowledge. A remarkable number of people don't know that the definition of the year is the time it takes the Earth to go entirely around the Sun through a period of 365 and approximately 1/4 days. The rotation of the Earth having very little, in fact, having nothing to do with the orbit of the Earth around the Sun. The orbit is very close to a circle, but it's not a perfect circle. It's in the shape of what's called an ellipse. The ellipse has a fairly simple definition. You take 2 points, call each one a focus. The definition of the ellipse is that the sum of the distances from each point on the curve to the 2 foci is always a constant. If you take the 2 foci and shove them together at the center, the ellipse falls into the circle. The circle is actually a special case of the ellipse. And if you then stretch them out farther and farther from the center, you get an ellipse of longer and longer and longer proportions, flatter and flatter and flatter. Now, if you could see the orbit of the Earth from space, actually look at the shape of it, you probably couldn't tell that it's anything other than a circle. It looks very close to a circle, but it's not perfect. The Sun is offset from the center by a very slight amount. The flattening is only a matter of about 1% or 2. But this does change the distance between the Earth and the Sun. When the Earth is closest to the Sun, it hits a point in the orbit called perihelion, from 2 Greek words, helios from sun. When the Earth is farthest from the Sun, it's at a point called aphelion. Now, perihelion takes place, when you were closest to the Sun, around January 2nd, in the dead of winter in the northern hemisphere. This should tell us something right away, that the seasons have nothing whatever to do with the distance between us and the Sun. Aphelion takes place roughly on July 3rd or July 4th, when we're farthest from the Sun. There is a slight difference in the amount of sunlight falling on Earth, but it is overwhelmed by other effects, and we really don't feel it all. The seasons are caused by the tilt of the Earth's axis against the perpendicular to the orbit. It sounds complex, it's not. We'll look at it a little bit farther down the line. But let's take a look first at how the Earth appears to move around the Sun. As the Earth goes around the Sun will appear to go around the Earth. You're standing on the moving body, and again you have reflexive motion. We're moving. If you can look down from the north, the Earth has a counterclockwise path around the Sun. And as you stand on the Earth, you keep seeing the Sun in different directions, and it looks as if the Sun has a counterclockwise path around the Earth. Now, all this is going on at the same time that the Earth is spinning. So we have 2 effects. Every time the Earth makes a 24-hour rotation, the Sun will appear to rise in the east and set in the west. However, as the Earth goes around the Sun will gradually appear to shift its position against the background stars. Now, we all know we can't see the stars in the daytime. They're there. They don't go away when the Sun comes up. They can't disappear. It's just that starlight is so faint and so feeble that you can't see it against the brightness of the blue sky. There are many planets that you can see. You can see Venus with the naked eye. You can even barely, if you've got really good eyes, know where it is, even spot Jupiter in the naked eye during daylight hours. If you have a telescope, you can even see some stars once in a while. They're there. So let's at least pretend that we can see the stars in the sky with the Sun in the foreground. As the Earth goes around the Sun will appear to make a path around the Earth. This path is called the ecliptic. Word has nothing to do with ellipse. It's just a coincidence. It has to do with eclipses because eclipses take place on the ecliptic. The ecliptic is the apparent path of the Sun. Now, it takes the Earth 365, a little bit more, 365 days to go around the Sun through 360 degrees. Now, that's not a coincidence either. Where do we think the 360 degrees came from? It's an ancient concept of putting degrees in a circle equal to the number of days in a year. Now, you don't want to have 365 degrees in the circle because that's not really very easily divisible by anything. But 360 is a lovely number. It's divisible by 2, 3. It's divisible by just about everything. You can cut it down to smaller and smaller proportions. So we have 360 degrees in a circle for a 365-day year. This means that the Earth very nearly goes through 1 degree of its orbital path, assuming it's a circle, which is close enough, through its orbital path per day. And that means the sun will appear to move toward the left in the direction opposite its rising and setting, toward the east as you look at it, 1 degree per day against the background stars. Now, everybody's familiar with the fact that the stars are in groups in the sky called constellations. These patterns are used for ancient storytelling. All cultures have had different groups of constellations. And we'll look at these in the next lecture. But there's a very special group of constellations through which the sun appears to go over the course of the year, through which the ecliptic passes. Because the Earth's orbit doesn't wobble terribly much. The plane of the Earth's orbit is very constant from one year to the next. And that means that the ecliptic is very constant from one year to the next. The sun just keeps going through the same path over and over and over again. The ecliptic cuts through 12 ancient constellations called the constellations of the zodiac. They are some of the oldest that we have. They were sacred to many of the ancients because, after all, the life giver, the sun, is found within the constellations of the zodiac. They're the homes of the sun and of the planets, because all the other planets have pretty much the same orbital paths around the sun and pretty much the same planes. So we find the other moving bodies of the sky within these constellations of the zodiac. Hence the rise of astrology, the idea that maybe we can tell our fates by where all these bodies are against the background stars. Of course, every culture makes them differently, and we could make up anything we want. But the constellation of the zodiac, the word zodiac comes from circle of animals, same root word as zoo. It's an animalistic collection from very, very ancient times, many of which are fertility symbols. So the constellations of the zodiac hold the sun. The sun appears to move through these constellations year after year after year. Now, you can't see the stars in the daytime sky, but you can see them at night. At night, you're in the shadow of the Earth. As you rotate around, the sun is setting on my western horizon, and when I face in the opposite direction, the sun is to my back, and it's night, and I see the stars come out. As I orbit the sun, I continue to look in different directions at midnight. Tomorrow night, the stars will appear to have shifted over by that same 1 degree. I am always at night looking at the stars that are opposite the sun. So over the course of the year, the stars will appear to shift their nightly positions. If I look at a star at, say, 8 o'clock tonight, and I find it, let's say, due south, you don't even need to know your constellations to do this. Just go out and look. Find something bright, align it against a lamppost or something at any given particular time. Tomorrow night, you go out and look at exactly the same time. That star will have shifted over by 1 degree. A week later, it will have shifted over by 7 degrees. And you can watch the stars march around the sky, shifting nightly at the same time by 1 degree to the west. At the same time, of course, rising in the east and setting in the west. We have 2 motions going on at exactly the same time. So in that sense, you can actually watch the Earth go around the sun with the shift of the stars at night. So the stars and the constellations become seasonal. In the wintertime, in the northern hemisphere, the sun appears in the direction of the constellation Sagittarius. Now, loosely we would say it's in Sagittarius. It's not. Sagittarius is a pattern of named stars. The stars are at all different distances, at great distances from the Earth, and the sun is nearby, only 1 astronomical unit away. So the sun appears to be projected against the background of the distant stars. When the sun is in Sagittarius, at night we see the opposite constellation, Gemini, high in the sky. 6 months later, the sun has moved around to the constellation Gemini. So what do we see at night? We see the constellation Sagittarius. Now the sun is in Gemini in northern hemisphere summer, so Sagittarius becomes a summer constellation because that's when you see it. And vice versa. When the sun is in Sagittarius in northern hemisphere winter, Gemini becomes a winter constellation. So we speak of the seasonality of the constellations. Pegasus, an autumn constellation. Leo, a springtime constellation. All of these patterns and the roots behind them to be developed in the next lecture. Well, if I were to or if you were to stand in your room and you had the sun directly in front of you, say shining overhead on your belt buckle, and you walked around the room always perpendicular, which you would have to do, otherwise you would fall down, the sun would always be shining on your belt. If the axis of the Earth were exactly perpendicular to the plane of its orbit, then the sun would have to shine overhead on the equator at all times, and life would be relatively boring. The sun would rise exactly in the east and set exactly in the west. The equator of the sky goes from precisely east to precisely west, so that the equator of the sky is always centered on the north and south celestial poles. That isn't what actually happens. The Earth is tilted through an angle of 23.5 degrees relative to the perpendicular to the equator. This is the origin of the seasons. It's a very difficult thing to get across because the common sense is going to tell you that as you get closer to a fire, you're going to warm up. As you get farther away from a fire, you're going to cool off. So as you get closer to the sun, it should get warmer. As you get farther from the sun, it should get colder. And all other things being equal, that in fact is what would happen. But all things are not equal. The difference in distance is really pretty small. You wouldn't really notice the effect very much. But look at what happens with the seasons. First of all, perihelion and aphelion in the northern hemisphere are completely out of sync with the seasons. You're closest to the sun in the dead of winter. You're farthest from the sun in the middle of summer. Not only that, the seasons alternate between the hemispheres. When it is summer in the northern hemisphere, up here, it's winter in the southern hemisphere, down here. And if the distance of the Earth from the sun had anything to do with it, the seasons would be the same in both hemispheres. And they're not. It has to do entirely with this tilt. And that's why globes are placed upon stands the way they are. This tilt relative to the perpendicular, which is here, is 23.5 degrees. The term for this tilt is the rather long one called the obliquity of the ecliptic. All planets have obliquities of their ecliptics, and all planets have different ecliptics because they're in slightly different planes. Why 23.5? No one really knows. It's an accident of nature. So we'll see in the last lecture, the planets were formed, we're almost sure, by the successive collisions of larger and larger bodies that built the planets up from tiny dust grains that were in orbit about the early sun 4.5 billion years ago. And the last collisions were humdingers. They could have the effect of tilting the planets one way or the other. And Earth came out with approximately a 23.5 degree tilt. In a way, it's an accident of nature. So look at the effect that this has. The axis of the Earth is tilted toward the sun at this point. The sun shining overhead on the northern hemisphere. And it will shine overhead somewhere in the northern hemisphere no matter what the rotation of the Earth. All day long it will shine overhead in the northern hemisphere. 3 months later, the sun has gone through 90 degrees of its orbit, and the sun now shines overhead at the equator. 3 months later, the Earth has gone another 90 degrees around, and the Earth is tilted in the opposite direction relative to the sun, and the sun now shines overhead in the southern hemisphere all day long as the Earth rotates. 3 months later, we're back to where we were again. The result in the sky is that the ecliptic does not lie on the celestial equator. The ecliptic is a tilted circle, the big circle tilted by 23.5 degrees relative to the celestial equator. So what we see when we stand on Earth is that the sun must cross the celestial equator twice over the course of the year, once going north, once going south, and sometime during the year it will be as far north of the equator as it can get by 23.5 degrees, and then it'll be as far south of the equator as it can get by 23.5 degrees. Viewing it from any given location on the Earth, we then see when the sun is at these crossing points, which are called the equinoxes, the sun will rise exactly in the east, be up for 12 hours, set exactly in the west, and be down for 12 hours. Days and nights are equal, hence the term equinox. We have 12 hours of sunlight, 12 hours of darkness. Now, there are two crossing points, once where the sun crosses the equator going north, once where it crosses the equator going south. At the crossing point going north marks the first day of spring. The sun crosses the equator northbound on roughly March 20th of every year. We celebrate the first day of spring. It keeps going north for 3 months until it hits its farthest northerly point, 23.5 degrees north of the celestial equator. At that point, it begins to turn around and go back. That most northerly point is called the summer solstice. The word solstice has to do with sol, Latin for sun, sol, standing still. It doesn't stand still, but for a long period of time, it looks like the sun is not changing its angle relative to the equator. So the sun is going to be very high in the northern hemisphere sky. It will rise in the northeast. It will set in the northwest. You will have more than 12 hours at mid-temperate latitudes. You will have more than 12 hours of sunlight. You will have fewer than 12 hours of darkness. So you have long summer days and short summer nights. The sun is very high in the sky. You'll get your maximum heating. 3 months later, the sun is back to the ecliptic again. And we're back now to the autumnal equinox, which the sun passes around September 23rd. It then plunges into the southern hemisphere of the sky, appears low from northern latitudes, high in the sky from southern latitudes. When it reaches its most southerly point, 23.5 degrees south of the celestial equator, we mark it as northern hemisphere, beginning of northern hemisphere winter. That takes place around December 22nd, and then it goes back up again toward the equator. And we start the whole thing all over again. Now, you have a beam of sunlight. Pretend the sun is high in the sky. The beam of sunlight is shining directly down on the Earth. You have a shaft of light coming down. The Earth is heated entirely by the sun. Oh, there's a little bit of geothermal energy, a little bit of radioactivity, but that is very, very minor compared to the amount of energy that we get from the sun. It's basically sunlight that causes the warmth of the Earth. As sunlight shines, pretend straight down, that shaft of light will heat a small area of Earth. That is, you're concentrating the light into a small area. Whereas if the sun is hitting the Earth like this, that same shaft spreads itself out over a very broad area, and the amount of heating you have per unit area is much lower. Consequently, the Earth cools off when the sun appears low in the sky, and it heats up when the sun is high in the sky. The tilt of the axis, the obliquity, is the entire cause of the seasons. Northern hemisphere summer, the sun passes not overhead necessarily, but very high, and you'll get your maximum heating for a very long time because the sun will have a high northerly position for many, many days, many weeks at a time, and you'll get a lot of heating. Maximum heating will take place a month or two after the solstice, and then it will cool off down to the first day of winter. It'll continue to cool off as the sun comes back up, and by the time we reach March, it's starting to warm up outside. The difference in distance, the variation in distance from perihelion to aphelion does make a slight difference. All other things being equal, perihelion takes place in northern hemisphere summer and aphelion in southern hemisphere winter. So the southern hemisphere seasons on the Earth, all things being equal, would be a little bit more severe than the northern hemisphere seasons because you have to add in the effect of this varying distance. However, if you look at the globe of the Earth, you'll see that things aren't equal at all. Look at where the continents are. Most of the continental landmass is in the northern hemisphere, whereas most of the southern hemisphere consists of oceans. Water is a wonderful heat sink. It absorbs and releases heat very slowly, so it moderates out the seasons. And the variation in distance between the Earth and the Sun is completely lost in the difference in distribution of the land masses on the Earth. So it has nothing to do with the seasons whatsoever. The whole thing has to do with the tilt, with the obliquity of the Earth's axis. Now, this has some other interesting effects. Since the Sun can get no farther than 23.5 degrees from the Earth's equator, the sun can shine overhead on the Earth no farther than 23.5 degrees from the Earth's equator. Tropic of Cancer, the maximum southerly limit where the sun can be overhead. The sun can be overhead only between 23.5 degrees north, 23.5 degrees south. The southern limit is called the Tropic of Capricorn. In old times, You go back 2,000 years, 2,500 years, the sun was in the direction of the zodiacal constellation Cancer when it was at the summer solstice. Another way of saying that the summer solstice was in Cancer at that time. That's why it's called the Tropic of Cancer. Because of this 26,000-year wobble of the axis, very slow wobble called precession, discovered over 2,000 years ago. Because of that, the vernal equinox slowly shifts its constellation positions. It used to be in the constellation Aries. This is why Aries tops the newspaper horoscope charts. It no longer is. The vernal equinox is in the direction of the constellation Pisces. The summer solstice is in the direction of Gemini. It used to be in Cancer. If you were doing this now, you'd call it the Tropic of Gemini. It's a historical artifact. Back in the old times, the winter solstice was in Capricornus. Now it isn't. It's in Sagittarius. It's shifted over, but it's a memory of 2,500 years ago when people were first beginning to learn their astronomy. Go to the other extreme. 90 minus 23.5 is 66.5. Remember circumpolar stars from the last lecture. If you're at a latitude of, let's make one up, 40 degrees north, the north celestial pole is 40 degrees above the horizon, and any star within 40 degrees will not set. It will be circumpolar. Now go up to a latitude of 66.5 degrees north. The north celestial pole is very high in the sky. Any star, any body within 66.5 degrees of the pole is going to be circumpolar. If it's within 66.5 degrees of the pole, it'll be 23.5 degrees from the equator. That is, on the first day of summer, if you're at a latitude of 66.5 degrees north, a complement of the obliquity, the sun becomes circumpolar. It doesn't set, and you have a midnight sun. We can look up here, and sure enough, there's a little dotted line around the Earth at 66.5 degrees called the Arctic Circle. 66.5 degrees south latitude, called the Antarctic Circle. These are zones above or below which the sun can be circumpolar sometime during the year and never set. This includes a significant portion of the state of Alaska. The northern point of Alaska, up at Barrow, Alaska, at 71, 72 degrees north, has several days of circumpolar sun, has a couple of months of circumpolar sun, in which it never sets, and then it has an equal number in the wintertime where the sun never rises. If you go up to the north pole of the Earth, if you stand on the north pole, the Earth is oriented like this, such that the equator of the sky is on the horizon. If the equator of the sky is on the horizon, then on March 21st at the North Pole, the sun will rise. And as long as the sun is in the northern hemisphere of the sky, you will have daylight. So at the North Pole, you have 6 full months of daylight. The sun reaches its maximum elevation above the horizon on June 21st. It's not very high. It's up for 24 hours, 6 months a day, and it's cold up there. The duration of the sun above the horizon doesn't have very much to do with the temperature. It all has to do with the elevation above the horizon and how much heating you're getting per unit area on the ground. So this is, in a sense, a demonstration, again, of the seasons. On September 23rd, the sun will set at the North Pole. You'll have a period of twilight, twilight being that part of the evening where the sun is illuminating the Earth's atmosphere, not the ground, but the atmosphere, and it remains light for a period of time on the ground. So you'll have a period of time in the after the sun sets at the North Pole, and then you'll have about 4 months of perpetual darkness. And when it's fully daylight at the North Pole, it is dark at the South Pole, and vice versa. So the tropics are the places where the sun can shine overhead sometime during the year. Above and below the Arctic Circle are the places where you'll get full sunlight for at least 24 hours. At the Arctic Circle, the farther north you get, more and more sunlight you get, the more period of darkness you'll get in the wintertime. The cultural history of this is very, very deep. Imagine yourself as a tribesperson of long ago, or an old farmer from thousands of years ago, and you don't understand what's going on. The sun is a god. Every year the sun gets lower and lower, and it doesn't take much to correlate, especially if you live outside, how far the sun is above the horizon with the temperature. The sun goes down farther and farther and farther. It's getting closer and closer to the horizon. Your elders, the priest of the tribe, will say, it's okay. It's going to be okay. We'll do the magic incantations and we'll bring the sun back up again. But maybe you've done the wrong thing. Maybe the tribe has done the wrong thing. And the sun will drop farther and farther down and it will never come back and it will freeze and we'll all die. It goes down farther and farther and farther. And then once again, everything works right. The sun comes back up again and we're saved for another year. Now, what are you going to do if your life has been saved once again? It's party time. So we have a whooping party when we learn the sun comes back up again. Do we have a holiday around that time? Some people might jump in as New Year's. No, Christmas. Christmas. Think of the cultural history of Christmas. Christmas is a time that was taken by the early church fathers as a memorial, in a sense, to the birth of Jesus Christ. It had nothing to do with the origin of Christmas. Think of what you do at Christmas time. You bring out lights to celebrate the darkness, the bringing back of the light of the sun. We bring a tree into the house. That has a lot to do with Christianity, doesn't it? Now, you try to explain this to a Martian, why we have these odd symbolisms that have nothing to do with one of the major religions of the earth. And it has to do with the fact that Christmas, as a solstice holiday, long predates the religious holiday. You can find all manner of holidays that string out along these points. The winter solstice, the vernal equinox at the time of the birthing of things, Easter, Passover. Summer solstice. Shakespeare wrote a play about the summer solstice, Midsummer Night's Dream, when all the little people came out and frolicked and had a party. Many cultures celebrated an autumn holiday. The Jewish New Year is around the time of the autumn holiday. It is pinned to the autumnal equinox, in fact. And then back to the winter solstice again. And like most people, of course, that gives us maybe a few parties a year, but we really like more parties than that. So hey, how about a party in between the winter solstice and vernal equinox? We can at least celebrate the vernal equinox on its way. So we split the difference halfway between the winter solstice and the vernal equinox. And I'll let you think about this a little bit. Halfway between, we have a little celebration called Groundhog Day. It's an astronomical, it really is. It's an astronomical holiday. It comes to us from an old English holiday of a different name. But it's a ritual of the coming of spring. May Day Eve. Back in the old days, you'd wrap ribbons around your maypole. It's halfway toward summer. The English have and the Scots have another celebration in August, the halfway point. We don't, but the big party is halfway between the autumnal equinox and the winter solstice. Let you think about that one a minute, too. What do? Oh, we have all kinds. We dress up in costumes. We go out and get candy from the neighbors. And it's the celebration of All Saints' Day Eve, Halloween. Groundhog Day, Halloween, they are astronomical holidays. They're called cross-quarter days, and they're genuine astronomical holidays. Everybody always wants a party. The cultural history is incredibly deep, all over the world. In the south of England is a ring of stones, 3 meters high. Doesn't matter. They're big stones, set up like this with capstones on the top in a big ring. If you stand in the center, there is another stone to the outside. And on the first day of summer, the sun rises directly over that stone. It's a calendar, an ancient calendar, among other things. It was a place of religious veneration for a people long gone. In places in the United States, there are rings of stones where the Native Americans did exactly the same thing. Mounds. Everybody has done this. They have created part of their culture where the sun rises, where the sun sets. We've sort of displaced ourselves by that now by simply the use of the calendar. We do mark the days. We do mark the dates. We have to synchronize somehow the rotation of the Earth with the orbit of the Earth. 365 is not a terribly friendly number. In fact, it's 365 and a quarter, which makes it even unfriendlier. And there are some cultures where they just put 360 days in the calendar, and then when the 360 days are up, everybody stays inside for 5 days and just ignores them. Maybe they'll go away and then walks outside, and we start the whole thing all over again. Our civil calendar tries to reconcile all of this by having 365 days in a year and then adding an additional day every 4 years to make it 365 and a quarter, which is very close to the actual number of days within the year. But it's not exactly 365 and a quarter. It's 365.2422. We're a little bit shy. So Julius Caesar's astronomers, showing how important astronomers are, of course, at all times, because you couldn't do this without astronomers, would set this up with the leap year every 4 years. But by this 15th, 16th century, the seasons were getting out of sync with the calendar. So Pope Gregory the 13th hired some more astronomers. We don't get employment very often, as you can see. Hired more astronomers to figure out what to do with the calendar. They jumped the vernal equinox from, I think it was March 11th, back to March 21st, where it was in the 3rd century, when there was a big religious council, and then dropped 3 leap years every 400 years on centuries not divisible by 400. So the year 2000 was a leap year. But for all of you who can live long enough, the year 2100 will not be a leap year, to the intense confusion of everybody at the time. This averages things out to 365.2425, which makes it almost perfect. It's called the Gregorian calendar. England and its colonies went over to it in the 1700s. George Washington was born under the old calendar, died under the new calendar. You'll sometimes see old style or new style for this. We wind up with a very nice calendar. The Jewish calendar tries to synchronize the motion of the moon within it, which is why the holidays get a little bit offset from the civil calendar, but there they solve it by putting in an extra month, the 13th month, which snaps the New Year back pretty much, or close at least, to the autumnal equinox. The Muslim calendar, on the other hand, ignores the sun altogether and simply uses the moon. The months begin at the new moon, and the Muslim months cycle throughout the year. So there are a variety of ways of solving the problem. The Mayans solved in a way that's still not entirely understood by everybody, with an almost hopelessly complex calendar. All is a result of the Earth spinning on its axis, going around the sun like this, like a dancer, rotating as it goes. We've set the sun now into the pattern of the sky. It's time now, in the next lecture, to look at what these patterns are and at the cultural history of the constellations, where they came from, and how we organize all of this. With 8,000 or so stars visible to the naked eye, you've got to start giving them names and somehow. So let's see how we organize it the next lecture down the line. Thank you.
After listening to Lecture 3, a student posed this question to Professor Kaler. What happened when Pope Gregory reset the calendar? Let's listen to the professor's response.
The resetting of the calendar in Pope Gregory's time was kind of a traumatic event. They had to drop 10 days from the calendar to skip from where the vernal equinox had moved to, the date that it had moved to, back to March 21st. It had been originally set at March 25th in Julius Caesar's time, but for religious reasons it was placed at the 21st in Gregory's time. Well, this was commanded by the Pope. So it had the background of religion to it, the imprimatur of religion. So there weren't really any heavy problems at the time, except, of course, that the Catholic countries went over to the new calendar, but the non-Catholic countries weren't about to do anything that the Pope had decreed, so they stayed on the old Julian calendar. So we were running 2 calendars at the same time. This presents a serious problem for commerce, as anybody can imagine. Finally, England and its colonies went over in the 1700s, by which time the date of the vernal equinox had drifted 11 days away. So they dropped 11 days out of the calendar. But since there was no imprimatur of religion at this time, and this was basically a political event, there were calendar riots throughout England and what became the United States, because people thought that days were being stolen out of their lives. And in a self-fulfilling prophecy, many people died in the riots. That's exactly what happened. But politics reigned supreme. We did go over, everybody went over to the civil calendar in roughly the mid-1700s, and here we are today operating on an almost perfect system called the Gregorian calendar.
This ends Lecture 3. Astronomy, Earth, Sky, and the Planets. Lecture 4, Stories in the Sky, Constellations.
I left you last time with the sun moving against the background of the constellations. We talk about constellations a lot, but what really are they? Where are they? Who made them up? How many of them are there? Why are they there in the first place? In this lecture, we're going to look at the ancient constellations. We're going to see something of their origins. Look at the modern constellations, kind of a surprise. Very few people know that there are such things as modern constellations. And then conclude with a relatively good, hard look at how we organize the sky and something about star names, where they came from, both from ancient times through relatively modern times to what we do now. There are millions of stars with names, tens of millions of stars with names, even if they simply come down to coordinate systems. And we'll look at the whole thing, starting with the very most ancient of times. There's a lot of misconceptions about constellations. First is about astronomers and constellations. There's sort of a feeling that the whole purpose of the astronomer is to know the constellations, know where they are, check on them every night, and make sure that they're all there. I would say about 80% of all astronomers can't identify constellations, don't know where they are, don't know what they are, or where they came from, because most come into this field from physics. They come into it from a point of view of pure science and pay little attention to the constellations at all. I find them charming, and I find them instructive, and they are useful even today in terms of naming stars. They're also a wonderful vehicle for getting the kids out into the backyard to look at nature. So many have been brought into science in general, not just astronomy or physics, but into science through the fascination of the stars and through the constellations and learning them. So let's go on a nighttime tour and take a look and see what they are and what we actually have up there. Another misconception about constellations is that they're supposed to look something like what they're named after, and it's a rare one that actually does. One thing to keep in mind throughout this whole lecture is that constellations are commemorative of things. They don't necessarily have to look like what they're supposed to be. They don't portray. There's no artist up there drawing a bear or a man or a bunny. They are representative of something that was important to the people of the time. They have two basic purposes. One is sacred, the other is secular. The constellations of the zodiac, the constellations through which the sun goes over the course of the year, have deep sacred meanings. Many cultures, in fact most cultures, have probably invented their own. The one that we use, what we consider our Western constellations, came to us from times past. We don't even know where they originated, from thousands of years ago. They were translated by the Greeks, the ancient Greeks, into their own stories, and they were handed down to us through them. Take a look at the constellations of the zodiac, picking out a few of them, starting with, say, the top of your newspaper horoscope column. Aries, the ram, where the vernal equinox was so many years ago. A ram. Taurus, the bull. Gemini, twins. Two people, warrior twins yet. Cancer, the crab, another animal. Leo, a lion. You can go through the whole set and you find powerful fertility symbols that have to do with planting, that have to do with harvesting, where the sun was at a particular time of year. Virgo, a virgin. Libra, scales. It's kind of odd. I thought they were all animalistic. Zodiac, from zoo, the circle of animals. Libra is a relatively modern invention, only a couple of thousand years old, that was translated from its original form as the claws of Scorpius, the scorpion. Yet another strong figure. Sagittarius, a centaur, half man, half horse, another strong figure. And then we go through Capricornus, a water goat, and I don't want to get into that any deeper. I'm not entirely sure what a water goat is. Aquarius, the water bearer, and Pisces, the fishes, representing a wet quarter of some time. You can almost see the seasons fall out from the constellations of the zodiac. So they have sacred meanings. This is where you find the sun. This is where you find the moon. There are 12 ancient constellations of the zodiac because the moon goes around the earth approximately 12 times in a year. Goes through its phases 12 times a year. So every time you reach a different new moon or a different full moon, the sun is in the next constellation of the zodiac over. Many of the artifacts of today have come down from times like this. 7 days of the week, 7 moving bodies of the sky, the quartering of the moon. We'll see this in the next lecture. The other meaning of the constellations is in storytelling. But you get away from the sacred. If you go all across the sky, we've got birds, we've got heroes, we've got gods, we've got all manner of things up there. Try to imagine yourself out in the desert where these originated. We think they came to us from ancient Babylonia, and it's important to remember that every culture has invented constellations of one sort or another. The Chinese had somewhere around 30 constellations of their zodiac, one for each day of the lunar orbit. Native American Indians had something quite different from one coast to the other. Each tribe had its own culture, so to speak. They were important to everybody. But it's probably more important where you can actually see the sky rather than in rainy areas where it's difficult to do so. So let's go back to our own, what we call Western constellation lore, and think about how some of these may have originated. You're out in the desert and it's been a long day herding the goats or whatever it is that you're doing. And people in ancient times were very much like people now. They had to have recreation. You didn't just finish work and go to bed. You had to have entertainment. What kind of entertainment? Well, you might dance, you might sing, or you'd have a tribal storyteller. It was one of the most honored positions in the tribe. The storyteller was often passed down from father to son, mother to daughter, and you tell the ancient stories of the tribe. And then you're sitting around under a nighttime sky, and the storyteller is saying, look up there, look, see that pattern up there? That's whatever, Orion the Hunter. That's the little boys. That's the sisters, perhaps. That's something maybe the American Indians would have said. Let me tell you about them. And they launch into a long story that can go on for hours about how that particular group got in the sky and how the gods put that group up there. Now, it may or may not look like what it's supposed to be. Corvus the crow does not look like a crow. It's a box of stars. No more than that. You have a lot of trouble figuring out how to get the bear out of Ursa Major, the Great Bear. Yet some of the other constellation patterns just jump out at you. Orion the Hunter really does look like a human being, and many cultures have called that particular pattern a human being. The stars are arranged kind of at random, not entirely so. And the patterns are not uniformly distributed. They're just random groupings of stars. So some things will look like what they're supposed to be, some won't. In some constellation patterns, the stars are actually physically related to each other, either forming some kind of clustering or some other organized pattern where they were all more or less born together at the same time. But in most cases, when you think about the three-dimensional quality of the sky, the constellations have no physical meaning at all. They're just a bunch of stars that happen to be aligned in more or less the same direction that form some kind of pattern. If you were to take anybody who did not know the constellations out into the evening, that person would begin to pick them out all by him or herself. The human brain and eye are wonderful at picking out patterns. So let's take a look at some of the things we actually have out there. The most famous constellation, probably in the northern hemisphere, is the Big Dipper. Aha, it's not a constellation. We have to discriminate between official constellations, those handed down to us by the ancient Greeks, and what we call asterisms or informal constellations. Many of them there are, and they can vary all over the world. Some people picking out one group, some people picking out another group. The Big Dipper, which is known in England as the Plough, you see, it depends upon your nationality or where you are. The Big Dipper is a small part of what's called Ursa Major, the Great Bear. These constellations that we use in English-speaking countries carry Latin names. You see a whole cross-culture of the world when you begin looking at constellations and constellation patterns. Ursa Major, the Great Bear. It doesn't look much like a bear, but if you start relaxing your imagination, pretending you're 5 or 6 years old, and just let the imagination wander, maybe you can see it. The bowl of the Big Dipper makes the hindquarters of the bear, and then there's the long bear's tail, which is the handle of the dipper. And then if you look carefully, you see three little pairs of stars that kind of represent the bear's feet or his tracks, which the ancient Arabs called the leaps of the gazelle. Something entirely different. Every eye sees the sky is somewhat different. And then you might see a long snout, and then maybe you might make out the pattern, but it's kind of forced. Again, it's commemorative of the bear. The story, you ever seen a bear? You ever take a good look at one? Their tails are not very long. They're little bitty things. How do you get a bear in the sky? Well, you very carefully. You have to do this carefully. You sneak up. You can't let the bear see you. You sneak up in back of the bear. You grab the bear's tail, and then you whirl it around your head, and you throw it off into the sky. Of course, that stretches out the bear's tail, which is why the bear has a long tail. If you're a good storyteller, you can string this out for an hour and a half without any trouble at all. And you've got the Little Dipper, which is the asterism of Ursa Minor, the smaller bear, and there I'm lost altogether. I, even with my imagination, can't see a bear out of that. And the handle goes in the other direction. So we have two bears up there, and we have two asterisms within the bears. So many are the formal constellations, far more are the asterisms, or the constellations of the people, so to speak, the informal constellations. There are 48 recognized ancient constellation patterns, the ones that were handed down to us from truly ancient times. We don't know when they were invented. Probably 3000 BC, somewhere around then. They were picked up by the culture of ancient Greece. The first mention we have of them is in Homer. And the Greek poets and storytellers began to tell their own stories, that is, wrap their own myths about the more ancient constellation patterns, until they became what we now consider the ancient Greek constellations, but they were ancient even to the Greeks of the time. They were cast in their final form by Ptolemy. Claudius Ptolemaeus, the astronomer, the last famed Greek astronomer and librarian at Alexandria. He wrote a magnificent textbook, the textbook of the time, called the Syntaxis. The Arabs knew it as the Al-Majesti, the great book, in which he set down all the astronomical knowledge of the time, including a set of 48 ancient constellations, which have been passed down to us 2,000 years later, and the ones that we still use today. One of these constellations was Argo. It's the ship of the Jason and the Argonauts. Huge thing. If you know Orion, and we'll get to that in a little while, way down below, down to the left of Orion, hard to see from mid-northern latitudes. It was broken up in the 19th century, not as you break up a ship, but the constellation was separated into three parts: Puppis, the hull, Carina the keel, and Vela the sails. So that gives us 50 ancient constellations once we consider the breakup of Argo. And that's what has been passed down to us. And these are the ones that people generally like to learn. There are two great icons of constellation lore from the northern hemisphere. One, of course, is Ursa Major, the Great Bear, or the Big Dipper. The other is Orion. Orion, the great Greek hunter. If you find either of these, they will, with a small star map, lead you to find others. That is, you can use stars within them as pointers to eventually the entire sky. So those are the first two that I at least try to tell people to locate. And they're the first two that most people do locate because they're so bright. Orion is a beautiful 7-star figure. You can almost see a human being looking down at you with a 3-star belt, 3 stars right on the celestial equator, a bright reddish star up here at his right shoulder, down here at his left foot, another bright bluish star. Outstanding figure that was known to the ancient Arabs as Al-Jawza, and my apologies for the pronunciation because I'm sure it's not correct, but she was a mysterious woman. We don't know where she came from. Yet another example of a culture showing Orion, which we see in our wintertime as a human figure. Orion's accompanied by 2 hunting dogs. Down and to the left, you take Orion's belt, points to the dog star, Sirius, the brightest star in the sky. It looks for all the world like a dog standing on its hind legs, one of the constellations that looks like what it's supposed to be. You look over to the upper left of Orion, and you will find the smaller hunting dog, which is just 2 stars. You can't get the figure of a dog out of it. It's commemorative again. It's not supposed to look like anything. The 3 bright stars of Orion, Canis Minor, the smaller dog, Canis Major, the larger dog, making a magnificent asterism called the Winter Triangle of 3 very bright stars. The constellation patterns are made of stars of all different brightnesses, and this is a good time to introduce a subject called magnitudes. You can make a little more sense out of constellations with that. Around 130 BC, the subject goes back a long ways, one of the greatest of all Greek astronomers, Hipparchus, suggested that we divide the stars up into 6 brightness groups. The brightest were called stars of the first magnitude, at least that's what we call them in English. Stars, the faintest ones you could see, were called stars of the 6th magnitude, and everything in between. The Dipper stars are generally 2nd magnitude. The North Star is 2nd magnitude. Strangely enough, we used this system over 2,000 years after it was invented. It's been quantified, put on a very careful scale. We can measure stars to the 1,000th of a magnitude unit now. All of this done in the 19th century, yet it all harkens back to early Hipparchus. Young eyes can see down to 6. I've known people who could see to 7th magnitude. Older people, you lose a little bit with age, maybe 5th, but the sky is filled with these faint stars. There are only 20 first magnitude stars, 20 or 21, depending on where you want to actually get the cutoff. Many, many more second than the number of 3rd, 5th, 6th, and so on. With telescopes, you see fainter than that, 7th, 8th, 10th. Hubble Space Telescope sees down to 30th, but that's far removed from any discussion of the constellation patterns. Orion has 2 wonderful first magnitude stars. The stars of the belt are 2nd, most of the other stars. That's why this constellation just jumps out at you. In a northern hemisphere winter with the clear skies and the dry skies, they just sparkle and twinkle at you, making the most magnificent of figures. There are many other groups. In fact, it's easier to learn them by groups, and many stories that are told about them. Perhaps the most famous is the Perseus myth. If northern hemisphere autumns, you'll see rising up from the northeast, Cassiopeia, which goes around the sky opposite the Big Dipper, the two acting like a giant clock. You can actually tell your time by where they are. Cassiopeia was, I'm a storyteller. We're sitting around the campfire. We're all staring, what is the storyteller going to tell us next? Cassiopeia was an ancient queen of Ethiopia. She was married to Cepheus, a dim bulb of a constellation, probably reflective of Cepheus himself, apparently. Anyway, Cassiopeia and Cepheus had this beautiful daughter named Andromeda, and you can see her rising up above the western horizon as a long, graceful curve of stars. They bragged, or Cassiopeia bragged, that her daughter Andromeda was more beautiful than the sea nymphs, and you didn't say this about gods and demigods, Neptune's daughters. Well, he took offense at this and had Andromeda chained to the rocks at the coast of Ethiopia to be ravaged and to be eaten by Cetus, the great sea monster, which also appears in the sky. Well, Perseus, who was not terribly far from Cassiopeia in the sky, 2 beautiful streams of stars in the autumn sky in the middle of the Milky Way, had been assigned, you can assign a hero to do something, to kill the Medusa, which was a figure with hair, snakes, so horrible one look would turn you to stone. And Perseus was a pretty bright hero. How do you kill somebody you can't see? So he polished his shield, pulled out a sword, cut her head off, put it in the bag, and went on his flying horse, Pegasus, which rises as a great diamond of stars, the great square of Pegasus in autumn skies, flying back home, and there's Andromeda chained to the rock. And what's a good hero going to do but to go down there at the last minute, pulls the Medusa out of the bag, shows it to Cetus, turns him to stone, takes Andromeda home to Cassiopeia and Cepheus, marries Andromeda, and they live happily ever after, except poor Cassiopeia. Neptune's still a little annoyed, so he makes Cassiopeia ride over the pole in her throne upside down. Now everyone's enthralled. You know, things haven't changed much. What do we do here when we're all done for a day of work? We all go home and we sit around the campfire. And who are our most important people in some ways but our storytellers? And what's the campfire? It's called television. Used to be called radio. Used to be called the piano. But it's a way of us all getting together, and things haven't changed much, have they, over the centuries? Well, the Greeks named the obvious figures, but many are the spaces in between the obvious figures where you don't have much in the way of bright constellations. The Greeks called them the amorphous regions, and they were presumably some area where if one were to do a great deed, the gods could rearrange the stars and place you in the sky, a blank canvas, so to speak. When astronomy really began to become a science at the Copernican Revolution in the 1500s, there began to be a need to fill in the blanks, so to speak. And besides which, the Greeks, who were up at 38, 40 degrees north latitude, couldn't see the deep southern skies around the south celestial pole. So the explorers who first went down there began to map the sky and come up with new constellation figures of their own imagination, and brought a few back to be drawn by the northern astronomers. And then other astronomers began to fill in the blanks between the ancient constellations. So between about 1600 and 1800 AD, We had the era of the modern constellations, of which there were countless numbers, probably 100 or more that were created. Any astronomer worth his salt would make up constellations, try to curry favor with the king maybe, or just to make himself famous. Not very many made it. Some were more or less reasonable. You have Monoceros, the unicorn, right in the middle of the winter triangle. We have such patterns as Lynx, the lynx, Lacerta, the lizard. But then you have artifacts of your own time. The ancients made constellations from what they knew, from their own culture. So what do we have in the modern constellations other than the few animals that were added in? Fornax, the furnace. Sextans, the sextant. Octans, the octant. Then there was quadrans, the quadrant. That got a little boring after a while. We got all three of them. And some of them just got silly. Machina electrica, the electric machine. And the list just goes on and on. It gets to be pretty funny after you read it for a while. They started breaking up old constellations. Edmund Halley had the right idea. He created a modern constellation called Charles's Oak after Charles II in hopes that the king would do something good for him. And the king actually did. He made Cambridge University apparently give Edmund Halley a master's degree because of the honor that Halley had imposed upon him through his constellation. By the 1900s, the sky was a mess. Everybody had different constellation patterns. It was getting difficult to name stars. So in the 1920s, the International Astronomical Union, the organization of professional research astronomers, said, enough. We're going to adopt the 50 ancient constellations, which include many of the storytelling genre, many single ones, Cygnus the swan, Lyra the harp, Aquila the eagle, and so on, the three bright stars of which make the summer triangle, and we'll pick 38 of the modern constellations, and we'll throw the rest away. So we wind up with 88 that neatly divide the sky, and just to make sure, they put little dotted lines all around them, nice rectangular lines, so that every star belonged uniquely to a specific constellation, and finally we have the sky in place. With a lot of other silly ones out there that are kind of hard, they're kind of fun to look at. We have Musca australis, the southern fly, but fortunately Musca borealis, the northern fly, got swatted, and we don't have to deal with that one anymore. But there are many others that are in a way, equally silly. But what would we do if we were to do it now? We would have running shoes in the sky, computers. We'd have things of our own culture. 500 years from now, they'd be laughing themselves silly over what we picked out. They do have a real meaning. They are useful in partitioning the sky into small groups. Star names have a very long history to them. They come in a variety of forms. The most obvious is proper name. The brightest star in the sky is Sirius. The first magnitude stars in the northern hemisphere, the brightest are Arcturus, Vega, and Capella. You'll learn these after a while. We use the proper names for about the top 20 and a smattering of some of the second magnitude stars as well. They almost always have something to do with either their appearance or their position within a constellation. Sirius, for example, comes from a Greek word that means searing or scorching, very appropriate for the brightest star in the sky. Arcturus, it's the end of the southern star of Boötes, the herdsman, which rides the sky behind the Big Dipper or behind the Great Bear. It comes from the word arctos, Greek for bear. It means the bear driver. So you get an idea of where these names came from. Well, most star names, however, are a few are Greek. A small number, like Regulus and Leo, which means the little king. A few of them are Latin, but the vast majority are, interestingly enough, Arabic. The Greek culture, and this is grossly oversimplified world history, the Greek culture passed down to Alexandria in northern Egypt. From there, much of it passed, of course, into Rome, which adopted much of Greek culture and the Greek constellation lore, in fact, much of the Greek religion. And then much of this also passed down into the growing powers of ancient Arabia. After the burnings of the library at Alexandria, we lost a great amount of Greek literature and Greek culture, but it had been translated for us into Arabic. Much of what we know about it comes from the ancient Arabic texts. The ancient Arabs viewed Greece as culturally as almost their center. They took all of Greek astronomy into themselves and dropped a lot of their own constellation lore and began to name the stars in Arabic after their position within the constellation. So we have such stars as Deneb, which means tail of Cygnus the swan. And then there are these Arabic names were retranslated back into Latin in the Middle Ages by people who didn't really understand Arabic very well and just made a mishmash out of the original Arabic names. So if you excuse the pronunciation, Betelgeuse comes from a term in Arabic meaning the hand of the central one, and it got reduced to just one word from a phrase, Betelgeuse, which we call now, which is often mistranslated as the arm or the armpit of the giant. It means nothing like that at all. Many of these names have no real scholarship behind them. We don't even know what they mean. You try to use most of these words on any Arabic-speaking person, they would have no idea of what you're talking about. You have to go deep into how the name was corrupted back into Latin. Nevertheless, probably 80-90% of all the star names in the sky, and there are a couple of thousand of them, are of Arabic origin. You can't remember all of these. There are many to recall. So in the year 1600, around the year 1600, Johannes Bayer, the famous German astronomer, took the stars that were measured by an earlier astronomer named Tycho Brahe, who we will encounter a little bit later, and plotted them on a map and called the brightest one within the constellation Alpha, second brightest Beta, and he didn't follow the rule very well. Sometimes it was done by position, so it only more or less, the Greek letter sequence only more or less goes by the brightness, but mostly the brighter stars in the constellations, the alpha stars. And then you tack onto that the Latin possessive case of the constellation name. So Alpha of Orion in Latin becomes Alpha Orionis. Beta of Orion becomes Beta Orionis. So all good astronomers have to know there are 88 constellations and there are 88 Latin genitives or possessives, or you have to know where to look them up at least so you won't sound too terribly ignorant when you talk to other astronomers about them. Well, there's only 24 Greek letters, and that means that you don't get a chance to name too many stars within a constellation. So enter John Flamsteed around the latter part of the 1600s, who was the first astronomer royal and who had been assigned by the crown to come up with good star positions for the purpose of celestial navigation. He observed a large number of stars with very high precision and laid them out in order of the sky's longitude. The sky has a coordinate system much like latitude and longitude on the Earth. It's called right ascension and declination. Right ascension is the sky's analog to longitude. It's just the angle measured eastward from the vernal equinox, and declination is the sky's version of latitude. It's exactly the same thing. So he listed his stars in order of coordinates within a constellation, and others later, probably Halley and Newton, although no one quite knows for sure, numbered them. So we have now the Flamsteed numbers. The first star whose distance was measured was 61 Cygni. Vega, as a proper name, the alpha star of Lyra the Harp, Alpha Lyrae. It's also 3 Lyrae. So now we've got the Flamsteed numbers. We can go quite a bit fainter with these. And then we want to go fainter yet, and at that point we've really got to start using catalog names. So we dispense with the constellations and then simply use the coordinate names of the stars all the way around the sky in a variety of catalogs that go fainter and fainter and fainter into the depths. Any given star might have a dozen, 2 dozen, 3 dozen different names depending upon what catalog it's in, and it can be quite confusing to translate one to the other to the other. The most famous is, and I love this because they're the HR numbers, they're Harvard revised in the Yale Bright Star catalog, and it had to do, of course, with beginnings at Harvard, translation to Yale, in which you simply number all of the naked eye stars all the way around the sky in order of right ascension from the vernal equinox, irrespective of the constellation. And then there are other catalogs that take you fainter down to 10th, 11th magnitude. The Hubble Guide Star catalog takes you down to 15th magnitude. As we'll point out a little bit later, each magnitude set, 5 magnitude sets, is a factor of 100 in brightness. So a change of 1 magnitude is a factor of 2.5. You go fainter very quickly, even with a small increase in numbers. When you get into the telescopic catalogs, we have somewhere around 15, 20, maybe even 100 million stars that have names. Astronomers have taken it upon themselves to be the namers of the stars, by the way. Anybody can go out and name one, but the professional astronomers pretty much ignore it and go on with their own catalog numbers. The top numbers are still known. Thousands of years after they were born, the top stars are still known by their proper names. You'll see professional articles about Arcturus and Rigel and Betelgeuse and Deneb and all the rest of the first magnitude stars. Beyond that, you tend to use Greek letter names, then Flamsteed numbers, and finally the variety of catalogs. And allowing not only all the naked eye stars, but every star you can see from a typical backyard telescope to have a name associated with it. It's a long way we've come from ancient Greece. And it's well to remember, too, that you shouldn't be too provincial about this, because every culture has different constellation patterns and different constellation lore. You go down into South America, they name the dark patches in the Milky Way. The Milky Way is the band of light around the sky, which is the disk of our galaxy. If you look at it carefully, you see that it's not a uniform disk. It's chopped up with all manner of dark, thick clouds, which we know now are clouds of interstellar dust, out of which stars are actually born. The Incas of Peru and Chile named constellations after these dark patterns, these spots in the Milky Way. The North Americans didn't do that because the spots are not as prominent up here. So everybody had their own spin on it. The Pleiades, the Seven Sisters star cluster in Taurus, which could be considered an asterism on its own, was known as Colcha in Incan literature. It was a basket. It was a harvest basket. Whereas in the Northern Hemisphere, to the Greeks and their predecessors, it was the Seven Sisters, the daughters of Atlas and Pleione. The Western constellation lore has pretty much taken over the sky. It's outside of, say, Chinese, Japanese, some of the Asian constellation lores where we have the documentation that goes back thousands of years. Many of these others have been lost. We know very little now about South American constellation lore other than what's been resuscitated for us by some modern anthropology. Much of the North American native lore is being lost as well, unfortunately. And it's fascinating to see what other cultures have done with what we sometimes consider the ancient Greek constellations, which aren't really Greek at all, but come down to us from truly ancient times. And I think next time you go out in the backyard and look at these constellation patterns, you might think about the fact that although stars slowly shift their positions in the sky, not over 3,000 or 4,000 years, and you're seeing the same patterns that Homer saw. You're seeing the same patterns that Aristotle saw. And you're thinking maybe some of the same thoughts that they did. It's a direct link with ancestors thousands of years before we lived. Thanks.
After listening to Lecture 4, a student posed this question to Professor Kaler. Why do we call our galaxy the Milky Way galaxy? Let's listen to the professor's response.
The Milky Way has a very deep lore. Not all cultures would have called it that, but it looks like a river. And it's white. It's a white band. And it looks like milk. It looks like somebody's taken a jug of milk and literally spilled it across the sky, which is the obvious origin of the term. It was often considered a pathway of souls to heaven. That was a very common belief, because nobody knew what it was. It was just this broad band of light. It is strikingly beautiful. In a dark sky, you get the least little bit of artificial lighting, and it just sort of all goes away. You really have to see it in a dark, moonless sky. And then you can't possibly miss it. You do not have to look for it. You look up in a northern hemisphere August evening, and there it is in all its stunning glory. And as a celestial river, it was often thought of a way of the gods bringing water to water the crops, filling the oceans. Many other stories told about it as well. The constellations, although they're rather denigrated these days even in the 19th century by professional astronomers, still have a very great use to us. First of all, they bring the kids out to look. I think that's their most important use. But secondly, they divide the sky up into reasonably small, organized areas. If you said about some incident regarding the United States, it means it's much more vague than if you said it happened in Montana. It's the same thing. I could say to somebody, hey, there's a new comet tonight. Go look in Canis Major and you'll find it. Nobody will have any problem. Anybody who knows the sky will know when Canis Major's up at any time of the year. Go look, there it is. Rather than say, there's a new comet. Where? Oh, I don't know. That doesn't work too well. So they divide the sky up into manageable portions just for informal use. And they're also, of course, used for the naming of stars. The Greek letter system is based upon constellations. The Flamsteed numbers are all based upon constellations. Sure, there are old ways of doing it, but they're still professionally used. Even in the early days of radio astronomy, when we first began to find bright, discrete radio sources in the sky, they were named after constellations. First bright radio source in Sagittarius was called Sagittarius A. First one in Cygnus was called Cygnus A. And then they found hundreds, if not thousands of others, and the system broke down. Yet everybody still knows Cass A, Sagittarius A, Cygnus A. We all know these, and we all know what they are. So the names are still useful to us. The constellations provide a good background for the naming of things and for the partitioning of the sky into relatively small areas. And it, again, is a charming link with the past that I hope never fades.
This ends Lecture 4. Remember to visit this course's webpage at www.modernscholar.com, where you'll find additional information about the lectures that you just heard. Astronomy, Earth, Sky, and the Planets. Lecture 5, Romance of the Moon.
In the last lecture, we looked at the constellations, the background of the sky, and one of the most important sets of all the constellations, the ecliptic, which forms the background of the motion of the sun. But there are many other moving bodies of the sky as well, the most important of which, certainly the brightest of which, that anybody can recognize is the moon. This lecture is called The Romance of the Moon, one of the most beautiful objects in the sky. And in here, we're going to look at the phases of the moon, what really causes the phases of the moon, not what most people think cause the phases of the moon. The correlation between the phases and the rising and setting times of the moon, why you can see it in the sky sometimes and why you can't. Sometimes why you can see the whole outline in the early evening, why the moon looks so big when it rises as at full phase, what it has to do with the calendars, and then at the end we'll look at eclipses of both the moon and the sun to see where they come from and why we don't see them all the time either. The moon is in orbit about the Earth. It's our closest neighbor. It's 238,000 miles, about 380,000 kilometers away from the Earth. It's the only other place to which humans have actually gone. Sure, we've sent robotic craft all the way out to Neptune and beyond, but we've only walked two of the planets of the solar system, the Earth and the Earth's moon. It orbits the Earth rather than the sun. That is, the Earth and the moon together orbit the sun, with the moon going around the Earth. So we have to add additional movements here. We have not just the rotation of the Earth, but the orbit of the Earth, but we've got the movement of the moon going around the Earth all at the same time. The moon moves through a set of phases over the course of just about a month. It takes 29 and a half days, namely just short of a month, which is where our month actually comes from. We speak of so many months. We say what we really mean is so many moons ago. There are 12 months in the year because the moon goes around the Earth approximately 12 and a half times a year. But we have in our civil calendar taken the phase month and stretched it out to 30 or 31 days to get the months to fit the moon. You can hear it in the word itself, month, moon. You find the same thing in other languages of the world, that the term for the month has come from the moon. It is the most obvious calendrical pattern there is outside of the day and the year. The phases are commonly misconstrued as having something to do with the shadow of the Earth falling on the moon, which is why the moon changes its apparent shape in the sky. That is confusing the phases of the moon with eclipses. Eclipses involve shadow phenomena. The phases of the moon are caused by our seeing different portions of the sunlit side of the moon over the course of the month as the moon goes around the Earth. You can demonstrate it rather easily, even in your mind, by thinking of the sun out in space at a great distance, the moon in orbit about the Earth in different positions, and imagining looking at the daylight side. The sun illuminates one half of the Earth's hemisphere. It also illuminates one half of the lunar hemisphere at the same time. Now, when the moon is situated exactly, or more or less, I should say, in between the Earth and the sun, you are looking at the nighttime side of the moon, and it disappears. You can't see it. That's a phase called the new moon. You're beginning the new phase cycle. Both the Jewish calendar and the Muslim calendars begin with the sighting of the new moon, or with the new moon, I should say, or sometimes with the sighting of the first crescent when the moon first comes out of new moon. Now, bring the moon a quarter of the way around. Quarter the orbit. Now the moon and the earth are side by side with the sun illuminating the front half of each. From the earth, you will see one half of the illuminated face. You'll see the other half in night, in other words, invisible. And you will see a half moon in the sky. Astronomy is famous for confusing vocabulary. The word half moon and quarter moon mean exactly the same thing. They just refer to two different things. At the half moon phase, you are seeing half the illuminated apparent disk from the Earth, but the quartering means that the moon has gone a quarter of the way around the orbit. It takes about a week to do that, which is one of the origins of our period of time of the week. That and the 7-day week coming from the 7 moving bodies of the sky, all ancient knowledge. Now, when the moon is halfway in between, or roughly halfway in between, the new phase and the half phase, or the first quarter as it's called, from the Earth you're looking at mostly nighttime side and a little sliver of daylight, and the moon will appear to be a crescent in the sky. Now take the moon to the other side of the Earth, opposite the Earth. Now, from the nighttime side of the Earth, you are seeing the full daylit side of the moon, and we call it full moon. That takes about 2 weeks after the new moon. We bring the moon around to its third quarter, 3/4 of the way around, and again you're seeing mostly daytime side, half the nighttime side. You have the third quarter through the crescent, and then you're back to the new moon again. In between third quarter and full, we call it the gibbous phase. It's a growing phase as it heads toward full, what we call the waxing moon, and on the other side it's a waning phase as it goes from full through gibbous, where you're seeing mostly daylight, a little sliver of nighttime, and then third quarter and back to new again. It all has only to do, and nothing more, with the amount of illuminated surface that you see. The moon goes through its daylight and nighttime phases, nighttime stages, I should say, just like the Earth does. One of the curiosities about the moon, however, is that you can see dark spots on it. These are, as we will find out later, large impact basins on the moon that have been filled with dark lava. They are the figures that make the man in the moon as seen from the Earth, and you will see that they never change their relative position. They're always in the same place as the moon goes around the Earth. The moon is in what we call synchronous rotation relative to the Earth. That is, as it goes around, it keeps one face pointed toward the Earth at all times. This is a result of tides that are raised by the Earth on the moon, something we'll talk about when we get to discussing the physical natures of these two bodies. But if the moon keeps one face pointed toward the Earth at all times, it must rotate relative to the sun. So if we stand here at new moon, put the moon in between the Earth and the sun, the far side of the moon, the part that we cannot see, is in full daylight. The near side of the moon, the part that we can see, is in night. We can never see the far side of the moon from the Earth because one face points at us all the time. Sometimes it's called the dark side of the moon, which is a misnomer, because that far side, it has to do more with hidden than anything else, that term. The far side of the moon will see just as much daylight as the near side of the moon. At new moon, the far side sees full sunlight. At full moon, it's the near side that sees full sunlight, and the far side is in darkness. If you were on the moon, when we go back to the moon, perhaps I should say, and if you could live through a full phase cycle on the moon, you would see the sun rise in the east and set in the west just like it does on the Earth, except that it would take 29.5 days for the whole cycle to go from sunrise back to sunrise again. Whereas the Earth would just hover constantly in the sky, since the moon's one face of the moon points toward the Earth at all times. The Earth at any given location on the moon will have a constant position, and the Earth will go through its phases in the sky just like the moon goes through its phases as viewed from Earth. Rising and setting times of the moon are very strictly correlated with the phase. Think of the moon at new phase. It's in between the Earth and the sun. As viewed from the Earth, the two must be lined up in the sky. So when the sun sets, the moon sets along with it. New moon rises with the sun, it sets with the sun. Go to the first quarter. Now the two are 90 degrees apart, a quarter of the turn. You start at new and you go 90 degrees around. There's a 90-degree or right-angle separation. When the sun is setting, the first quarter moon will be seen roughly to the south, fairly high in the sky. You can see it in the early afternoon. In fact, the first quarter will rise on the average at noon, cross the sky during the daylight, and then you see it in the evening shortly after sunset, and the first quarter will set shortly about 6 hours after the sun. If it's in the growing or waxing crescent phase, in between the first quarter and new moon, the moon may be only 30 or 40 degrees from the sun, and the crescent sets immediately after the sun, very quickly. You will not see the crescent, or it's very difficult to see the crescent because it's not all that bright, during the daylight hours. As it grows and the moon gets brighter and brighter, then you begin to see the moon in the daylight hours. Now, full moon is opposite the sun in the sky. When the sun is on one side of the earth, full moon is on the other side of the earth, and when the sun goes down, the full moon must come up. So full moon rises at sunset, it sets at sunrise. You can never see the sun and the full moon in the sky at exactly the same time, because they're opposite each other in the sky. When you go 270 degrees around to third quarter, when the sun sets, the moon is way down below the horizon. At midnight, the third quarter comes up, and then it's seen during the morning hours when you go to school or you go to work. The phase is then strictly correlated, entirely correlated with the rising and setting. So sometimes you see the moon in the early evening, sometimes you don't. Depends. You'll see it in the early evening when it's in its crescent phase, when it's in its first quarter, when it's in the waxing gibbous. You'll see it in the morning hours when it's at third quarter, when it's at the waning crescent phase, and then you'll see it rising shortly before the sun. So sometimes it's there in the daytime, sometimes it's there at night, sometimes it's not there at all. From the moon, the Earth has to go through exactly the same phases, but in reverse. If you are standing on the moon at new moon, looking at Earth, you are on the nighttime side of the moon. It's the far side that's illuminated. Now you're on the nighttime side of the moon looking at the full Earth. If the moon is in its full phase, where someone on Earth will see the full illuminated surface of the moon, then someone on the moon is looking at the nighttime side of the Earth, and the Earth is then new. The moon is quite a bit smaller than the Earth. It's about a quarter the size of the Earth. So it doesn't have anywhere near as much reflecting area. And it's made of dark rock. It has no water to speak of. It has no atmosphere, no clouds to reflect sunlight. So it's quite dark. The reflected moonlight has about the brightness of, say, Yosemite, going out to a dark granite rock or even a lava plain on the Earth. The Earth, however, is brilliantly reflective. It's not only 4 times bigger than the moon, which gives it 16 times the reflecting area, but its surface is covered with reflective water and in particularly bright reflective clouds. The moon reflects only a few percent, maybe 10% or so of the light that falls on it. The Earth reflects around 80%. The Earth is actually much, much brighter in the sky to an alien, let's say, than the moon would be. Now, I think everybody's had the experience of going outside at night under a full moon and being able to run, ride a bike, almost to be able to read. Many times I've looked through the window on a winter night when the moon is high in the sky in Gemini, and it's illuminating the outdoors so brightly that it looks like it snowed outside. As bright as that is, imagine the brilliance of the Earth from the moon. When the moon's in its crescent phase, let's say it's waxing crescent phase, then someone on the moon would be looking back at an almost, but not quite, an almost full Earth. The brightness of Earth light on the moon is so bright that it lights up the nighttime side of the moon enough that you can see it from the Earth. When you watch the setting thin crescent moon, you can see the entire outline of the moon, the bright crescent, and then the nighttime side of the moon in a ghostly fashion illuminated by reflected Earth light. It's not a rare phenomenon. You can see it at every crescent. By the time the moon has gone around to 90 degrees in first quarter, the effect disappears and you can't see it anymore, but you'll see it again with the waning crescent when the moon rises just before sunrise. It's a startlingly beautiful sight. Between that and the rising of the full moon, which is equally beautiful, many of the questions about why is the moon so darn big when it rises. You don't notice this effect at the quarters, at the crescents, but you sure do notice it at the full and the near full moon. The subject is still being argued by the psychologists. It is an illusion. It's in fact, it has a name. It's called the moon illusion. The moon looks huge when it rises, and then sometimes it rises red, changes its color as it goes across the sky. The color is simple to explain because when you're looking at the horizon, out through the Earth's atmosphere, you're looking through 30 or 40 times more air than when you're looking directly overhead. And the air selectively absorbs the blue component of sunlight or moonlight, and that's why the sun and moon tend to look reddish when they're on the horizon. But the size is a rather different matter. Nobody quite knows why the mind-brain combination does this, but it does. The common explanation is that when you're looking at the moon on the horizon, you're comparing it with other things on the horizon, whereas when it rises up in the sky, it simply looks smaller because you have no point of comparison anymore. The sun does the same thing, even constellations. You see Orion rising up above the trees. It looks enormous. It gets up high in the sky, it looks smaller. It's entirely an illusion. It has nothing to do with the size of the Earth or anything else. It's unfortunate that it has to be one, I suppose, but it doesn't take away from the beauty of a full moonrise. Now, the distance and the angular size of the moon really do change. The moon's orbit is fairly elliptical. The distance between the Earth and the moon changes by around 5% one way or the other, close to 11% total. So when the moon is closest to the Earth at perigee, it really is angularly bigger than when it is farthest from the Earth at apogee. The difference is about 10%. That is entirely impossible to see with the naked eye. You have to measure it. And it has nothing to do with the moon illusion at all. That is strictly a problem with the eye and the brain. Well, let's put the moon back at new moon. And I talked about the moon being in between the Earth and the sun. Or at full moon, with the Earth being between the moon and the sun. Everything casts shadows into space. You cast a shadow at night on the ground, in the daytime on the ground. The Earth casts a shadow. The moon casts a shadow. The sun is vastly larger. Any kind of demo you kind of rig up at home doesn't quite show the relationships. The sun is enormously larger than either the moon or the Earth. The moon and the Earth therefore cast long conical shadows into space. The Earth's shadow is many times longer than the distance between the Earth and the moon. The moon's shadow is just barely long enough to reach the Earth. Well, it's possible at new moon, at full moon, one would then think that the moon should go entirely into the shadow of the Earth and disappear, be removed from light, and you would then get an eclipse of the moon. And then it's possible when at new moon, you would think that the moon would be right in between the Earth and the sun, and the shadow of the moon should fall on the Earth. You will then get an eclipse of the sun. That is, the moon is getting in the way of the sun. You are in the shadow of the moon. Common experience shows that that doesn't happen very often. The reason is that the moon is not exactly in the ecliptic, but is tilted at an angle of 5 degrees to the ecliptic. The moon is really not very big. It looks much larger than it is because it's so darned bright. The angular size of the moon is only half a degree across, which turns out to be the same as the angular size of the sun. 30 minutes of arc, a half a degree. You could actually stack 180 full moons from the horizon to the point overhead. People don't believe you when you tell them that, but if you make the measurements, it's absolutely true. If you can find the Pleiades, or the Seven Sisters star cluster in the sky in the constellation Taurus, it looks so small you could fit 3 full moons within that star cluster. It's really a very angularly small body as seen from the Earth. It just fools the eye. So the moon has a great ability. The moon's shadow has a great ability to miss the Earth, and the moon has an easy ability to miss the shadow of the Earth. The moon's orbit is tilted by 5 degrees. So normally at full moon, the moon will go up like this over the Earth, and the shadow will miss the Earth, or under it, and the shadow will miss the Earth. And then it will come up around the other side, and the moon will be above the shadow, or the moon will fall below the shadow, and we won't get an eclipse. The only time you can get an eclipse of the sun or the moon is if the moon happens to be crossing the ecliptic at the same time it goes through either the new phase or the full phase. Take a look first at eclipses of the moon. They're the simpler to understand. The moon's orbit is tilted by 5 degrees. The moon's orbit is a circle in the sky, and it has to cross the ecliptic twice over the course of the month. Normally, it'll cross the ecliptic at some random point in between, at the quarters, at the gibbous phase, at the crescent, or whatever, and you can't possibly get anything approximating an eclipse. If the moon is close to crossing the ecliptic at full moon, it will plunge through the shadow of the Earth and be eclipsed. And you will begin to see the shadow take a chunk out of the moon until it's all disappeared if it actually gets immersed. Sometimes only part of the moon gets immersed in the shadow for a partial eclipse. Here we're talking about total eclipses. And then the moon moves entirely into the shadow of the Earth, and it gets extremely dark and practically goes away, the whole event taking a few hours from start to finish. That can happen about twice a year because there's a northern crossing point to where the moon goes north of the ecliptic, another crossing point to where it goes south, and the full moon can take place at either of those points, and typically you'll get, on the average, a little fewer than 2 eclipses of the moon per year. Now, half the time at least, it's going to take place during daylight when the full moon isn't up and you can't see it. The people on the other side of the Earth are going to see it, so you miss easily half of them. By the time you're done with all the ifs and buts, maybe every 2 years or so you get to see a total eclipse of the moon. Sometimes you go for a little longer period, sometimes there'll be a couple in a year, typically separated by roughly 6 months, not quite 6 months. The moon is actually visible during totality when it goes into the into eclipse behind the Earth, into the Earth's shadow. It can be fully immersed in the Earth's shadow, but the Earth is surrounded by a thin atmosphere. And that air scatters and refracts light into the shadow, so the shadow is not completely dark. During a total eclipse of the moon, if you were standing on the moon, you would see a ring of sunlight surrounding the Earth, in other words, the Earth's illuminated atmosphere. Some of that light then gets through to light up the moon. So the moon does not turn entirely black. It usually takes on rather a dull reddish color, depending upon the state of the Earth's atmosphere. Eclipses of the moon are not terribly interesting scientifically anymore. They're used occasionally to catch meteorite flashes, bodies from space that hit the moon and cause a flash of light. And they are often used to test the state of the air. If the air is particularly murky, not much light will get through, and the eclipsed moon will be quite dark. It mostly depends upon the state of volcanic activity on the Earth. If we've had a lot of it, and the air is filled with volcanic dust, then the eclipsed moon is going to be very dark, sometimes almost impossible to see. If we've been a few years without any kind of activity like this, the eclipsed moon will be quite bright. The variation is considerable from one eclipse to the next. After the major eruptions of Pinatubo, for example, many years ago, the moon turned almost black. You could hardly see it during totality. Eclipses of the sun are something else again. The moon's shadow is, on the average, just barely long enough to hit a little shadow spot on the Earth. And whether that shadow spot actually reaches the Earth or not depends upon where the moon is in its orbit at new moon. You can only get a total eclipse of the sun at new moon, when the moon is positioned between the Earth and the sun and crossing the ecliptic at the same time, which has to happen actually at least 2 times a year, as it turns out from the geometry of the eclipse. If the moon is at apogee, at its farthest point, 5% or so farther than average, the shadow spot is not long enough to reach the Earth. It stops short of the Earth. Standing on the Earth, the moon looks angularly smaller than the sun, and it fits over the sun, and you see a ring of sunlight surrounding the moon. It's called an annular eclipse, from annulus, having nothing to do with the year. It's just a ring of sunlight. Now, eclipses are dangerous to try to look at unless you have proper equipment. This is true of any kind of eclipse of the sun. There's a good time to put a warning in here before we talk about them a little bit farther. It has nothing to do with the eclipse itself. It has to do with the brightness of the sun. Nobody would go out on a nice sunny day and say, hey, let's go look at the sun, and just stand there and stare at it. You wouldn't have your vision for very long. You would go blind very, very quickly. It only takes a few seconds to burn the retina. It's no different than taking a magnifying glass and holding it above your hand in sunlight. You will get a burn very fast, and the retina cannot be repaired, and you are partially blind. Do not try to look at the sun or eclipses without proper protection. Now, the eclipse doesn't magnify the solar rays. It's just that eclipses tend to draw the eye. That is, there's an eclipse, let's go look at the eclipse. But to do that, you have to look at the sun. And even if there is a small sliver of sunlight remaining around the edge of the moon, that is just as dangerous as looking at the full sunlight. And you can still burn your eye. Even in an annular eclipse, where the moon is hiding most of the sun, that ring of sunlight is dangerous to look at. The best way of viewing an eclipse is not to try to look at it directly, but to take a piece of cardboard, punch a hole in it with a pin, let the sunlight fall through the hole onto another piece of cardboard or say onto the ground or something like that, and you project a pinhole image. This is lensless photography. It was some of the first way of producing photographs. You can do it in a shoebox. Put a little hole in a shoebox, put a piece of film here, expose the film, and you get a beautiful image of the outdoors. In fact, it produces better images than lenses do. So you are actually being able to watch the eclipse that way. Now, don't look through the hole. People sometimes confuse it and then try to look through the hole. No, don't do that, because then you're looking at the sun directly again, and you don't want to do that. This is a perfectly safe way to do it. Another nice way of doing it is to go under a tree. It's a nice summer day. You're out with a romantic picnic with your partner. On the ground are dapples of sunlight. Now, let's get unromantic for a minute and look at the dapples. They're round. They're round for a reason. Dappling of sunlight through a tree is caused by little pinholes in the spaces between the leaves. You are actually projecting hundreds of images of the sun on the ground that overlap each other. Now, when you watch an eclipse under a tree, you will get the shape of the sun. As the moon goes across the sun, you will see a crescent, and under the tree, all the dapples are crescents. In an annular eclipse, all the dapples are little circles. It's an extremely cute thing to look at, and you can just stand under a tree and just happily watch your eclipse without having to look at it. You can also buy proper eclipse glasses that are professionally made. Do not try to make your own. It's a very bad idea. Darkened film does not work. Do not trust it at all, or any kind of homemade filter or sunglasses. It's a big mistake. Do not do that. Get professionally made solar filters and you're okay. They are sold occasionally at times of total eclipses. Now, for the kicker, is when the moon is near perigee, when it's closest to the Earth, the shadow spot can reach the Earth. But that's all it is. It's a little spot on the surface of the Earth. And as the moon goes around the Earth, and as the Earth is rotating, of course, at the same time, the shadow spot sweeps across the Earth. It's never very large. Several tens of miles, usually. So you have to be in just the right place to get that moon positioned exactly between the Earth and the sun. But when you do that, and you hide the bright image of the sun, out pops this beautiful solar corona. You cannot see it in the blue sky. The blue sky is too bright for it. It's very difficult to see from Earth. It's a large, magnetically heated white crown around the sun that diffuses out and out and out without any real edge to it all. It's a stunningly beautiful sight. At most, an eclipse, when the moon is very close to the Earth at its closest point, these total eclipses can last for only a few minutes, 7 or 8 minutes at the most, and it's all over with. But the corona is so interesting to scientists to look at that they will go almost anywhere to view the outer corona during those few minutes. So these things become scientifically very important. Now that's totality. Any given position on Earth will average a total eclipse maybe every 300 years or so. They're really quite rare for any given location. Globally, they're quite common. They're more common than eclipses of the moon. They have to occur at least twice a year, and you can get as many as 7 solar eclipses a year if the conditions are just right. But any given eclipse is at a very small location. On the other hand, there's a region of partial shadow. If the shadow spot is, say, at the equator, you can go up to, say, Spain, and you can see the moon hiding part of the sun, just not all of it. This is called a partial eclipse of the sun, and that can cover a very large portion of the Earth, and that's what most of us see. But you generally, unless you're very lucky and have one pass over you, you have to travel to see the total solar eclipse, something very, very well worth doing to be able to see the extraordinary phenomena that take place, especially the solar corona. Knowing how all of this works hardly takes away from the beauty and the romance of the moon. I think the more you know about a subject, the more you're going to appreciate it, and the greater the aesthetic quality of what you see. There's little that is more beautiful than a moonrise in twilight, or an examination of Earthlight on the setting crescent. If you understand how the moon works and how the phases work, you can night to night watch the daylight division move across the moon, know where sunrise is on the moon. You can imagine yourself on the moon looking back at the Earth, going through the same phases and imagining what it would look like from there. We've looked at the phases, the rising and setting times, and correlated it most specifically with eclipses, which can take place only when the moon passes new to give you a solar eclipse, only when the moon passes full to give you a lunar eclipse. Again, there's little more beautiful than the eclipses of the moon. You can spend hours watching the moon plunge through the shadow. An appreciation of how it works only enhances the beauty of the experience itself. And again, there's little that's more lovely than the eclipse of the sun, and to watch that glorious corona jump out at the instant that the moon covers the full face of the sun. No danger in looking at that, because the eye is really quite a marvel. As soon as that first flash of sunlight appears, the eye automatically wants to turn it away. And be sure you do, because any look at the sun directly without the proper filtration can be quite dangerous. That doesn't take away from the beauty, of course, of the eclipse, as long as you follow the rules and understand what you're doing. So go on out at some clear night and try to find the moon. Half the time you won't be able to see it because it'll be below the horizon, but eventually you will, and you'll watch it climb above the western horizon, getting a little bit higher each night as it goes through its phases. The first quarter swings around through gibbous to full, and then begins to rise after midnight as it goes through third quarter and back to the crescent and new. The cycle perpetuating itself over and over and over again into the distant future.
This ends Lecture 5. Astronomy, Earth, Sky, and the Planets. Lecture 6. Happy Wanderers, the Planets.
In the last couple of lectures, we've looked at two of the moving bodies of the sky. The brilliant sun moving against the constellations of the zodiac, the less bright but still very nice-looking moon, doing very much the same thing, going through its phases and producing eclipses of both itself and of the sun. Now it's time to look at the other moving bodies of the sky, the ancient planets, Mercury, Venus, Mars, Jupiter, and Saturn. In this lecture, we're going to see how they move and how the ancients dealt with this problem, and trying to explain some of the seemingly erratic motions, and how science began to convert itself, how we really began to figure out how the planets are moving around the sun, which led directly to the discovery of how gravity keeps it all tied together. Start with the planets themselves. The names are evocative of their appearances in the sky. Mercury is seen close to the sun. It zips back and forth with incredible speed. Now you see it, now you don't. It's no surprise that it was named after the messenger of the gods, Mercury. Venus, the goddess of love and beauty, one of the most beautiful objects in the sky. It's creamy light in the morning, so bright it'll sometimes cast a shadow on the ground, so bright you can see it in full daylight. Sometimes seen as the classic morning star, sometimes as the classic evening star. Moving out a little bit farther, Mars. Not as bright as Venus, surely, but it can be number 4, although it usually is not quite as bright as Jupiter. Brilliant reddish body moving through the sky. Not surprisingly, the ancients named it after the god of war, after its kind of orange-red color. Jupiter farther out, usually the 4th brightest object in the sky after Venus, taking 12 stately years to go around the sky, one constellation of the zodiac per year. Again, no surprise that it was named after the king of the gods, Jupiter. Zeus Pater. Jupiter actually means God the Father, coming down to us from the ancient pantheon of the gods. And farther out, Saturn taking a longer period of time, moving slower. Saturn was Jupiter's father in mythology, and we'll deal with the other planets when we can talk about gravity and make a little bit more sense about how they were discovered out there. The planets move in odd, rather irregular ways. The sun and the moon move methodically around the sky, at least seeming to move methodically around the sky, and their explanation is rather straightforward. But the planets seem to stop, turn around, go backwards, make erratic movements that were really rather confusing to the ancients. Even though they came up with explanations for them, their explanations were quite wrong. It was, however, the observation of the movements of the planets that finally led us to the discovery of how gravity keeps all of this together. And we'll tell half of the story in this lecture and the other half of the story in the other lecture, in the next one to come. The planets increase in distance in sort of a geometrical progression away from the sun. Mercury is very close at 4/10 of an astronomical unit, the AU being the average distance between the Earth and the sun. Venus at 7/10 of an AU out. Then you go to 1.5 for us, of course, 1.5 for Mars. Then you make this rather big jump to Jupiter at 5 astronomical units, then almost 10 out to Saturn. the orbital periods progress in very much the same way. You get very close to the sun. Mercury only takes a mere 88 days to go around. This is called the sidereal period. It's sort of the star to star. If you actually stood outside and watched the planet from point to point, going all the way around the sun back to its initial point. The sidereal period for Mercury is but 88 days, very short. For Venus, farther out, it's 225 days. For the Earth, of course, it's our famous 365 days. And for Mars, it takes a little bit longer, almost 2 years, about 1.9 years for it to make the full journey around the sun. The Martian year is quite long. If you lived on Mars, all your seasons would be stretched out about twice as long as they are on the Earth. Then you make the big jump to Jupiter, 12 years from start to finish. I've lived a little bit over 5 Jupiter years. I've watched it go around over 4 times now. It's a fun thing to do. It's easy to find in the sky, and its progression from one constellation to the next through the 12 constellations of the zodiac, very easy to follow. Saturn farther out, first magnitude most of the time, still quite bright, very easy to see. The next one out, barely visible. That one in the next talk. Planets are divided into a number of different groups depending upon the context. We sometimes speak of the ancient planets, the ones I've just talked about, and as opposed to the modern planets, the ones that have been discovered in relatively modern times, Uranus, Neptune, and Pluto. We can also divide them physically, something we'll do more carefully later. The terrestrial planets, the planets that are like the Earth, the Jovians that are like Jupiter, and then the others that are similar to each other when we get farther out into the planetary system. They're also divided, and here is where it's important in our lecture here today, into groups that depend upon their position relative to the sun. Mercury and Venus are called inferior planets, not because there's anything wrong with them or they're any less better than the others, but because they're in a sense below the Earth. They're in between the Earth and the sun, and their appearances therefore are quite different than the superior planets, which are the planets outside of the Earth's orbit, the ones, so to speak, above the Earth, Mars, Jupiter, Saturn, and the others that have been discovered in modern times. The first thing to do, and the easiest thing to do, is to concentrate first on the superior planets and try to make some sense of their motions. The planets and the sun have various aspects in relation to each other, depending upon the angles in between them. And there are 2 that are very important. We can actually relate these to the phases of the moon to some small degree. When the planet is opposite the sun in the sky, with the Earth in the middle, we say that the superior planet is in opposition to the sun. Here is the sun, here is the Earth in the middle, the sun is on one side, the planet on the other, and when you are standing on the Earth and the planet is at opposition, it will rise at sunset, set at sunrise. The moon, at its full phase, is similarly in opposition to the sun, although the term is not very often used relative to the moon. The other important one is conjunction. Conjunction of a superior planet takes place when the planet is aligned with the sun. It'll be on the other side of the sun, not necessarily behind it exactly, because the planetary orbits are all tilted a little bit, and usually at conjunction with the sun, the planet passes above the sun or below it and never really gets hidden. Not that it matters, but because the sun is so bright, you can't really see it anyway. So these points of conjunction and opposition are important in terms of the visibility of the planet. All planets have 2 kinds of period associated with them. The sidereal period, which is the point-to-point period, 12 years for Jupiter, 88 days for Mercury, 365 days for the Earth. The other kind of period is called the synodic period. The synodic period is the period of the meeting of the planets with the sun. The word coming from the Latin word synod for meeting. The synodic period is the interval between 2 successive oppositions or 2 successive conjunctions. Take Jupiter as an example. Jupiter is at opposition to the sun. Jupiter takes 12 years to go all the way around. The Earth only 1 year. As the Earth goes around the sun in its 1-year journey, Jupiter only moves 1/12 of its way. After 1 year, Jupiter has shifted a little bit, and it takes an additional 1/12 of a year to bring Jupiter back into opposition with the sun. That means the synodic period of Jupiter is 13 months. The synodic period is actually the lapping time. A good analogy is a track meet. Let's say that you are a fast world-class runner, and we all meet together to have a race at your local track. You, the fast runner, are on the inside. the first lane. You're running around at, let's say, 5-minute miles. We'll make up a number. I'm doddering along in the outside lane at 10-minute miles. Now we start off together. That is, we are in line with the center at the starting line. I am in opposition to the sun from your point of view. The sun is in the middle of the loop. Now, we both start at the same time. You're going fast, not only faster than I am, but you are going through a shorter journey. And then you catch up to me. When you catch up and pass, I am again in opposition with the center of the track, or of the sun that's in the middle. And the lapping time is the synodic time. It's exactly the same thing as any kind of horse race or a track meet, just the lapping time of one planet relative to the other. And of course, it's always from our point of view because we are the observer standing on the Earth. So the synodic period of Mars is rather long. It's slightly over 2 years. The synodic period of Jupiter is only 13 months because it's farther away. The synodic period of Saturn is only 12.5 months because it's farther away yet. The synodic period is the period of best visibility for the planet. Clearly, the best visibility is going to be at opposition. At opposition to the sun, the planet rises at sunset, is up all night long, and sets at sunrise. We are also closest to the planet at opposition. The best time to observe Mars is always at the opposition of Mars because we are at its closest to that planet, and we can get a better view here from the Earth. The same is true with all of the other planets. Now, a curious thing happens as a planet begins to approach its opposition point. Generally, all the planets, in fact, they all are moving in the counterclockwise direction around the sun in the same direction as with which the Earth goes around the sun. Again, no accident, as we'll see in the last lecture of this course. As the planet approaches opposition, it is going easterly in the sky, in this counterclockwise direction. But as it approaches opposition, the planet appears to stop against the background of the stars. It then reverses its direction and begins to go in the westerly direction. Now, this is entirely independent of the rising and setting. Ignore the rotation of the Earth and the rising and setting of the planets. It's not what we're talking about. We're talking about the motion of the planets against the background of the stars. They generally go in the same direction as the sun, toward the east. But near opposition, they stop, turn around, and go backwards. That backward motion is called retrograde. And it was of immense confusion to the ancients. They didn't know why it happened, but all these gods that populated the sky in the zodiac decided to change their minds at the time of opposition and reverse themselves, having their fastest retrograde motion at opposition, and then after opposition they would stop and turn around and go back in the other direction, in the normal easterly direction. All the superior planets do this on a regular basis at opposition. The inferior planets behave slightly differently. They are closer to the sun than we are, and obviously can't ever be at opposition. You can't take a planet that is inside the Earth's orbit and have it be outside the Earth's orbit at the same time. So the inner planets, Mercury and Venus, the two inferior planets, go through two different kinds of conjunction. The first kind is when the planet passes in between us and the sun. And again, it doesn't necessarily cross the face of the sun. Generally, it'll go above the sun or below the sun. On occasion, it does do that. It transits across the sun. They're rather rare, but it does happen. But that's a quibble. When the planet is in between us and the sun, it's called inferior conjunction. Again, it doesn't mean that it's any worse than any of the others. It just means that it's sort of below the sun. It's in between us. As the planet goes around the sun, it then goes on the opposite side of the sun and goes through another conjunction with the sun, in which is said to be at superior conjunction with the sun. Now, the inferior planets can't ever get very far from the sun in angle because they're inside the Earth's orbit. Venus can never be any more than 47 degrees from the sun. That's its maximum angle. It will occur when you look tangent to the orbital circle of the planet. When that happens, Venus will be as far in angle from the sun as possible, set shortly after sunset, or rise shortly before sunrise. The planet is therefore never visible at midnight because it can't be opposite the sun. It can't be at opposition to the sun. So you'll never see it at midnight. Venus is therefore either the evening star or the morning star, not a star at all. Of course, the term is poetic. It has nothing to do with the planets. All shine by reflected light. They are not visible in the optical spectrum. They're not visible to the eye at all on their own. You shut off the sun, the planets would entirely disappear, whereas the stars would still continue to glow. You watch Venus, and it slowly moves up from the western sky in the evening, getting higher and higher over the months. It then reaches its maximum height above the horizon in the early evening, and then rapidly disappears, passes through inferior conjunction, and pops up in the morning sky as the morning star, and then goes around the sun and the backside of the sun again at superior conjunction. It keeps doing the same thing over and over and over again. Mercury is much harder to see. A 47-degree angle is quite large. You can easily see Venus in a darkened sky. When it's at its maximum separation from the sun, it will set well after sunset, well after the end of twilight, or will rise well before the beginning of morning twilight. But Mercury's greatest separation, because it's closer to the sun, is a mere 28 degrees at best. And that is not enough to get Mercury to clear twilight. It's one of the reasons we know so little about the planet. We get a very poor view from here. Mercury is visible only in twilight, shortly after sunset or shortly before sunrise, making the planet very elusive, so elusive that even though it's quite bright, it's very difficult to see. Because these planets are in between the Earth and the Sun, they go through phases just like the Moon. At inferior conjunction, you're looking at the nighttime side of Venus because it's in between us and the Sun. So it's invisible. As it swings around the sun, you first see a glimmer of crescent. You begin to get a little bit of the daylight side. When it's at the tangent point to the orbit, you then see what appears to be a half Venus in the sky. Now, you can only see this with a telescope, of course. And then when it is at superior conjunction, it will be at its full phase. The brightness of the planet, however, depends upon its maximum reflecting area, which turns out to be, when Venus is very close to us, when it's in the crescent phase. So Venus is at its brightest when it's visible in the daytime sky, just before inferior conjunction in the evening, and just after inferior conjunction when you see it in the morning, and then it fades gradually away, getting closer and closer to the sun when it disappears around and back to superior conjunction. It too will go into retrograde motion, but when it is passing inside the Earth, when it is passing inferior conjunction, when it is between the Sun and the Earth, then it, for a short period of time, as does Mercury, goes into retrograde motion as well. Well, no one really quite knew what to make of these odd movements. The theory developed finally by Ptolemy, the man who set the constellations, the ancient constellations, in order, and who was reasoning from many other Greek ideas long before his lifetime, suggested that all of the planets were in orbit about the sun, after all around the orbit about the Earth, a geocentric system. After all, the Earth was made by the gods, fashioned by the gods. We must be the most important thing there is in the universe. So all of these planets, which were not understood to be real worlds, must be going around us, as does the sun and the moon. The only way he could replicate retrograde motion was by having the planet on an independent orbit whose center was in orbit about the Earth. So as the planet went on the secondary orbit, every time it passed in between the center of its orbit and the Earth, it would appear to go in retrograde motion. It's rather like putting a light on the bicycle rim and watching the light move in this kind of flip fashion as the bicycle goes forward. That is, not putting it at the center, but putting it at the edge. It made no physical sense, but it made some kind of mathematical sense, because you could at least use this to make some kind of predictions about where the planets were in the future. But the idea that the sun was really at the center of the solar system goes back a very long ways, the heliocentric idea. And this was captured by the first in a series of scientists who led us finally to the understanding of the universe and how it worked. The first of these was Nicholas Copernicus, who lived in the middle part of the 16th century, who was a Polish cleric and spent most of his life pondering astronomy and putting together an enormous tome, an enormous work called De Revolutionibus Orbium Celestium, known as De Revolutionibus, a big, thick book in which he developed some of the mathematics for a heliocentric system, where the explanation of retrograde motion, that's backward motion, simply fell out as a lapping of the outer planet by the Earth or a lapping of the Earth by the inner planets. He actually used the geometry of the system to be able to measure the distances of Mercury, Venus, Mars, Jupiter, and Saturn from the Earth in terms of astronomical units. Now, nobody at that time knew the actual size of the solar system. Going back to ancient Greek times, there were attempts of measuring how big this system was. By Ptolemy's time, we knew the size of the Earth from Eratosthenes' work. We also knew the distance of the Moon from the Earth in Earth diameters. We knew how far away the Moon was over 2,000 years ago. Aristarchus tried to get the distance of the Sun through an interesting trick of the exact timing of the quarter. Turns out you can't do the experiment, but his idea was brilliant and correct. And he had the Sun placed farther away than the Moon, although much closer than we know it was today. Nevertheless, without this absolute scaling, you can still get the distances of the planets from the Sun and from the Earth at any time in astronomical units. Copernicus's heliocentric theory, however, didn't really work any better than Ptolemy's geocentric theory. In fact, it was a little bit worse in terms of predicting where the planets were in the future, necessary in some minds, of course, for astrological predictions. Yet, the idea was so aesthetically viable that, in a sense, the cat was out of the bag, and it couldn't be put back in by anybody. Science was burgeoning at this point. People were beginning to understand the nature of things around them, and it became pretty obvious to everyone except perhaps the church at the time that the Earth was not at the center of the system, that it was really the Sun at the center of the system. But how to prove it, how to go about improving it and finding out how the orbits of the planets really were shaped, fell to a man named Johannes Kepler. But first, to a great observer before the age of the telescope named Tycho. Tycho Brahe was a Danish nobleman of the latter part of the 1500s. Slightly after Copernicus's time. He was fascinated by astronomy. He kept a record of the first really recorded exploding star. He didn't know what it was. We do know now what it was, but not then. And this really piqued his interest in astronomy, and he convinced the Danish king to give him an observatory. Not consisting of any kind of telescopes. The telescope had not yet been invented. His observatory consisted of large quadrants, angle measuring devices, basically big protractors that were run by a crew to measure the positions of the stars. And his idea was to measure the best possible positions of stars and the best possible positions in terms of the coordinate frame of the celestial sphere of the planets. He developed a catalog, and this is no accident either. You can see the mystical mind at work here, of 777 stars. Now, Tycho was, by anybody's lights, not a very pleasant person. The rumors come down to us from older times of him as a very contentious man, a warlike man, one who liked to duel at the drop of a hat. The stories are that he had his nose cut off in a duel, and that to scare everybody that he was such a tough guy, he had a silver nose fashioned so that everyone knew what had happened to him, so they'd stay away from him. When the king of Denmark died, his son, the heir to the throne, was so sick of Tycho that he threw Tycho off the island, and Tycho went to Prague to finish the reduction or the calculations of the data so that he could get his precise positions in his catalog of 777 stars. These stars were later taken, by the way, by Johannes Bayer to produce his famous atlas, the Uranometria, where he first put the Greek letters down on paper. Same Greek letter system for naming the stars that we use today. Well, at about the same time that Tycho was leaving Denmark, Johannes Kepler, who was a teacher of astronomy and sometime astrologer actually, and mathematician, was being forced to leave his home in Germany because of religious persecution and wound up in Prague, where he became Tycho's assistant. When Tycho died around 1601, Kepler got the books, so to speak, even though I think the family, Tycho sued him to try to get them back. Kepler took them and went away with them so he could finish the reduction of Tycho's data and the manipulation of Tycho's data. And I think it was Kepler who, more than anybody else, set us on the path to what science is today, because instead of coming up out of the mind with how the planetary orbits should be shaped, he set out to find out how they were really shaped. Copernicus's great mistake, and I don't even know if you could call it a mistake, was going back to ancient Greek times, where the idea was that the circle was the perfect figure, the sphere was the perfect figure, and that everything could be understood out of pure thought. You didn't have to look. You could just think about it and understand how things work. So Copernicus adopted circles for planetary orbits, and they didn't work very well. Kepler said, however, let's use Tycho's data to see what the orbits really were like. He labored for almost a decade. This was pre-calculus. He had to do everything by almost trial and error. It was a very difficult mathematical task. He would try different shapes for the orbits to see what would fit and what wouldn't fit, until finally one day in around 1609, he said it was like it came to him in almost a dream. He said, the orbits are ellipses. Kepler's first law of planetary motion. The orbits of planets are ellipses with the sun at one focus. This means as the planet orbits the sun, it gets closer to the sun and then it gets farther away from the sun. Closer and farther away. This begins to explain the seemingly erratic motions of the planets as they move against the background of the stars. The other focus has no meaning at all. None at all. It's just the one that counts, and the sun is at one focus, and the planets go around the sun on their elliptical paths. He got most of this from Tycho's observations of the planet Mars. The second one, which he came up with at pretty much the same time, was a little bit more difficult. Imagine a planet connected to the sun by a line. This line is called the radius vector. And Kepler realized that the radius vector sweeps out equal areas in equal times. He didn't know why. But this means that when the planet is close to the sun and it goes around the sun, this radius vector, this line connecting the two, to be of an equal area to when the planet is out here at aphelion away from the sun, the planet must move faster. So the planet moves faster near perihelion when it's closest to the sun and slower at aphelion. And he quantified it. The radius vector sweeps out equal areas in equal times. This accounts for the changes of speeds of the planets along the ecliptic path, or close to the ecliptic path where they go. The system worked beautifully. He trusted Tycho's observations so much that he came pretty close. He had a sort of a squash circle at one point that came within a few minutes of arc of Tycho's observations, of trying to replicate Tycho's observations. But he said the great man would not have made an error that large. Tycho was able to get the positions of stars and planets to close to 1 minute of arc, a 60th of a degree, which is the resolution limit of the human eye. It was a spectacular feat that directly led toward Kepler's laws of planetary motion. So Kepler kept working. Many of the lesser lights would have said, hey, this is close enough, I'm happy with it, let's go with it. But he kept working until he replicated Tycho's observations to within about a minute of arc. The next step took him almost another 10 years. Tycho's observations, his good ones, were primarily of Mars, but he had observations of Jupiter and Saturn as well. Kepler was something of a mystic. He believed in the music of the spheres. He actually thought the planets made music as they went around the sun, and that there was some kind of harmony of the motions of the planets. And he found it, in a sense. He found that there was a strict relationship between the period, the sidereal period of a planet in its orbit, and the size of the orbit. The size of an ellipse is characterized by the semi-major axis. It's half of the longest line you can draw in the ellipse. And it's pretty close to being the average distance of the planet from the sun. Kepler said that the square, he didn't say it, he found it, he discovered it, that the square of the period of a planet in orbit about the sun in years, that's relative to the Earth, is equal to the cube of the semi-major axis in astronomical units. Well, how does this work? It sounds kind of complex. P squared equals A cubed, a theme that goes throughout all of astronomy. We simply couldn't live without it. For the Earth, it's pretty trivial. P is 1 year. Semi-major axis of the orbit is 1 astronomical unit. That's the average distance between Earth and Sun. 1 squared, multiply itself, 1 cubed, 1 equals 1, we're done. Take a look at it with Jupiter, which illustrates it a little bit better. Jupiter's distance from the Sun is 5 astronomical units. Its period around the Sun is 12 years. If you know one number, you've got the other. The sidereal period of a planet around the sun is easy to get. All you need to do is go out and look. How long does it take Jupiter to go from the constellation Gemini all the way around through the constellations of the zodiac back to Gemini again? 11.9 years. Make it an easy 12. 12 squared multiplied by itself. P squared is 144. Now you make the lightning quick calculation of the cube root of 144. Not all that easy to do, but you can do it by trial and error. 5 cubed is what? 5 times 5 times 5 is 125, getting close to 144. 6 times 6 times 6 is well above 144. By trial and error, 5.2 cubed is equal to 12 squared, to within the order of accuracy to which we're doing this. If you want to take the numbers and string them out to a high level of decimalization, the relationship is exact. Kepler had figured out his harmonic law, Kepler's third law, of how the planets actually go about the sun and the relationship between the periods and the semi-major axis. From Kepler's 3 laws of planetary motion, you can begin to calculate with great precision where the planets are in their orbit around the sun, which ultimately led to why they go around the sun, which is something we'll address in the next lecture when we talk about gravity. This led to Newton's discovery of gravity, at least to a very high degree, or not discovery of gravity, but how gravity works. Everybody knew about gravity, but we'll talk about that in the next lecture. The next person in line was a contemporary of Kepler, was Galileo. We still had no real proof, in the sense of the way scientists mean proof, of the sun really being at the center, or at least at the focus of the ellipse, at the center of the solar system. The church still wanted us all to believe that it was really the earth, that we were at the center of the universe. And here were the heretics saying, no, it wasn't. It was the sun that was the center. And this could get you in a lot of trouble for doing this. People did get in a lot of trouble. Copernicus didn't get in any trouble because he died about the time his book was published. But one unfortunate named Giordano Bruno was burned at the stake as a result of promulgating ideas like this. Galileo made use of the first telescope. He did not invent the telescope. He heard about it from apparently a Dutch lens makers were making these things. He was the first one to grind the lens for a telescope that was good enough to use on the sky. There were others who were beginning to do the same thing, but Galileo went beyond that. He began to catalog the sky, to write down what he saw, to try to explain what he saw. And he saw marvels. Anyone with a new technological device is going to skim the cream in any kind of science. You put the Hubble Space Telescope up, all manner of discoveries drop into your lap, things we couldn't possibly have seen before. Galileo had the Hubble Space Telescope of the time. And what did he find? He looked at Jupiter. He saw 4 little points of light coming away from Jupiter, and they orbited Jupiter. There was something in orbit about a planet, which by analogy meant that the sun could do the same thing with the planets. It made sense now that the planets could go around the sun. He didn't know why. Nevertheless, they did that. Then he looked at Venus. And didn't Venus go through its phases? Now, in an Earth-centered system, Venus will go through some phases, but not through the whole cycle. If you put the sun at the center, Venus goes through the whole cycle of phases, which is the best possible proof you could get that the sun was at the center of the planetary system. Looked at the moon. He discovered mountains on the moon. The moon was not a perfect surface. It looked an awful lot like the Earth through his little telescope. He even looked at the sun, a dangerous thing to do, and nobody's quite sure of how he did it or how he filtered it, but he did, and he found that the sun was not perfect either. Something known, by the way, to the Chinese 2,000 years before, who had recorded naked eye sunspots. Don't try to do this at home, okay? They had either made some kind of smoke glass filter or they saw the sun at sunrise, but they could see the little spots. So we've known for a long time that the sun had flaws on its surface. Galileo found them. All of this got him in a great deal of trouble. He was called to Rome for the Inquisition. He was told not to say any more about this at all, and he'd be okay. He was put under house arrest for the rest of his life. Dangerous knowledge of the time. All of this set the stage for Newton to put it all together and to develop a theory of how gravity is the glue that makes Kepler's laws of planetary motion actually work. All of this began in ancient times with looking at the motions of the planets around the sun. going up through our own times, beginning with the 1500s, when Copernicus began to put it together and began to show us how the solar system is actually constructed. Through Tycho, through Kepler, through Galileo, and at that point, by 1620, it was all beginning to fall into place. Now, put Newton on the stage in the next lecture, and let's see what happens.
After listening to Lecture 6, a student posed this question to Professor Kaler. How many eclipses do we have every year? Let's listen to the professor's response.
Lunar eclipses seem to be more common of the two, of the solar eclipses, and there are typically 2 per year, on the average. For the solar eclipses, there have to be at least 2 per year. They don't seem to be as common because the moon's shadow covers such a small spot. For any given location on the Earth, they're relatively rare. But globally, there have to be at least 2 solar eclipses per year, and there can be as many as 5. On rare occasion, there can be as many as 7 eclipses if you add the lunar eclipses and the solar eclipses together. 5 solar and 2 lunar. So solar eclipses are actually quite common over the course of the entire Earth.
This ends Lecture 6. Astronomy, Earth, Sky, and the Planets. Lecture 7. Keeping it all together.
In the last lecture, we looked at how Kepler defined how the planets went around the Sun. Kepler, however, didn't know why the planets went around the Sun. He had an idea that there was some kind of force that kept pushing them. He really didn't know. But he set the stage for the greatest scientist that we know, Isaac Newton, to tell us how and to tell us why. In this lecture, we're going to look at the basis of the planetary motions, which will begin to launch us out to the physical natures of the planets. And look at Newton's laws of motion from an astronomical perspective, at Newton's famous law of gravity, how he found how gravity worked. At his replication, just an amazing feat, his replication of Kepler's laws in a wonderful generalized fashion. And then we begin to look at the discoveries that can be made from this, the discoveries of the outer planets, of Uranus, of Neptune, and Pluto, wherein the entire planetary system can be put together. And at the end, a little bit of a tag here, at the final act, where we bring Einstein back on the stage, who really put it all together and showed us where gravity really is. Gravity is an amazing thing. It's like a magic act. Here's a ball. There's nothing between the ball and the floor. And yet, when I let go of the ball, it falls. Why does it do that? Well, gravity, we say. Well, that explains it all, doesn't it? So what is gravity? Well, it's one of the 4 forces of nature, we say. Gravity, a couple of them that involve the nucleus of the atom, electromagnetism, we'll look at them all in their proper order. Forces that act over a distance without anything seeming to be in between. So that doesn't really explain. What is gravity? We don't know. No one. We can explain how it works, but no one knows really what it is and what causes it, what makes it. Not the greatest minds that have ever walked the planet have yet figured that out. Maybe someday we will, but we still don't know. Nevertheless, we know exquisitely well in what way it works, enough so that we can send spacecraft all across the planetary system and hit holes in one, like hitting a golf ball in New York and having it land in the hole in Los Angeles. We know it that well. So what is it and how does it actually work? To understand it, we've really got to go back again to Isaac Newton, who, working from ideas that were formulated originally by Galileo, came up with 3 laws of motion, which were all mathematically correct. That is, he put the mathematics behind it. Newton did so much. Not only the laws of motion, the law of gravity as he knew it then. He was the first person to split sunlight into a spectrum. He invented the Newtonian type of reflecting telescope. He invented the calculus, much to the horror of a great many undergraduates in this country who have to study it, but he invented it. If it's difficult, if you think it's difficult to understand, try to imagine inventing it, along with Leibniz in Germany, and the two had quite a fight, in fact, over who actually was the proper inventor of it. We got to do a little technical stuff here because science often uses a precise vocabulary that is a little bit different than the vocabulary that is used in everyday speech. The ball has a velocity across the table, or as I walk around, I have a velocity. Velocity in science means two things. It means both speed and it means direction. If I move the ball this way, it has a different velocity than if I move it this way. Its speed may be the same, but it changes direction. If you walk around in a circle, then you are continuously changing your velocity because you are changing your direction. Always speed and direction are together in physics. Any change of velocity is called an acceleration. That doesn't mean whether you are speeding it up, slowing it down. You put your foot on the accelerator of a car, you accelerate the car. That's common parlance. But if you put your foot on the brake of a car, you are also technically accelerating it in the technical sense that you are changing the velocity. Drive around a curve at 40 miles an hour. You are accelerating the car. Even though the speed is constant, you are changing the direction. That too is an acceleration. Now, Newton's first law, motion, commonly put in kind of a boring fashion, put a ball on a table. Now spend the day watching it. Fascinating day of watching that ball just sit there. It will do nothing, will it? I think we know that right from the start. It won't do anything until you smack it one, and then it goes flying across the table. The basic idea is that a body in some state of motion is going to stay in that state of motion unless you do something about it, or unless somebody does something about it. Rest, if you just let a ball lie on a table, rest is a state of motion. It's a state of zero motion. Or if you roll it at 1 mile an hour, it'll keep going at 1 mile an hour unless brought to a stop by some force. Well, you know that if you roll a ball across the floor, it stops. But it stops because you're doing something to it. There is a force of friction between the ball and the floor, and that makes it stop. If that force of friction were not there, the ball would roll forever and never come to a halt, ever. To get the ball moving from its state of rest here, you got to apply a force. What's a force? A little bit of a circular reasoning here. Force is anything that causes an acceleration, out of which Newton formulated the famous formula, probably the most famous in physics. Force is equal to mass times acceleration. Or the acceleration is equal to the force over the mass. You can express it in a variety of ways. The greater the force, the greater is going to be the acceleration. But if I apply the same force to two masses, one of which is big and one of which is not, the smaller mass will be accelerated the more. You know, you can push a marble with a force and it will really go sailing along. If you try to do the same thing with a bowling ball with the same force, it won't accelerate very much. All seemingly obvious to us now, but not obvious at all at the time. Newton's third law was that if you're going to have a force or some kind of reaction to force, you're going to have a reaction in the other direction. You can't have an action without a reaction. This, of course, is absolutely fundamental for anybody who flies in a jet airplane or anybody who walks, for that matter, because to walk, I apply a force in one direction and I move in the other. All very, very basic stuff. Newton's laws of motion, which began with ideas of Galileo. Now, given that it requires a force to produce an acceleration, what happens when we drop the ball? The ball falls at an ever-increasing speed. Balls do not fall at a constant speed. They continue to accelerate until they hit the floor or until they hit the ground. The longer they're in the air, the faster they're going to go. Now, the exception to this, or what is air resistance. If you throw a ball from an airplane, it will reach a terminal velocity. If you jump out of the airplane yourself as a skydiver, you will reach a terminal velocity of a couple of 100 miles per hour. That's because air resistance is buoying you up. If there were no air resistance, not only would your parachute not work, which of course is applying a force to your acceleration, but you would keep falling at ever-increasing acceleration at 9.8 meters per second, increase in speed for every second in the air until you smacked into the ground. This is why there are holes in planets from asteroids hitting them, because they're being dropped at exceedingly high altitudes from millions of kilometers away. And by the time they hit the planet, they're going very, very fast indeed. In fact, at orbital speeds. So, gravity is a force that acts over distance that can produce an acceleration. Newton's law of gravity said that for any two masses, put two masses, mass 1 and mass 2, and separate them by a distance d between their centers. One of Newton's great discoveries was that the Earth acts as if all of its mass were concentrated to a point at the center. That is, the stuff on the other side of the center was not acting as strongly as the stuff on the near side of the center, and it all canceled out as if it were all concentrated to a point. So in terms of your reaction to gravity, you might as well be standing on a platform 4,000 miles high from a little dot at the center that had the mass of the Earth, and you'd feel exactly the same way you feel here. So the force that draws two bodies together depends upon the distance between the body's centers, assuming that they're spherical. If they have funny shapes, then you have slightly different rules. You've got to take some kind of an average. But let's just assume spherical bodies. Newton realized by a combination of the acceleration of the falling ball, the acceleration of the moon as it went into its orbit around the Earth, and the realization from Kepler's third law that whatever force was causing the accelerations of the planets had to be an inverse square law. That is, the force dropped off as the distance squared from the sun. He put all this together and formulated his universal law of gravity. And there's a nice little equation that says that the force between two bodies that draws them together is equal to a constant. It's a constant of nature. It's called G, the gravitational constant, which you can determine from the laboratory, and we don't have to deal with that here. The force is equal to this constant times the product of the masses. You multiply the masses of the two in kilograms together and divide it by the square of the distance in meters. Now, that's crucial because that means as you separate the bodies, the force of gravity drops off. If you double the distance, the force of gravity decreases by a factor of 4. It's an inverse square law, but it can never go to zero. The only way you can get it to go to zero is to drive that denominator, that distance between the two, to infinity, and you can't do that. That means every body in the universe attracts every other body in the universe by a force inversely proportional to the distances between them. You can't get out of the Earth's gravity, ever, no matter where you are. It weakens with distance, and of course if you go far enough away, other gravitational fields from other bodies overwhelm the Earth's gravity, and it's inconsequential, but it doesn't go to zero. This is a glue that ties the entire universe together because everything is acting on everything else. A startling idea at the time, and one that worked. Using the law of gravity and his laws of motion, Newton did something truly astonishing. And the calculus, we can't forget that. He reinvented Kepler's laws, but he reinvented them in a marvelously generalized form and explained that Kepler's laws were simply the result of this gravitational force. So we have two different kinds of Kepler's laws. We've got Kepler's laws as he invented them, or as he discovered them, I should really say. The empirical laws, the ones that were derived solely from the observations alone without any idea of why or how they worked. Let's look at them again. That planetary orbits are ellipses with the sun at one focus, the other focus being empty. That the radius vector, the line that connects the planet with the sun, sweeps out equal areas and equal times, which means that a planet close to the sun is going to move faster than a planet far from the sun. And simple old p squared equals a cubed. The square of the period in years relative to the Earth is equal to the semi-major axis of the Earth in astronomical units, cubed, again relative to the Earth. Turns out that Kepler's laws, as he discovered them, are simply special cases of the generalized form that Newton came up with. Take a cone. Think of a paper cup that you'd pull out of a water fountain stand and tip it upside down with a point on top. Clip off the top with a pair of scissors, and the cross section, what you're doing is cutting the cone with a plane. The cross section is a circle. You can imagine that easily. Now cut it at an angle to the base, not perpendicular, not parallel to the base, but an angle, and what you get is an ellipse. Now cut it parallel to the side of the cone. and you will get a circle that has only one loop on one end, and it opens up forever at the bottom. It's called a parabola. And if you cut it at a steeper angle, you'll get an even wider open curve called a hyperbola. These four curves are the conic sections. An ellipse is one, the familiar ellipse, the circle is the other, and the hyperbola is a family of open-ended curves. The parabola is sort of the dividing curve between the family of hyperbolae and the ellipses. Well, what Newton discovered was that orbits don't have to be just ellipses, or in the special case circles, but that orbits are conic sections with the sun at one focus. This allows for open-ended orbits. They occur all the time in nature. Here you are on the Earth. The killer asteroid is coming in from outer space, lining up on the Earth, but not quite. It comes close to the Earth, zips around the Earth in orbit around the Earth on a hyperbolic orbit, and goes back out and never comes back. That's a perfectly acceptable orbit. It's just a one-way orbit. When the Apollo spacecraft were launched, the first ones were launched to the moon in elliptical orbits. They went around the moon and they were destined to come back. The later ones were launched relative to the Earth on hyperbolic orbits, and if something went wrong, they weren't coming back anymore. How do you get a hyperbolic orbit? Any body has what is called an escape velocity associated with it. In the case of the Earth, it's 7 miles per second. I can take a body and throw it up this way, and if I exceed 7 miles per second, 11 kilometers per second, I've put it into hyperbolic orbit around the Earth. We have to think for a minute and pause here to understand what an orbit actually is. We talk about orbits so glibly, one body going about the other. In the case of Newton's generalization of Kepler's first law, we're dealing with any two bodies at all. It doesn't matter what kind of body. It could be two stars in orbit about one another, Jupiter satellites in orbit about Jupiter. It just doesn't matter. Any two bodies. But what exactly is an orbit? Let me take the ball again. I can drop it. It falls. I'm not going to throw it, but if I could throw it in one direction, think of throwing the ball parallel to the Earth. It will immediately fall toward the Earth. It can't help but do that. The acceleration of gravity downward toward the Earth is not dependent upon the motion of the body horizontally. As soon as you throw it, it'll drop. Known to any baseball pitcher. If you fire a rifle, as soon as the bullet leaves the muzzle of the rifle, it will begin to fall. How far the bullet goes depends upon the muzzle velocity, and that's all. Now, you can, of course, point the rifle upward and the bullet will go into an arc, but it will go up, slow down, and then fall. Again, it will always fall. If I can throw this ball fast enough, really throw it hard and fast, the curvature of the Earth comes into play. I'm throwing the ball far enough so that the Earth begins to drop beneath the ball. The Earth is continuously curved, remember. I mean, it looks flat locally, but it's curved all the way around to meet at the other side. And if I could throw this ball fast enough, it's somewhere around 17,000 miles per hour, as the ball went off this way, it would fall, but it would fall at the same rate at which the Earth drops off beneath it, and it would curve around and come back to its starting point, and that would take about 88 minutes or so. I've put the ball in orbit. Now, I've pretended that the ball, of course, is able to go through walls, mountains, and everything else that's in the way. So, which I can't do. However, I can put it on a spacecraft, on a rocket, launch the ball or the spacecraft upward to get it above all the barriers, including the air, which acts to heat it up, an air resistance. And when I get it up to 100 miles or so, I can keep curving it over, keep accelerating until it hits orbital velocity, and it just keeps going around and around and around and around. It's in the Earth's gravity. One of the great misconceptions of orbital mechanics that many newscasters have is that the shuttle is in orbit around the Earth because it's outside of the Earth's gravity. It isn't. It's the gravity of the Earth that keeps it in orbit. If I could magically shut off the gravity of the Earth, the darn thing would just skitter off in a straight line and never come back in a perfect hyperbolic orbit. It would not ever return. It's gravity that keeps the acceleration going. The effect of gravity on the shuttle astronauts is just minimally less than it is down here at the surface because its gravitational force is only falling off as 1 over the distance squared. Now, how does that explain how the astronauts are weightless in space? Well, they're falling. You don't feel weight when you're falling. You feel weight when you're standing on the ground. The reason I feel weight is because it is the mass of the Earth times the mass of me divided by the square of the distance between the center of the Earth and me. That is my weight when I'm standing here. If I climb a set of stairs, I weigh less because I'm farther away from the center of the Earth. If I go on a different planet with a different mass and a different radius, I'm going to weigh something different there. When I'm falling in the air, I am weightless. I don't feel weight until I land. The spacecraft is falling toward the Earth. The astronaut is falling toward the Earth at the same acceleration. There's no differential, so the astronaut feels no weight at all. Orbiting bodies are falling bodies. The moon is in orbit around the Earth, which means it's falling toward the Earth at all times, but it has this horizontal motion that makes it simply go around and around and around and never come back to its starting point. The Earth is falling to the sun. It just can't get there because it has this looping path that never takes it closer to the sun. That's the orbit. And orbits can come in all four of the conic sections. That was one of Newton's great discoveries. The other one is a terribly complicated name to it. It's called the conservation of angular momentum. I got a weight on a string, and I could sling this weight around, and the weight has a velocity. It has a mass, and it has the length of the string. You multiply the three together, and you get what's called angular momentum. Now, angular momentum is conserved in the absence of some kind of outside force. That is, once I get it going, I can bring in the string and the thing goes faster. Because I drop the length of the string, the velocity has to go up to keep the angular momentum constant. This is familiar to anybody who skates, dances, does almost any kind of athletics. How does a skater put herself into a spin? You bring the arms out. You apply the force with the skate, get the spin going, and you lower the average radius of the body by bringing in the arms and watch the skater speed up. If you really want to speed up, you put the arms over the head and lower the radius of the body even further. Dancers do the same thing in a pirouette. Start with the arms out, bring them in, snap it in, speed it up. What happens as a planet gets closer to the sun on its elliptical path? The radius vector shortens. The speed goes up. Kepler had discovered the conservation of angular momentum, and he didn't know it. Newton put it in proper form. This is a crucial point in this course and in any study of astronomy. The conservation of angular momentum pervades this subject. It will come back to it many times over the course of this course. Kepler's third law, generalized by Newton, has kind of a complicated form. Remember that the force of gravity depends upon the product of the masses. Yet Kepler's third law has nothing to do with mass. The mass is not there. Where did the mass go? It seems to have disappeared. Kepler got away with this because the masses of the planets are so minuscule compared with the mass of the sun. They're effectively zero compared with the mass of the sun. The sun dominates everything. Newton put together a formulation of Kepler's third law that included the masses, and it goes as p squared, again, like Kepler's third law, except p is now in seconds. It's in actual physical units rather than in terms of the Earth's orbit about the sun. P squared in seconds is equal to a constant again, constant's well known, times the semi-major axis of the orbit cubed, a cubed, just like Kepler did it, that's fine, except that a, the size of the orbit, is now in centimeters or meters or whatever unit you want to use, real physical units, divided by the sum of the masses. Kepler couldn't know that because what happens is that you have the sum of the mass of the sun plus the mass of the Earth. The mass of the Earth is pitifully small compared to the mass of the sun, 1/300,000th. So you can throw it away. That is, mass of the sun plus the mass of the planet is effectively the same for all the planets because the masses of the planets don't amount to anything. And the mass of the sun is a constant. You throw it into the constants, you wind up with p squared equals a cubed when you put it relative to the Earth in years and astronomical units. If the planets had had masses comparable to the sun, Kepler would have gone crazy. He never would have figured this out. He was just lucky that the planets have small masses compared to that of the sun. In fact, if the planets had large masses compared to the sun, we wouldn't be here anyway, and we wouldn't be having this discussion because for life on Earth probably requires a fairly low gravitational field, as we'll see as we progress through this course. This allowed Newton to determine ultimately the mass of the sun. What's the force of gravity between the ball and the Earth? It's the mass of the ball times the mass of the Earth divided by the square of the distance between the ball and the Earth, multiplied by this constant, which we don't really need to deal with. The acceleration of the ball downward depends upon the mass of the Earth and depends upon the mass of the Earth. Now, one of the things Galileo discovered, he's purported to have discovered, is that the acceleration of a falling body does not depend upon the mass of the falling body. He was said to have gone up at the Leaning Tower of Pisa and dropped 2 masses off. Whether he did or not is irrelevant. You drop 2 masses off, they fall at the same speed. The ancient Greeks thought that they fell at different accelerations. They don't. As I drop the ball, it's falling in the field of gravity of the Earth. The acceleration of the ball depends only upon the mass of the Earth and the square of its radius, or the square of the distance between the ball and the center of the Earth. You multiply that by the mass of the ball, and then F equals ma, and you've recovered Newton's law of gravity. So the acceleration of a falling body is going to depend only upon the mass of the Earth and the distance between it and the center. So all I need to do is measure the acceleration of the falling ball, use Eratosthenes' ancient measure of the radius of the Earth, and I've got the mass of the Earth, which of course is huge. Somewhere around, it hovers in at around 10 to the, just an uncountable number. Now, how do I get the mass of the Sun? Kepler's third law, again, as generalized by Newton. I've got the period, square of the period of the Earth in seconds. What's the orbital period of the Earth in seconds? 31 million seconds it takes the Earth to go around the Sun. I've got the distance between us and the Sun in, let's say, centimeters. You know, I know it in kilometers, 150 million kilometers, and 10 to the 5th centimeters, 100,000 centimeters in a kilometer. I've got that distance. I know all the constants. What do I have left? The mass of the Sun plus the mass of the Earth. The mass of the Earth is inconsequential compared to the Sun. I wind up with the mass of the Sun. Remotely. I don't have to go to the Sun and measure anything. I can't put the Sun on a scale. What I do is to measure the strength of the gravitational field of the Sun at a known distance. This opens us up to understanding the entire universe. You can watch 2 bodies in orbit around each other, get the sum of their masses, and at some point we'll look at how we can get the individual masses. Any 2 bodies, get the mass of Jupiter, watch one of the satellites go in orbit around Jupiter, get the mass of Jupiter. Toward the end of the 1700s, William Herschel, who founded what I call, modern observational astronomy, made an astonishing discovery. Herschel was a transplanted musician from Germany who went to England and was really more interested in astronomy than making music. He brought his sister with him, and the 2 of them began to make telescopes. He made the telescopes. The 2 of them were out there observing any clear night they could get. And one night, 1781, Herschel saw a funny-looking body drift through the field of view. It had a disk to it. He thought for a while it might be a comet, but he followed it, and he announced its existence, and other astronomers followed it, and they realized it was moving along through the zodiac, more or less following the ecliptic path, just like a planet, but farther away. Herschel had discovered the first modern planet, the first planet outside the orbit of Neptune. He called it Georgius Sidus, George's star, after his monarch, King George III, who was the reigning monarch of England at the time, and of course the boss of the colonies of what became the United States. That didn't go down terribly well with the French or with the Germans or anybody else to call the new planet after the King of England. So let's just continue the progression of mythological names. Saturn was Jupiter's father, who was in mythology Saturn's father. In Greek, at least, Uranos, the god of the sky. The next planet out became Uranus. Well, it turns out Uranus is visible to the naked eye, 5th magnitude at its brightest, at opposition, and was seen by many people prior to its discovery. They just thought it was a faint star and didn't know where it was, didn't know what it was. So we had enough information to get a pretty good orbit for Uranus shortly after its discovery. And we realized very quickly that it didn't follow Newton's laws. It was never where it was supposed to be. And it occurred to 2 people, John Adams in England and Leverrier in France, that there might be some other planet outside the orbit of Uranus that was pulling on it. Remember, gravity is always mutual and everything affects everything else. It's not quite correct to say, as it turns out, that the orbits of planets are ellipses. They can't be. The Earth is being pulled on by Mars, by Jupiter, by Saturn, Mercury, Venus. Everything's pulling on everything else. Consequently, the orbit of the Earth is slightly changing. It's only an approximation to an ellipse. A good approximation, but nevertheless an approximation. If you want to know where the Earth is going to be at any given time, you've got to take into account the accelerations of all the other planets in the solar system. A non-trivial job, at least on paper and pencil. Not so bad if you've got a high-speed computer. But they didn't have those back in the early... Hard to believe, isn't it, at a time when they didn't have high-speed computers or PCs. Not in the middle of the 19th century they didn't. So Adams and Leverrier set about calculating where this trans-Uranian planet should be to produce the deviations that we saw. Like so many other things in science, they came up with the same answer at about the same time. Around 1846 or so, Adams sent his results about where this trans-Uranian planet should be to the Astronomer Royal in England, who basically paid no attention to it. Leverrier sent his results to the Berlin Observatory, where they had a good star map. The first night that John Gala looked through the telescope, bingo, there's Neptune, right in the field of view. They had discovered Neptune on paper using Newton's laws of motion and the law of gravity. It was an absolute triumph. This affected all manner of things. In thinking, determinism, if you knew where everything was at any time in the universe and all the velocities, you could know where everything was going to be in the future. No free will. I robbed the bank because of Newton's laws. I couldn't help myself. Not really that way. As we'll find out in a lecture down the line, we can't know where everything is at any one time. It is absolutely impossible. But that does not negate the great discovery, which really goes back to Newton. We found a planet with a piece of paper and pencil before it was actually discovered in the sky. They tried to do the same thing. Uranus still didn't quite behave itself, even when you factored in Neptune. So, hey, maybe there's something out beyond Neptune. So we tried it again, futilely. It took decades, finally, for Clyde Tombaugh, who was hired at the Lowell Observatory in Arizona, to discover little Pluto, 40 astronomical units away, 248-year journey around the sun, which we know now is it a planet, is it not a planet? It's still being argued. And it turns out that Pluto doesn't have anywhere near the mass to affect Uranus. It turns out that the problem was that we didn't have really good enough masses for the outer planets. When the Voyager spacecraft passed by the planets on their hyperbolic orbits, we were able to get good masses for them. Finally, Uranus falls right into place where it's supposed to be. So does Neptune. Everything is well with the world. There is no planet X out there. We have come to the end of the planetary system. With Neptune, if you want to factor in Pluto, that's fine too. And with hundreds of other bodies that lie outside the orbit of Pluto, all too small to affect the inner planets to any significant degree. And largely as a result of Kepler going to Newton from Galileo, we've been able to put our solar system together. It's not really the end of the story. The best observations still slightly evade Newton's laws. It took Albert Einstein to figure out what was going wrong here. The problems with the speed of light. The speed of light is the fastest thing in the universe. Nothing can approach it because light has no mass. So you can't get beyond it. Light has a very odd behavior. If I throw the ball at someone and a person catches the ball at a certain speed, now I run at that person and I throw the ball at the same speed. For me, the catcher catches it at a faster speed, which is why, of course, baseball pitchers lunge toward the plate to add the speed of their body toward the speed of the throwing arm. Cricket players do exactly the same thing. Light doesn't work that way. If I shine a light at you, you'd measure it at 186,000 miles per second. If I ran at you at half the speed of light, the light would still pass you at 186,000 miles per second. That is strictly non-intuitive, but that's the way the universe works. Einstein put together a concept known as space-time, 3 dimensions of space and 1 dimension of time all locked together. And he made the interesting concept, what could happen if you could try to catch a light wave? Run alongside it. You can't ever catch it because no matter how fast you run, it still keeps going past you at the speed of light. The only way to explain that is that your time must slow down. And if you could run alongside the wave, time would stop. Not your clock, not your watch, but time itself. A distortion in time, which also means a distortion in space, And what Einstein realized was that gravity can be explained as a distortion of space-time produced by a mass. Why that happens, we don't know. And there's a slight difference between that and the Newtonian laws. As long as speeds are low, you're okay, but if you start going near the speed of light, all the rules change and Newtonian dynamics no longer works, and you have to use Einstein's theories of relativity. We've gone a long ways here, from Copernicus, through Kepler, through Tycho, through Galileo, to Newton, finally to Einstein. And we understand how it works. We just don't know why.
After listening to Lecture 7, a student posed this question to Professor Kaler. Does the disappearance of another star in the galaxy and the loss of its gravitational pull affect our solar system? Let's listen to the professor's response.
Because the forces of other stars on our planetary system are so weak, it wouldn't affect us at all. And stars do this. They do blow up and, in effect, dissipate their mass throughout the galaxy. In that sense, they disappear. But they're so far away, they wouldn't have any effect on us at all. If somehow, for some reason, Jupiter could magically disappear, it would really make a mess out of the solar system. The orbits of planets would change. It would probably partly destabilize the orbits of the inner planets, in fact. Nobody entirely knows for sure. It wouldn't have much an effect immediately, but it probably would over the long term. We have a very stable planetary system, probably because of the way the planets are put together. Jupiter and Saturn all influence everything else. And there are ideas that the stability of the inner planets is, in fact, due to the very existence of Jupiter. The bottom line in much of astronomy is that there are no things that are really isolated from everything else. You can approximate that, but everything else pretty much affects everything. Everything pretty much affects everything else. Now, it's a matter of degree. If a star in the galaxy disappeared, we wouldn't notice it at all. If a planet in the solar system disappeared, it would have a small impact on the orbits of the other planets. If the sun disappeared, then all the planets would go off in straight lines and never come back.
This ends Lecture 7. Astronomy, Earth, Sky, and the Planets. Lecture 8. Reaching Outward.
We left off the last lecture with one of the four forces of nature, gravity, the glue that holds everything together in the universe. This lecture, Reaching Outward, we're going to start looking at another of the forces of nature, the electromagnetic force. This is going to allow us to look at the natures of the planets, at the stars. Most of the energy in the universe is transmitted by light. So we'll look at light, we'll look at the other parts of the electromagnetic spectrum, the radio waves, X-rays, go through the whole spectrum, look to see how this relates to matter, what matter is composed of, look at atoms, their structure, and finally go into telescopes and how we look outward into the universe. What's light? Everybody's familiar with light. You can't really see light. What you see is the effect of light upon your eyes. But you don't see the light itself. Light is a moving electromagnetic wave. Over the centuries, people have argued about what light actually is. Is it a particle? Is it a wave? It's a little easier at first to think of it as a wave. Think of it as a water wave in a way. It's a flow of energy moving through space. Not in anything. There's no material in which the wave is actually moving. It's an alternation of electric and magnetic fields moving along at the speed of light, 186,000 miles per second, 300,000 kilometers per second, the fastest thing we know of. There's no mass involved in light, and that's why light can actually move at the speed of light. Anything that does have a mass cannot move near the speed of light. Now, Isaac Newton was the first person to decompose light into its component colors. Red, orange, yellow, green, blue, and violet, the principal 6 colors. The color depends upon the wavelength. Our eyes are sensitive to wavelengths somewhat short of about 1/10,000th of a centimeter. Very, very short. These waves carry an enormous amount of energy, enough to activate the chemistry of the human eye. You can also think of light as a small particle. In fact, it's both at the same time. The particle of light is called a photon, and it's almost impossible to describe intuitively. You can think of it in a sense as a little chunk of a wave moving along, although that's not really right, but it's at least one way in which the human mind can think about it. The energy carried by an individual particle of light, an individual photon, depends strictly upon its wavelength. The longer the wavelength, the lower the energy. Shorter the wavelength, the higher the energy. That is, the higher the frequency, the higher the energy. That is, the more waves that hit your eye per second, the higher the energy is going to be. Violet light carries about twice as much energy as red light. The human eye will pick up these photons at different wavelengths and then automatically convert them to different colors. The pure spectral colors are startlingly beautiful, and of course you can see them very easily in the rainbow, which is a natural decomposition of light, sort of a natural prism in the sky, very similar to what Isaac Newton used. The electromagnetic spectrum is the array, the full array of different wavelengths. The human eye is sensitive only to about a factor of 2 or so in the wavelength of light. Once you get to waves a little bit longer than red, you cannot see it anymore. It's still there, and even the skin is sensitive to it as heat. Longer than red, we call it infrared. The infrared spectrum extends out to approximately a millimeter or so. Once you get beyond that, we call it radio. It's all exactly the same thing. Radio waves don't carry very much energy at all because the wavelength is so very long. You can live all your life underneath a megawatt FM broadcasting tower and never feel a thing. It's perfectly benign. The shorter the waves, the higher the energy. You go through the optical spectrum again, and then you get to violet, and you go shorter than violet, you reach the ultraviolet. Shorter than violet and the ultraviolet, the waves get quite energetic. A little bit of this high-energy radiation from the sun sneaks through the Earth's atmosphere, and this can cause sunburns. This is causes tans. It's a natural reaction of the human body to the short-energy waves. Shorter than ultraviolet, by the time you get down to waves that are maybe 1,000th or less than 1,000th, that to which the human eye is sensitive, we call X-ray. Shorter than that, we call gamma rays. Nobody is going to stand in front of an X-ray machine for terribly long. It's an extremely dangerous thing to do. Gamma rays are produced by atomic bomb explosions. You want to stay very far away from anything like this. Fortunately, the Earth's atmosphere is entirely opaque to this kind of radiation, and we're perfectly safe on the ground. Although the sun is producing, for a variety of reasons, producing a lot of high-energy radiation, we don't have to worry about it unless you get into space and you get completely exposed to sunlight, which nobody is going to do. Astronauts with spacesuits are, of course, protected as well. Now, light interacts with matter through the atoms. Almost everything we know about the universe comes to us by way of electromagnetic radiation. Astronomy is not an experimental science. You can't take something into the lab, with some very few exceptions, and examine it. You can't bring a star into the lab and examine it. You can't bring a planet in. What we know about all these bodies comes to us by means of the electromagnetic radiation that these bodies radiate. Electromagnetic radiation from the electromagnetic force, one of the 4 forces of nature, interacts with matter through the atoms that make the matter up. To understand the Earth, to understand anything about astronomy, to understand the very large, we also have to understand the very small. The Earth is made out of somewhere around 90 to 100, depending upon how you want to count them, around 90 chemical elements. The chemical elements are composed of even smaller particles. We have to understand how they're put together before we can begin to understand the nature of the universe. So let's take a good look at atoms and atomic structure. Atoms are decomposed into 3 really very basic particles that probably everybody has heard of: protons, neutrons, and electrons. Now, we call these things particles, but like light, they also have a wave associated with them as well. They have a dual nature, similar to light. Let's keep calling them particles in any case. It's simpler to understand them that way. The proton carries the positive electric charge. The electron carries the negative electric charge, and the neutron carries no charge at all. For reasons that are not at least understood, protons and electrons carry exactly the same electric charge, just opposite directions. The electromagnetic force is extremely powerful. It's trillions of times stronger than gravity. That comes as a surprise because everybody is in the gravitational force of the Earth, in the gravitational field, and you don't really even notice the electromagnetic force. Gravity cannot be balanced by an anti-gravity. There is no anti-gravity. Gravity goes in one direction. The electromagnetic force, on the other hand, is neutralized. There are as many electrons in the universe as there are protons in the universe, and generally things are neutral. So you don't feel the electromagnetic force unless you unbalance it. Anybody who has by accident stuck their finger into an electric light socket knows the strength of the electromagnetic force when it becomes unbalanced. It can kill. It is extremely dangerous. As long as it's neutralized, you're perfectly okay. Now, the proton and the neutron have approximately the same mass, very, very small. They're extremely small particles, about 1/10 of a trillionth of a centimeter across. The electron has no known dimension, and its mass is about 1/1800th or so that of the proton and the neutron. An atom is constructed with a nucleus that consists of protons and neutrons in the center, which is loosely orbited by the electrons. The electromagnetic force, in a broad sense, acts kind of like the gravitational force in keeping a planet attached to the sun. The electromagnetic force keeps the electron attached to the proton. Now, we can't get too carried away with this analogy because it's not like a miniature planetary system. There are science fiction stories that have little people living on the electron going around the proton. It does not work that way at all. The electron is actually characterized as a wave as much as it is a particle, and you almost have to think of the electron as surrounding the proton almost everywhere around the proton. It's not a hard little ball. Again, it's not an intuitive concept. So we go back to the idea of thinking of the electron in orbit, but keep in mind at all times that it's not really an orbital problem. Not really. The problem we face in dealing with atoms, again, is one of scale. It goes back to the old portrait of the sun and the planets that we started this course off with the huge sun and all the huge planets all lined up in a row, completely out of scale. We have the same problem with the atom. The nucleus is extremely small compared to the size of the orbits of the electrons. Let's start with the simplest of all chemical elements, hydrogen. Hydrogen consists of one proton surrounded by one electron. It's the simplest possible atom you can get. What makes it hydrogen is the one proton. We can even get rid of the electron and we still have a hydrogen atom. It's called a hydrogen ion at that point because we've now unbalanced the electromagnetic force and we have a positive charge to the atom. So another name for the proton is simply hydrogen. It's the simplest possible one we can get. You neutralize it by having the electron in orbit about the proton, loosely speaking, that is. Now, the size of the atom is about 100,000 times the size of the proton. There's an enormous amount of empty space. The atom is, in fact, mostly empty space. The real analogy is to go to your favorite ballpark, put a rice grain on second base. That's the proton. The electron is in the outer seats. All the rest of it is empty. It's about a factor of 100,000. This allows for an enormous amount of squeezing room in matter, and it's what allows us to take stars like the sun when they die and squeeze them down to bodies the size of the Earth, and take some stars and squeeze them down to something the size of Manhattan because of the squeezing room. Now, when I look at something solid, realize that it's mostly empty space. It looks solid, certainly, and I can't put my hand through any solid body. The chair you're sitting on, for example, you would think that all the atoms should just pass through each other and you should fall right through it. What you feel as solidity in a body is not really the matter itself, it's the electromagnetic force that keeps you from keeps your hand, for example, from passing through a desk, or keeps you from just walking through the wall. You can try it, run into the wall, and see if you pass through, but I guarantee you're not going to be able to do it because of the electromagnetic forces that are going to stop you. Now, all of the other chemical elements depend upon the number of protons in the nucleus. You go to helium, it has 2 protons in the nucleus, 2 neutrons for most normal helium atoms. Well, the proton carries the positive electric charge. The electron carries the negative electric charge. We know from old grade school teachers that like charges repel each other, opposite charges attract each other. That's why the electron is attached to the proton, because they're unlike charges. They want to attract each other. What are two protons doing stuck together? They are similar charges. They should repel each other. Aha! Enter the strongest of all the forces of nature, the strong force. Sometimes it's called the nuclear force. The electromagnetism and gravity are inverse square laws. As you increase the distance, the force drops off, but it never goes to zero. If you double the distance, the force drops off by a factor of 4. The strong force, on the other hand, acts only over an exceedingly small distance, in fact, only over the size of the nucleus itself. So if you try to put two protons together and you push them closer and closer, they will try to repel each other until you get them within about their own diameter, and then the strong force takes over and makes them stick. Now, in a helium nucleus, you have two protons. But two protons are not really enough to make the nucleus stick together. You need an additional neutron to force the stickiness, so to speak, because the neutron carries the strong force as well. So you throw a neutron in, it doesn't add anything repulsive in terms of the electromagnetic force, it adds strong force, and you lock that helium atom together. Most helium atoms consist of two protons and two neutrons. But there is a kind of helium that's called helium-4 because there are 4 particles in the center. But you can fool around with the number of neutrons. You can take one away. Now you got 2 protons, 1 neutron. That gives you what's called helium-3, which is a part of nature. You can do the same thing with hydrogen. You can take a hydrogen atom and you can stick a neutron to it, and you have what's called deuterium, or a form of heavy hydrogen. Sometimes it's called hydrogen-2 because you have 2 particles in the nucleus. It doesn't affect the chemistry of the body of the atom at all. Now, we can go right up what's called the periodic table, which of course establishes the chemical natures of the atoms, just by increasing the number of protons. Lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, nitrogen has 7, oxygen 8, and we don't want to go through the whole thing. Iron has 26, uranium, which is sort of the heaviest one that naturally occurs on Earth, 92 protons. And then you increase the number of neutrons along with the number of protons. By the time you get to uranium, you've got 238 particles in the nucleus, a very heavy atom indeed. Now, most atoms have a range of neutrons associated with them that allow them to be stable. Hydrogen 1, hydrogen 2 are perfectly stable. About 1/100,000th of the water you drink is hydrogen deuterium oxide rather than hydrogen oxide, H2O. It's a natural part of the world. However, if you stick a second neutron into hydrogen and make hydrogen 3, sometimes called tritium, it becomes radioactive. That is, the nucleus falls apart with the emission of energy. Radioactive elements, isotopes as they're called, the variation in neutrons, isotopes. Radioactive isotopes can be quite dangerous because of the particles they emit. In the old days of the study of radioactivity, we found 3 different kinds of radiation coming out of these radioactive atoms, and we call them alpha rays, beta rays, and gamma rays. Alpha rays turned out to be helium nuclei. Beta rays turned out to be electrons, and gamma rays turn out to be real high-energy electromagnetic radiation. Now, radioactive elements are a natural part of the world. They occur, uranium is everywhere in the earth. In fact, it's the breakdown of uranium deep in the earth that provides a good portion of the earth's internal heat. So we get used to a certain amount of the stuff, and it doesn't really affect us. But if you get too much of it together, it can damage, it can cause cancer, it can kill. Some elements have no stable isotopes at all. A couple of them in the middle, number 43 doesn't have any stable isotopes. But once you get beyond number 83, they're all radioactive. This includes radium, it includes thorium, and includes uranium. And then you can get beyond number 92, number 93, neptunium, number 94, plutonium. Uranium and plutonium are used in atomic reactors to generate heat, to generate electricity. But not uranium-238. You have to strip away 3 neutrons and get uranium-235, which is highly radioactive. All matter emits or absorbs radiation. All matter will emit radiation depending upon its temperature. At a low temperature, the energy inherent in a body is very small. At room temperature, for example, a body will not emit optical radiation, the kind you can see with the human eye. At extremely low temperatures, down near absolute zero, about as cold as you can get, all a body will emit is radio radiation. As you increase the temperature to, say, 1,000 degrees above absolute zero, 1,000 degrees Kelvin it's called, the body can emit infrared radiation. When you get up into the thousands, the body will emit optical radiation, the kind you can see. You can see the effect in a toaster. Put it on in the morning, feel the heat coming out as the elements heat up, and eventually it hits a temperature at which it radiates light. At a couple of thousand degrees, it'll radiate only red light. As you increase the temperature, you begin to move through the electromagnetic spectrum in the optical part of the spectrum. A warmer body will start to emit yellow light. A hotter body yet will emit blue light, and then it will emit ultraviolet radiation, and then it will emit X-ray radiation, and then gamma ray radiation. It's just the opposite of what we tend to read about. The common phraseology has blue as cold, red hot. It's just the opposite. Red light is generated by a cooler star or a cooler body than blue light. From the quality of the radiation and from the amount of radiation that the body emits, you can determine its temperature remotely. This would work with glass melt in an oven, or it would work with a star or with a planet. It's from the quality and kind of radiation that a body emits that we learn what it is made of, and what its temperature is, what its density is. Almost everything we know comes from the analysis of the electromagnetic spectrum. But we have to be able to gather that electromagnetic spectrum. We do that with telescopes. The whole point of an astronomical telescope is to gather as much radiation as possible for a final analysis, whether it is in a photograph, even whether it's in visual examination through the telescope. The first telescope used in astronomy was built by Galileo in 1609, 1610. He turned the telescope on Venus, he turned it on Jupiter, he made an enormous number of discoveries. First telescopes built are called refractors. They use lenses to bend light to a focus. The astronomical telescope is about as simple and scientific instrument as possible. In its simplest form, it's simply a lens that light goes through, the light is bent down to a focus. You can put an eyepiece to examine the focus and see the object, or you can put, in more modern times, a piece of photographic film, a photographic plate, or some kind of electronic detector at the focus and take an image of the object. It's as simple as that. Refractors had their heyday during the 19th century. The largest refractor in the world is 40 inches or approximately 1 meter across, approximately the size of an outstretched hand to the face. You can't make refractors any bigger than that because they're made out of glass, and glass will flex to a certain degree. It's heavy. So when you point the telescope all around the sky, the lens bends a little bit, and that ruins the quality of the image down in the focus. The way around this problem is to use reflecting telescopes. The reflecting telescope was invented by none other than Isaac Newton, the person who first decomposed light into its colors. You use a curved mirror, very similar to a cosmetic mirror. The curved mirror will reflect the light back again to a focus in exactly the same way that a lens will do. Now, you do have a problem with a reflecting telescope because the focus is in front of the mirror. So if you try to look at the object, your head gets in the way and you can't see anything unless the telescope is very large. What Newton did was to put a small flat mirror in the light path. So the light comes down to the large mirror, comes up to a focus, and before it's focused, is bounced off to the side so the astronomer can look into the side and see the object after this double reflection. You can do it with other ways as well. You can put a smaller mirror, again, that will reflect the light back through a hole in the large primary mirror. In principle, there's no real limit to the size of a reflecting telescope. Isaac Newton's was very small, only a couple of inches across. By the end of the 19th century, we were making them a yard across. By the early 20th century, The 100-inch telescope at Mount Wilson in California went into operation. It remained the largest telescope until the late 1940s when Palomar went into operation with a 200-inch or 5-meter mirror. The telescope's still functioning beautifully at Palomar Mountain in California. That was the largest telescope for a very long period of time outside of a 6-meter that was built in the old Soviet Union. Part of the reason was we began to develop electronic detecting devices that effectively increased the size of the telescope by more efficiently monitoring the light that passed through it. So for a period of close to half a century, we went from photographic plates with a very, very low efficiency of light detection up to the kinds of charge-coupled devices, all kinds of electronic devices, the kind of things that you find in high-end video cameras that have almost 100% efficiency. We didn't need to build big telescopes anymore, at least for a long period of time. Once we hit the 100% efficiency mark, then we started building bigger ones. The sizes went up to 10 meters. They're going to go up to 30 meters, 40 meters, perhaps even bigger than that. We don't know what the next century is going to hold, but the plans are eventually to build something perhaps as large as a 100-meter optical telescope. The bigger the telescope, the more light it will gather, the brighter your image, or the fainter the stars, the fainter the objects you're able to see, the easier it is to spread the light out into its spectrum for analysis, the more detailed you can get. Well, we're really pretty limited in the optical part of the spectrum. The human eye samples only a factor of 2 in wavelength. In the 1930s, a radio engineer named Carl Jansky was assigned by Bell Telephone Labs to track down a source of mysterious radio radiation that was causing some interference with transatlantic communication. He built a large radio antenna in Holmdel, New Jersey, and every time the Milky Way went through the beam, through the direction in which his radio antenna was pointed, up went the background signal. He discovered natural radio radiation from the galaxy. Not much was done with this discovery until the 1950s when a tinkerer, I suppose you would call him, a brilliant man named Grote Reber, home-built what looked like a huge satellite dish in his backyard and made the first map of the Milky Way, done by an amateur. At that point, radio astronomy began to take off. Now, radio waves are long, and because of the length of the radio wave, you can't get a good detailed view of an object unless you build a very large radio telescope. A radio telescope is the same as a reflecting optical telescope. You build a big dish with it's a big radio mirror. The light comes down, hits the radio mirror, and bounces up to the antenna, which is actually the detector itself. The largest steerable radio telescope in the world is now about 100 meters across, vastly larger than the biggest optical telescope. At that point, you can't really keep the curve of the dish together. You have to have a perfect paraboloidal surface to be able to reflect the radio waves to the focus where you have the antenna. However, what you can do is to take 2 radio telescopes, separate them, link them by cables, or synchronize their observations with a highly precise atomic clocks, and look at the same object with 2 or more radio telescopes, and you can synthesize the effect of one that is so large that it would span the distance between the 2. The bigger the telescope, the better the resolving power, the greater the detail you're able to see. We have built such interferometers, they're called, as large as the entire North American continent. In fact, in some experiments, almost as large as the Earth itself, which allows us to get exceedingly detailed radio views of celestial objects. We've now expanded these observations through the entire electromagnetic spectrum. Radio waves you can pick up on the ground, at least in certain bands through which the Earth's atmosphere is transparent. The same is true of infrared. But if you really want to span the electromagnetic spectrum, you have to get above the Earth's blocking atmosphere, where you can get at ultraviolet radiation, you can get at X-ray radiation, even gamma ray radiation. So we built satellites that orbit the Earth to observe the entire span. This allows us to see high-energy processes that take place in space that produce nothing but X-rays and gamma rays. Space observatories allow us to see high-energy processes from space that we are completely ignorant of if we try to observe from the ground. The opening of the electromagnetic spectrum is probably one of the great astronomical triumphs of the 20th century. Space observatories, of course, culminated with the use of the Hubble Space Telescope, which launched in the early 1990s, which orbits the Earth. Not a terribly large telescope. It's only a couple of meters across. It's modest by ground-based standards, but it is in the best possible observing location above the Earth's atmosphere. One of the serious problems we have in astronomy is the effect of the atmosphere. Don't say twinkle, twinkle, little star to an astronomer. You get in trouble. It is a nasty thing to look at through a telescope with that star just boiling away, as pretty as it looks from the ground. It's not a nice sight through the telescope because it destroys our ability to see fine detail on a planetary surface or see fine detail in double stars, in any kind of celestial object. You get above the Earth's atmosphere, all the twinkling goes away, the stars settle down, and we get brilliant views. The Hubble has taken some of the best images we have ever had. Now, this doesn't vitiate ground-based observatories, because the ground-based observatories not only can span the go into the radio part of the spectrum, but they also can be built larger than space observatories. So astronomy now uses really a complement of the two, with space observatories observing what we can't get from the ground, ground-based observatories getting bigger and bigger and bigger, and you put the two together and we're able to analyze all the light that comes from the sky throughout the entire electromagnetic spectrum. The telescope itself does little. We need to have a detector of the light at the focus. We can take pictures with cameras. That is, a camera simply holds, in the old days, a photographic plate. Now it holds an electronic device which allows us to take pictures of the sky. We can scan the sky with radio telescopes and take radio pictures. We can take X-ray pictures with X-ray telescopes in orbit about the Earth. Or a more common way of analyzing the light is to use a spectrograph, something that stretches the light out into its component colors that allows us to analyze even the chemical composition of the body being observed. We don't know where the astronomical detection capability and telescopes are going to end. We're building them bigger and bigger and bigger. We're putting them out in space. Eventually, we hope to have some on the moon. There will be nothing better than an observatory on the far side of the moon, which gets us away from all light pollution. No problem with absorption by the atmosphere. We can observe the entire electromagnetic spectrum without any human-made interference. Eventually, it'll probably be done. In the meantime, we'll build bigger and better space observatories. We have had dozens of them in orbit about the Earth that have allowed us to expand our view through the entire electromagnetic spectrum and see the universe as nature intended us to see it. So in this lecture, what we've done is to set the stage for learning the physical natures of the planets and of the other bodies of the solar system, even of the stars, a subject to which we're now going to turn to see how they're composed, now that we know how we can observe them.
After listening to Lecture 8, a student posed this question to Professor Kaler. How much of the electromagnetic spectrum can the eye see? Let's listen to the professor's response.
Atoms and molecules, which are, of course, composed of combinations of atoms, also have another interesting property. They are capable, under certain conditions, of absorbing or emitting light and other forms of electromagnetic radiation at very specific colors or wavelengths. You can look at the absorptions that appear in the spectrum. They look like little lines, little cutouts in the spectrum of the sun or the planets. And you can use the positions of these little cutouts by comparing them with laboratory spectra. You can produce a full chemical analysis of the body being observed. Hydrogen, for example, will selectively absorb a particular band of color in the red, another one in the blue, another in the violet, and so on, at particular wavelengths that are replicated by no other atom. Each atom and each molecule, each ion, an atom with a stripped electron or more, will have a particular set of these absorptions, or reverse it, emissions. They can both absorb and radiate at the same specific wavelengths. And by analysis of these specific absorptions or these specific emissions, you can do a full chemical analysis of the body being observed. Tell exactly the chemical composition of it and the number of atoms that the body is composed of.
Another student then posed this question to Professor Kaler. What other kinds of analyses can we perform on distant heavenly bodies? Let's listen to the professor's response.
The human eye is sensitive to light from about 400 thousandths of a centimeter up to around 800 thousandths of a centimeter. It's only a factor of 2. It's 1 octave out of the electromagnetic spectrum. We see this little tiny cutout of the whole spectrum. With the eye alone, we learn very little about the universe. Fortunately, nature pumps an enormous amount of energy into that little band. It's no surprise, I suppose, that the human eye is sensitive to exactly where stars produce most of their energy. In fact, the peak energy of the sun is in the yellow part of the spectrum, which is exactly the same place where the human eye is most sensitive and can make the best use of sunlight. But beyond the red and beyond the violet, we have no sense of what's going on. We have to use other detectors to learn about ultraviolet, infrared, radio, X-ray, gamma ray, and all the rest of the electromagnetic spectrum.
This ends Lecture 8. Astronomy, Earth, Sky, and the Planets. Lecture 9. Our Domain, Earth and the Moon.
In this lecture, we'll be using a lot of shorthand for the chemical elements. In the previous lecture, we talked about elements like nitrogen, oxygen, uranium. You talked about their isotope numbers. Uranium-238, for example, with 238 particles in the nucleus. It's a lot simpler if we simply use the chemical symbols for them. Instead of hydrogen, we could say H. Instead of helium, He. Instead of oxygen, O. Instead of nitrogen, N. Instead of uranium, U. So instead of uranium-238, it would come out as U-238. Atoms are also combined into molecules. So we have chemical symbolism where we would say if we had 2 oxygen atoms put together, we're not talking about isotopes anymore, but molecules, we would call this the O2 molecule because there are 2 oxygen atoms put together, or the N2 molecule with 2 nitrogen atoms put together to create the molecule. In the last lecture, we looked at the tools of astronomy. What we use to examine the planets, what we use to examine the sun and the stars. Now let's turn our sights to the planets themselves and begin to look at their physical natures now that we know how to examine them. So in this lecture, we're going to look at the double world. We're going to look at the Earth and its companion, the Moon. Really 2 planets, if you don't mind counting the Moon as a planet, and I don't mind doing that at all. 2 planets that orbit the Sun together in space. One large, the other small, with a terrific contrast between the 2. We'll look at the physical natures of the interiors of the bodies, the exteriors of the bodies, what makes the Moon different from the Earth, what makes the Moon cold and dead, what makes the Earth a wonderfully alive, thriving planet, full of life. I have here a piece of a genuine planet, an actual piece of a planet. It's a fairly ugly rock that I picked up out of a parking lot. We pay little attention to these things. It's really quite a remarkable thing. It's made out of mostly silicon, oxygen, heavy stuff from the periodic table. Very little hydrogen, a little bit of water in it, no helium at all to speak of, none of the light stuff of the universe. The sun, the large planets are made of 90% hydrogen, 10% helium, and just a salting of everything else. This rock is the salting. It's the everything else. This is what the Earth is made of. Things like this, things like iron, things like nickel, all of the heavy things of nature, as are all of the other terrestrial planets for that matter. Let's look at the Earth from the point of view of a planet. This could be the Moon. In your mind, take a body about a quarter the size of the Earth. The Earth is 8,000 miles, 13,000 kilometers across. Now take a body about the quarter the size of the Earth, 1/80th the mass of the Earth, and put it 30 Earth diameters away. That's the scale. We've been all the way from the Earth to the Moon. That is as far as humanity has traveled. The other planets are vastly farther, much more dangerous trip. We haven't even been back to the Moon for a very long time, for that matter. We'll go someday again, I'm sure. The Moon is in orbit about the Earth as a result of the gravitational attraction between the 2. Gravity is always mutual. The Moon has gravity, the Earth has gravity, and it is the combination of the 2 that keeps the Moon in orbit about the Earth. It's actually something of a misnomer to
to say that the moon goes around the Earth. In fact, they go around each other. As the moon orbits the Earth also orbits the moon. However, the Earth is 80 times more massive than the moon, so the orbit of the Earth is only 1/80th the size of the orbit of the moon being 380,000 kilometers, 238,000 miles away. The Earth, nevertheless, has this little tiny orbit about the moon, about the so-called center of mass of the planetary, of the Earth-Moon system. Now, the Earth and the moon are extended bodies. They're not points. Think of the point underneath the moon. The gravitational force directly beneath the moon is stronger than the gravitational force on the other side of the Earth. That is, the force of the moon on the Earth. The effect of that is to stretch the Earth out into a slightly oblate shape on a line toward the moon. It's not very much. It's only about a meter or less. Every time the moon goes more or less overhead, however, you raise up a little bit and then go back down a little bit as a result of the stretching of the Earth. This stretching is called a tide. You don't notice it in the solid body of the Earth, but you sure do notice it in the waters of the Earth, because the waters of the Earth tend to flow toward a point beneath the moon and flow in the other direction toward a point opposite the Earth, opposite the moon on the Earth. The Earth rotates beneath this tidal bulge, so if you're at the coast, the water goes up and the water goes back down again. This tidal bulge on the Earth slowly dissipates the energy of rotation of the Earth and actually slows the Earth down. The day is getting longer by about a 10,000th of a second per century. Not very much, not something you'd notice over a lifetime. The only effect you notice is on timekeeping and on clocks. Well, the Earth raises a much more serious tide on the moon, the result of which is that the moon keeps one face pointed toward the Earth at all time. It's a tidal locking. We see similar things in the moons of Jupiter. We see similar things in the moons of Pluto and the moon of Pluto. Pluto and the moon keep one face pointed toward the other at all times. Even stars will do this over a period of time. The tidal force is extremely strong, an extremely powerful thing. We'll meet up with it again in our dealings with the other planets. The moon and the Earth were formed at the same time 4.5 billion years ago. Nobody was there, so how can we tell? Let's go back to this piece of our planet again. Although this is mostly made out of silicon and oxygen and some metal atoms, most rocks have a tiny amount of natural uranium in them. All uranium, U-238, with 238 nuclear particles in it, 92 protons, the rest neutrons, all forms of uranium are radioactive. There's no stable uranium at all. Now, U-238 is not terribly dangerous because it lasts for a very long period of time. You don't want to be around it for too long, but by itself, it's not terribly dangerous. It's the U-235 that's the really bad stuff. U-238 slowly decays away over billions of years into an isotope of lead called lead-206. It's lead with 206 nuclear particles in it. Most lead, however, the kind of lead you get in, say, a fishing sinker, is lead-208. The lead-206 is all coming from the radioactive decay of uranium. So all we need to do in our rock is to look at the ratio of lead-206 to U-238, know the decay rate of U-238. U-238 will cut itself in half every 4.5 billion years. That's called the half-life of uranium. Once we know that from laboratory studies, we can compare the daughter product with the parent product of a radioactive element and get the age of the rock since solidification. The oldest Earth rocks go older than 3 billion years old. The oldest rocks of the moon are close to 4.5 billion years old, and the oldest rocks of all, the meteorites, which are small asteroids that land on the Earth, bring in at about 4.5 billion years. They're the oldest things we know in the solar system. That must therefore be the age of the solar system, the entire solar system, not just of the meteorites, but of the Earth, Moon, and the entire system. We know how old it is from radioactive decay. And we don't have to just use uranium and lead. We can use a variety of parent products with daughter products, and they all come out the same, giving us an age for the planetary system of 4.5 billion years. It's a beautiful body, this Earth. It's covered with water, the oceans, land masses, the continents, covered with clouds, a pretty good atmosphere consisting of nitrogen and the oxygen that we breathe to keep us alive.
It's unique among the terrestrial planets. Of course, you can say that about any of the terrestrial planets. You can say that about any of the planets at all. They're all their own persons, so to speak. But the Earth is unusual in so many different ways. It's the biggest of the terrestrial planets, and it is marvelously active. Why active? It's hot inside, as we know. You go down even into a deep mine, the temperature goes up and up and up. We have evidence for lava coming out from molten rock below, telling how hot it is in the middle. This heat causes a great deal of activity on the Earth. The Earth is kind of an interesting planet. It's kind of bimodal. You have high areas in the continents, and then you have low areas that are filled with water, the ocean basins. So we have sort of high and low. The Moon isn't quite like that. The Moon is more one level. The mountains on the Moon are quite different from the Earth, as we will see. The Earth's land masses, some are flat, but along the edges of many of them, especially along the edge of the United States, South America, you find huge mountain ranges that span and all the way around through Asia, all the way around the Pacific Ocean basin. Where you find mountain ranges, in the centers of some of these continents as well, you also find great activity. The Earth shudders with powerful earthquakes that can bring down buildings. Volcanoes spew hot rock from the interior. All of these active regions tend to be linked together, the mountains and the earthquakes and the volcanoes. They're all together. The Earth is an extremely active body. Contrast with the Moon. Take a look at the Moon through a telescope sometime, as Galileo did back in the early part of the 1600s. And you see a dead surface. You always can see down to the surface of the Moon. No clouds ever block your view. The Moon has effectively no atmosphere at all. It picks up a few atoms from the wind that blows from the sun. A good fraction of the atmosphere of the Moon comes from rocket exhaust, from the takeoffs of the Apollo landings. It effectively has none. There is almost no water in the Moon at all. There's no water in the rocks that were brought back by the astronauts. This rock taken from the Earth, any rock taken from the Earth, has water within it. You can squeeze the water out of it if you squish it hard enough, but not on the Moon. It's an extremely dry body. The Earth, on the other hand, looks pretty wet. Look at all those oceans. It fools you. On the average, the oceans are about 2 miles deep. The Earth is 8,000 miles across. The amount of water on the Earth is remarkably small, and the water holds most of the hydrogen that we have on the Earth. The amount of hydrogen is also very small. The amount of helium we have, which of course is 10% of the sun, is very little as well. Almost all the helium we have on Earth comes from the radioactive decay of uranium, in fact, in the natural rocks of the Earth. Go back to the Moon again and just look at this dead, lifeless body. Fascinating in its beauty, of course, but it's simply a rocky surface that you can see forever. No lakes, no clouds, no air, almost no water. There is a tiny bit of ice, apparently, up at the poles where the deep basins are forever hidden from the sun and the water can't evaporate. But it is an incredibly small amount. Effectively, the Moon is just about as dry a body as you can get. The Earth, on the other hand, has more water than any of the other terrestrial planets, but it's still pretty darn dry. There's very little water on the Earth. Where you want to find water, as we'll see in later lectures, is out in the cold regions of the solar system, out at Jupiter, out at Saturn, and beyond, in the regions of the comets, where the bodies are, at least some cases, 50% water ice, but not in the inner part of the planetary system. The Moon is known not for its mountains, not for its mountains like we have on the Earth, but for its craters, for its basins. The Moon is entirely covered with impact craters. Everything from basins that are thousands of miles wide to little pits in rocks. The entire surface of the Moon is absolutely crushed with impacts. You can divide the Moon up into two very broad areas, the so-called lunar highlands, which are the non-basins, so to speak. They're sort of the average terrain of the Moon, which are completely covered with craters. You have craters piled upon craters, piled upon craters. You can see ghost-like craters that have been smashed up by craters piled upon top of them. From the Earth, you can see spots on the Moon that make the so-called man in the Moon. They're craters too.
They're huge craters. They're enormous impact basins that have been filled with lava big enough to see even with relatively poor eyes. These, when you look at them close enough, also are littered with craters, although not as many. The lava rock is dark. That gives the face to the man in the moon. What makes an impact crater? Rocks, any rock, is not infinitely hard. It may feel like one feel infinitely hard if you get hit by one, but you can compress any rock. They're not perfectly rigid. If you put enough pressure on one, you can deform it. How's a crater produced? Think of a flat plane, pristine plane. From the outside comes another rock, an asteroid, most likely, moving at orbital speed. In the case of the Earth goes around the sun at 17 miles per second. You can go across the United States in just a few minutes at speeds like this. The rock comes down, it can be anything from a small one to something many miles or many kilometers across. The rock comes down and hits the surface of the plane and compresses the surface rock, kind of like putting a bowling ball on a bed. The surface rock compresses downward until the impacting body's energy is used up. Now, much of that energy is going into heat. It's not much different than rubbing your hands together and having friction generate the heat between your hands. In this case, you are stopping a body that is moving at tens of kilometers per second, and that energy gets converted into the compressed rock and into heat as well. That heat begins to melt the rock, and the impact also shatters the compressed rock. Once the impacting body has stopped, you relieve the compression and whoomp, just like the bed spring, it pops back and blows everything out of the basin that's been created by the impacting rock, and you wind up with a hole in the ground. The stuff that gets splashed out goes into what's called an ejecta blanket around the outside, and much of it gets piled up on a crater rim that sort of slumps down, and the slumping helps in a big crater often produce a mountain in the middle. There was an argument that goes back a century or more as to whether the craters on the moon are volcanic or whether they are impact. We now know that they're almost all impact craters. There's very little in the way of volcanism on the moon because the moon is a cold, dead body. You don't have lava flows coming up from the inside. The moon chilled off very quickly after its formation. Now, the exception to that are these large impact basins. We can get the age of the moon from the rocks brought back by the Apollo astronauts. The ages of the lunar highlands go back as far as 4 billion years. The ages of the large spots that make the man in the moon, however, go back only about 3 billion years or so. What apparently happened was that in the early days of the planetary system, the moon was hit by enormous numbers of impacting bodies. It's called the late heavy bombardment, which slacked off about 4 billion years ago, and then the moon was whacked by some enormous bodies that created huge basins, hundreds of kilometers, hundreds of miles across, so big that it cracked the lunar crust and lava flowed up from below to produce lava seas. These large basins are filled, the large lava-filled basins are called maria, like the woman's name, M-A-R-I-A. It means sea in Latin. At one time, we probably thought they were ocean beds. They are not ocean beds. They are beds that are filled with now solidified liquid lava that came up from below. The amount of lava flow is very little. These things are not very deep. The moon never had much in the way of internal heating. It cooled off very quickly, and the amount of lava that's flowed across the surface is much, much less than has flowed across the Earth's surface because the Earth maintains heat in its interior as a result of its large size. Go back now and look at the Earth and contrast the Earth again with the moon. We've got continents on the Earth. We have basins on the Earth as well. These are not impact basins. Do we have impacts on the Earth? We have craters on the moon. Where are the craters on the Earth? The Earth should have picked up as many craters as on the moon. They're here, but it's hard to see because on the Earth we have an atmosphere, we have wind, we have water, and the impact basins simply can't stay. They get eroded away. Not only that, But the active nature of the Earth with the volcanism and, as we'll see, the shifting of the continents simply wipes them out. Nevertheless, there are about 200 recognized impact craters of fairly recent origin on the Earth. The most famous is near Winslow, Arizona. Out in the state of Arizona, there's a crater about almost a mile across that was hit by an impacting body 50,000 years ago or so, in recent enough times that the crater is still there. It's a famous tourist site. The largest crater that we know of is off the coast of the Yucatan Peninsula in Mexico that's about 200 miles or so across. And we think it is the crater of a huge asteroid that hit us that changed the Earth's global climate and probably did in the dinosaurs. So we have them too. They're just not as easy to see. Now I'll go back to the Earth and take a look at perhaps its most distinctive characteristic. If you look at South America and cut it out, imagine cutting it out of a globe, and rotate it a little bit, you find that it will fit right into this curve in Western Africa. This was noticed maybe a century ago or so. And it was suggested way back then that South America and Africa were once part of a giant continent that split in half, and the two have drifted apart. Continental drift. The idea was laughed at for a very long period of time. On the other hand, nobody knew what made mountains. We now know what is going on. In fact, not only does South America fit geographically into Africa, but you find similar rock structures when you fit it. You find similar magnetic field lines frozen into the rocks. There's all the evidence we need that the two continents were really once a part of a single landmass. Running down the middle of the Atlantic Ocean is an enormous mountain range where new crust is being formed. The Earth is hot inside. Take a look at the size of the Earth, 8,000 miles across. We can derive the volume of the Earth in cubic kilometers or cubic centimeters. We can weigh the Earth by dropping a ball, by measuring the acceleration of gravity downward. That is, we can get the mass of the Earth. You divide one number by the other, and you can derive the density of the Earth. The average density of the Earth is about 5.5 times that of water, about 5.5 grams per cubic centimeter. Surface rocks, on the other hand, are only 2.5 to 3 grams per cubic centimeter. They are less dense than the Earth at large. The implication here is that there must be something very dense and very heavy somewhere inside the Earth, most likely down toward the center. The most common heavy material is iron. And we find that, in fact, by the asteroids that hit the Earth, a good fraction of them are, in fact, iron. So from these data, and also from earthquakes, which send waves going through pressure waves, sound waves, shock waves through the Earth, we can actually derive a kind of X-ray picture of the interior of the Earth. And sure enough, down deep inside, about halfway in, is a ball of iron, about 90% iron, roughly, we think, 10% nickel. The outer part of that iron core is liquid. It's the circulation of that iron core that produces the Earth's general magnetic field. Inside that liquid iron core, about halfway into that in radius, it solidifies as a result of the enormous pressures. So it's like a solid iron ball floating inside a liquid iron ball, and the rest of it on the outside is similar in nature to our rock here. Similar in nature to any rock you might pick up outside, made mostly of silicates, silicon, oxygen, with all kinds of admixtures of metal, and also carbon, the heavy stuff. The outer layers are called the mantle. Well, the mantle is hot, is largely as a result of radioactive decay of uranium. Anytime you have a hot substance, it's going to try to rise. Although the mantle of the Earth is made out of rock, it's sort of in a plastic state, and it can undergo a state of convection. That is, the hot rock can slowly move upward, and the cool rock at the top will slowly move downward, and the mantle will begin to circulate around like this. Running down the middle of the Atlantic Ocean is an enormous mountain range. That is where new crust is being formed. Rock from the mantle is coming up and lifting this mountain range. Hot molten rock is coming out from it and creating brand new crust. As the new crust is created in the middle of the Atlantic Ocean, it pushes the continents apart. The Atlantic Ocean is getting bigger,
South America is moving away from Africa. North America is moving away from Europe. At the same time, the Pacific Ocean is getting smaller. This is shoving North America to the west, is shoving South America to the west, and the North American continent is being pushed over the Pacific Ocean basin. The Pacific Ocean basin is diving beneath the North American continent, and this pushes up mountain ranges all along the west coast of the United States, Canada, and the same all the way down through the Andes and all the way down to Antarctica. The Earth is divided up into about between 1 and 2 dozen crustal plates. These plates have nowhere to go. They can shift around, so they're constantly reforming themselves. One dives down beneath the other, creating mountain ranges that melts rock. The rock floats up to the top, produces volcanoes. Where do you find the volcanoes in the United States and Canada and Alaska? All along the west coast, the so-called Ring of Fire that is all the way around the Pacific Ocean basin. As the Pacific Ocean basin and the Pacific plates slide toward Asia, some of the material gets scraped off, producing island arcs like the Aleutians, Japan, and many others that you find around the Pacific Ocean basin. It's a nice theory, but does it actually work? One of the beautiful things about radio telescopes, when you create what is called an interferometer, where you have 2 radio telescopes acting as one, is that you can get the exact distance between the 2 radio telescopes. We set a radio telescope up in, say, Europe. We put another one in North America. Look at a very distant celestial radio source that radiates as just a little point. We don't care what it is. Observe with the 2 telescopes simultaneously. Synchronize them with atomic clocks, and you can measure the distance between the telescopes to within a couple of inches, within a few centimeters. Observe over a period of time, and we watch the 2 telescopes getting farther apart at about the rate at which the human's fingernails grow. That is, we can actually see North America moving away from Europe. We can actually see South America moving away from Africa. 250 million years ago, they were all together. They split apart as a result of convection in the Earth's mantle, and now they're being driven apart, and eventually North America will probably ram into Asia. Now, the Pacific Ocean plate is moving northward and rotating around. The Pacific Ocean plate joins the North America plate at a famous line called the San Andreas Fault. The Pacific Ocean plate is moving northward, but it's not smooth. There's no real lubrication. So think of putting your hands together and hard as you can, and then pushing one hand in one direction and the other one in the other direction, and suddenly they slip by many meters, all at the same time. Well, your hands by an inch or so. But think of rocks doing this. They will slip by many meters, suddenly, jarringly, and will send out tremendous shock waves. The San Andreas Fault comes up the Gulf of Mexico. It goes through Southern California and exits through the Bay Area and San Francisco, and it brings down buildings maybe once a century or so when it finally rips. These fault lines are all over the world, and they're the source of the earthquakes, and it's the slippage of these crustal plates that do the job. On occasion, you'll also get a plume coming up, hot rock from the mantle, creating things like the island of Hawaii. The biggest mountain on Earth is the big island of Hawaii. Kind of surprising. Most people think of it as Mount Everest. Mount Everest is the highest above sea level, but from base to top as a single mountain, Hawaii is the biggest, almost 7 miles from the bottom to the top. It's a result of a mantle plume that's coming up from below. It's a very special kind of volcano called a shield volcano because it looks like an old-fashioned Roman shield sort of placed upon the ground. Low slopes, kind of runny lava. All of the Hawaiian Islands are shield volcanoes. And the hot spot, the plume, is located at one point in the Pacific Ocean. The Pacific Ocean basin is moving to the north and carrying each island off the hot spot, at which point it begins to wear down. The northern Hawaiian Islands are small. They're worn down by erosion until they finally just disappear into subsea mountains. The real activity is now taking place in the southern coast of Hawaii, in Kilauea, and a new volcano that's coming that is now undersea, where some millions of years from now, we'll have a brand new resort south of Hawaii. You can actually see the scar, the track left by the shifting crustal plate. The Earth is the only body that has these crustal plates. Venus, for some reason, chilled off. The Moon doesn't have any at all. Mercury doesn't have any. Looks like Venus and maybe Mars tried to get them, but they don't have them. Only the Earth, the largest of the terrestrial planets, with enough heat inside to produce this kind of tectonic plate motion, as it's called, that simply carries the continents around the world. We can find many other pieces of evidence of this. India, for example, millions of years ago, crashed into Asia. As it did, it buckled up the land and created the Himalaya mountains that are still growing. India is still moving this way, and the ripple is extending farther and farther into China. You have to have processes like this to keep mountains, because the mountains would simply wear down under erosion unless there was something to keep building them up. And it's the plate motion that does it. The moon doesn't have it. It's one single crustal plate. It's a small body, roughly 1/80th the mass of the Earth, and it chilled off eons ago. It's completely dead. No longer any volcanic activity on the moon. Once in a while, somebody will see a little degassing, little outgassing in a crater, but that's about all. Pathetically small amount of activity. It's the deadest, really, of all of the inner planets. Moon has no atmosphere. The Earth does. It's terribly thin. You really can't survive more than about 3 miles, 5 kilometers or so above the surface of the Earth. Beyond that, the air is simply too thin to breathe. It's remarkable how fragile and how thin this terrestrial atmosphere actually is, consisting of roughly 4/5 nitrogen, roughly 1/5 oxygen in the molecular form, not the atomic form, that's poisonous. Nitrogen and oxygen, about 1% argon, a tiny fraction of a percent of water vapor, which is pretty variable, as we all know, and a tiny fraction of a percent of carbon dioxide and many other gases, methane, sulfuric acid, all kinds of little stuff that float around in the Earth's air, much of it from the degassing of volcanoes, the oxygen coming from life processes on the Earth. The Earth is the only one of the terrestrial planets that has an oxygenated atmosphere as a result of all of the life processes that have taken place on our beautiful planet. You can go to the top of Everest, but you can't stay there. The air is simply too thin. There are two particular molecules in the Earth's atmosphere of trace molecules that are of particular importance. Carbon dioxide, which is at a very low level, and water vapor as well, are fierce infrared absorbers. The sun is at about 6,000 degrees above absolute zero, about 6,000 degrees Kelvin, and it produces dominantly yellow light. Sunlight heats the body of the Earth, but it only heats the Earth a little bit above the freezing point of water. Let's say round it off to about 300 degrees above absolute zero. At 300 degrees, a body can't produce optical light. That's why it gets dark at night. The sun goes down and you don't see the land glow. It is glowing in the infrared where you can't see it. So the Earth re-radiates its heat as infrared energy. However, water vapor and carbon dioxide fiercely absorb the infrared energy and act as a blanket around the Earth that help keep the Earth warm. Without that little bit of carbon dioxide, the oceans would probably freeze. It's called the greenhouse effect. And of course, now we get into all kinds of debates as to what the effect is when we start dumping carbon dioxide into the Earth's atmosphere by burning the carbon in the rocks. That is, by burning oil deposits, coal deposits, and the like. And nobody is entirely sure what is going to happen. We are going through a period of global warming. Is it a result of carbon dioxide in the air, an enhanced greenhouse effect? Wait till we get to Venus and you can see the effect if the greenhouse effect really starts running away with itself. The other molecule of particular interest is ozone. It's the O3 molecule. What you are breathing in the air is the O2 molecule. O3, or ozone, is produced in electrical discharges. If you have a little train set at home, for example, you can smell it when the engine's running. It's kind of an acrid odor coming out of the motor. Ozone is naturally produced in the upper layers of the Earth's atmosphere, and it fiercely absorbs ultraviolet radiation. It is what keeps us from frying on the ground from the ultraviolet radiation that is produced by the sun. Again, it's a fragile molecule. It is broken down by air pollution. We have done wonders with trying to control this over the last decade or so, and have probably done it. Nevertheless, there is a hole in the ozone above South America that can extend all the way to Australia, which is causing some of the Australians, the beach-loving people, a bit of a problem, because as the ultraviolet radiation gets through the Earth's atmosphere, it causes an increased amount of skin cancer in human beings. So, as thick as the air appears to be,
It's a rather fragile layer surrounding the Earth. Much larger is the Earth's magnetic field. The magnetic field is generated by circulation in the iron core. And the school book picture has it as sort of a nice looping affairs coming out of the North Magnetic Pole, which is not at the North Geographic Pole. If you use a magnetic compass, you will not get to the North Pole. You'll get to an island in the northern archipelago of Canada, in fact. So you have to be a little bit careful on how to use these things. The magnetic field of the Earth is not really structured that way. There is a wind coming in from the sun that hits the magnetic field on the sunward side of the Earth and hammers it inward, compresses it, and strings the other side out into a long magnetic tail that actually stretches farther than the moon is from the Earth. The magnetic field of the Earth captures these particles, these high-speed particles from the sun, and protects us. There are two layers away from the Earth, one about 1.5 Earth radii and the other about 4 Earth radii out, called the radiation belts, the so-called Van Allen radiation belts, that are filled with these particles bouncing back and forth like dancers between the North and South magnetic poles that keep these particles from hitting the Earth. Every once in a while, when a magnetic field collapses on the sun, a big bubble of solar wind, particles from the sun come screaming down the solar wind, hits the Earth's magnetic field, overloads it, disturbs it, dumps particles in close to the North Magnetic Pole, expands these particles down toward lower latitudes, and we see a northern lights display showing that there is an intimate relationship, not just of radiation between the Earth and the sun, but of matter as well. The sun literally reaching out to touch the Earth. Without the magnetic field, we'd be in a lot of trouble because that solar wind could seriously influence the Earth's atmosphere. One of the dangers of living on the moon is, in fact, the solar wind. You're right out there exposed directly to it. In a spacesuit, you're okay for the moment, but a lunar colony would probably want to dig itself into the rock to protect oneself from the solar wind. The Earth protects us from all manner of things out there as a result not only of the atmosphere, but as a result of this marvelous magnetic field that shrouds the Earth and keeps the solar wind from hitting us. It's a remarkable body. What we know about the Earth, which we can examine directly, tells us a lot about how the other planets are structured. On the other hand, the other planets are natural experiments. From the way they are constructed, under different conditions, different separations from the sun, different masses, different radii, we can learn more about the Earth, which shows one of the great real uses of astronomy. Learning about the other planets tells us something about our own planet and how to protect it and how generations of us can keep living on it safely for hundreds, thousands, hundreds of thousands, maybe millions of years to come.
After listening to Lecture 9, a student posed this question to Professor Kaler. Why does the Earth have a magnetic field while the Moon does not? Let's listen to the professor's response.
The Earth has a magnetic field because of circulation of the iron core. Iron is an electrically conducting medium. If you move an electrically conducting medium, you will create a magnetic field. The iron core of the Earth, the outer part of the iron core of the Earth, the liquid iron core, is in a state of convection. It's circulating around like this. It's also the Earth in a state of rotation, and that sloshes the iron core around, and that generates the Earth's magnetic field. The Moon, on the other hand, is so small that it seems to be solidified throughout. We're not even entirely sure that the Moon actually has an iron core. If it does, it's very, very small. Even if it does, there's no circulation of the iron core, and the Moon is a magnetically inactive body. The Moon has no magnetic field.
This ends Lecture 9. Astronomy, Earth, Sky, and the Planets. Lecture 10. Iron Planets, Mercury, Venus, and Mars.
In this and other lectures from now on, we'll use the more scientific definition of temperature, which is absolute temperature scale, the so-called Kelvin temperature scale, in which we start at absolute zero, where we've taken all the heat out of a body, minus 273 degrees centigrade, minus 459 degrees Fahrenheit, and then count upward in centigrade or Celsius degrees so we can get rid of the negatives, unless, of course, specified otherwise so that we can get a more familiar be more familiar with what the terms actually mean. Generally, 0 will mean absolute 0. Unless otherwise specified, when I say 100 degrees, I mean 100 degrees above absolute 0, which is still pretty cold. In the last lecture, we looked at two prime examples of terrestrial planets. The biggest of them, the Earth, and if you like to count the Moon as a planet, the smallest one, of course, the Moon. The other three are all in between. And in this lecture, we're going to take a look at the variety of terrestrial planets from Mercury, the planet Venus, the planet Mars, what it might be like to be on one of them, what they look like, what's on their inside, and what they have to tell us about the Earth, because their story is pretty important. First, let's look at the similarities among them. They're all structured like the Earth. They all have iron cores, they all have rocky mantles, and they all have some kind of a crust on the outside. They run through a range of sizes. Mercury is the smallest, Mars is the next one up, Venus is the next one, and on top of the whole pile is the Earth. By looking at the smaller ones and how they're structured, how they're made, it'll tell us someday, even if not now, it'll tell us something about our own planet. Well, let's begin outward from the Sun and look at them in order, starting with Mercury. If you look at a picture of Mercury taken with spacecraft, you can't do it from the Earth. Mercury's very close to the Sun, at most 28 degrees from the Sun, and our picture from the Earth is just terrible. We can't even get a decent rotation period out of Mercury viewing from the Earth. It's a very difficult planet to study. Almost everything we know about it has come from a spacecraft flyby in the 1960s, which imaged the planet close up. And what did we see? Craters, 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 every place. It looks very much like the Moon. Obviously, it went through the stages of this late heavy bombardment that produced the same kind of impacts that we find on the Moon. And being the smallest planet, and being so close to the Sun, it has no particular atmosphere, and therefore no erosion, and we still have the remnants of the late heavy bombardment. It's a small body. It's about 38% or so the radius of the Earth, about 5% the mass of the Earth. What makes Mercury unique, however, is its enormous iron core. The planet is the densest of them all. It might be the smallest of the terrestrials, but it's denser than any of them, all the way out to Pluto. This implies that it has a huge iron core. Mercury could almost be considered an iron ball with dirt piled on top. The iron ball is really extraordinarily large. We're not entirely sure what happened and how this huge iron core was created. It probably has something to do with proximity to the Sun, something we'll address in the last lecture of this course when we look at the formation of the planets. A look at the surface, however, shows real differences with the lunar craters. The craters are flatter as a result of a lower gravity. There are, in a sense, fewer of them. The craters seem to be separated by some kind of intercrater plain, which implies some kind of lava flow that may have wiped out earlier generations of craters. There is an enormous impact basin. One thing that we will continuously see through this entire study of the planets is the awesome violence of the early solar system. We find collisions of gigantic proportions. The first ones we encountered were the Maria basins of the Moon, the huge basins that are filled with the Maria. They're filled with these lava flows. We find similar features on Mercury. A huge basin was created so violently that the shock waves went through and around the planet and jumbled mountain ranges on the other side. Neither Mercury nor the Moon has real mountains like the Earth. The Earth has these tectonic mountains that are raised up by continental drift. The mountains on the Moon are raised mountains from impact craters. That is, they're simply the rims of giant impact craters. In the Maria, we find the same kind of thing on Mercury. There are no tectonic types of mountains because there are no continents and there's no continental drift. Mercury does have a tiny, tiny magnetic field, however, and it does imply that the core is a little bit liquid, even in spite of the small size of the body. We're not entirely sure why it should be, but it is. It has very little atmosphere. Most of the atmosphere that Mercury has comes from atoms from the Sun that impact on rocks and kick atoms off of the surface rocks. But it's nothing that you could possibly breathe. The atmosphere is effectively zero or very close to it, very much like the Moon. It's basically a pretty dead body, and one that is not a nice place to visit. The surface rocks hit temperatures of somewhere around 500 plus degrees Kelvin. The surface rocks under the sun are pretty close to the temperature of a self-cleaning oven. If you put lead solder on the surface of Mercury, it would start to melt. It's that hot. What is also unusual about the planet is its rather odd rotation. This is a very difficult thing to view from the Earth. However, these terrestrial planets, particularly Mercury and Venus, are amenable to being hit by radar. That is, we use an active radio telescope by sending out radio waves from the Earth, bouncing the radio waves off the planets, and detecting the return signals, much like an aircraft radar system would work. We can not only measure the precise distance of the planet by how long it takes the radar beam to go out and hit the planet and come back, knowing the speed of light. We can also determine the velocity through something called the Doppler shift. Think of a light wave. Think of a wave moving in water, if you like. Run a boat through the wave. If you run a boat into the waves in the direction in which they're going, the frequency of the waves hitting you will appear to be higher. In other words, you will measure a smaller wavelength. If you go along with the wave, you'll measure a longer wavelength. This is called the Doppler effect. It's most noticeable in sound. If a car or an ambulance approaches you on the street, the pitch will be higher as it approaches you. It will be lower as it goes away from you. Light, radio, all electromagnetic radiation does exactly the same thing, which allows us to determine velocities of bodies in space without actually going out and being there. We can just, same way in which a police radar gun works. We can measure not only the speed of the planet of approach or recession and its distance, but we can hit different parts of the planet and measure the spin rate. And it turns out that Mercury has a very odd rotation. It takes 88 days to orbit the Sun, and its rotation period is exactly 2/3 of its orbital period, 59 days. Mercury is locked in synchronous rotation with the Sun, not unlike the way the Moon is locked in synchronous rotation with the Earth. The Moon keeps one face pointed toward the Earth because the orbit is relatively circular, but Mercury also has a relatively elliptical orbit. The result of that is that you get an exact 2/3 locking. That is, the rotation period of Mercury relative to the stars is exactly 2/3 of its orbital period, as a result, of course, of its proximity to the Sun. If you were on Mercury, the Sun would rise actually every 176 days, rise and set every 176 days. On the forward side of the planet, it would be blistering hot, whereas on the rearward side of the planet, on the nighttime side, away from the Sun, the temperature plummets to the order of 100 degrees above absolute zero or so. It would be a very unpleasant place to visit. It is a dry planet, except, again, there's good evidence for ice at the poles, even as close as the Sun, because there are basins up at the poles that never see sunlight. Consequently, if you have a little bit of ice, it'll last forever. It's not a polar cap like we have on Earth. It's probably ice mixed in rather loosely with the rubble caused by eons, billions of years of impacts. You move away from Mercury from 4/10 of an astronomical unit to 7/10, and you encounter a very, very different kind of body, Venus. It's often called the twin of the Earth because it's very much the same size as the Earth. It's 95% the radius of the Earth, about 80% the mass. If you were walking on Venus, your gravity would feel very similar to what you have here, whereas on the Moon, it's only 1/6 of what it is here. You'd be very light and you'd rather float around. On Mercury, a little bit heavier, but on Venus, you'd feel very much at home, except for the weather, which is something we'll talk about in a little while. We don't have a good view of Venus either. We can get a nice nighttime shot. We can see it from the Earth, but there's no features to see from the Earth to speak of. A few dusky markings here and there, and it's been known for generations that Venus is covered by clouds. You cannot see the surface at all. Sure, the Earth is covered by clouds, but there's lots of breaks in the clouds through which astronomers can look to see outer space. We can, for Mars, for example, we could examine the Earth. From Venus, we could examine the Earth, see the continents, see all the features over a period of time, but not Venus. It is perpetually cloud covered. You can never see the surface. So how do we know anything about it at all? First of all, we can hit Venus by radar from the Earth and get the rotation period. What a surprise. The rotation period of the atmosphere is quite different from the rotation period of the solid body of the planet. Venus is one of the 3 bodies in the planetary system that rotates in the wrong direction. It takes 243 days relative to the stars to make a full spin, and the axis is perpendicular, almost exactly perpendicular to the orbit, except that it spins in the wrong direction. Nobody knew why this was so for most of our study of the planet. The current theory, which could easily be knocked down, we don't really entirely know, is that the atmosphere, which is very thick around Venus, became tidally locked to the sun and then locked itself onto the planet. And as a result of this thick atmosphere surrounding Venus, which holds the clouds, that slowed the planet down and made it slowly spin in the wrong direction. It's the air that is so fascinating about this planet. One of the many things, in fact, that's so fascinating about this planet. The clouds completely cover it. When you observe natural radio radiation from the planet and infrared radiation, not from radar, but just the natural stuff that's coming off, we can determine the temperature of the surface. The temperature is close to 750 degrees centigrade, close to 900 degrees Fahrenheit. In spite of the fact that the planet is almost twice as far away from the sun as Mercury, it is just as hot. It's a result of the atmosphere. We can detect absorptions of carbon dioxide molecules from sunlight hitting the planet and scattering back to Earth. The only way that that planet can be so hot is that the atmosphere must be extremely thick. Direct sampling, in fact, has shown that at the surface, the atmospheric pressure is almost 100 times that of the Earth's atmospheric pressure. You'd simply be crushed trying to walk on the surface. And it is 96% carbon dioxide. On the Earth, carbon dioxide is a tiny fraction of 1% composition of the atmosphere. Even that is enough to significantly raise the temperature of the Earth's surface by absorption of the natural infrared radiation. There is so much carbon dioxide in the atmosphere of Venus that it has produced a runaway greenhouse effect that has made the temperature zoom up to that, again, of roughly a self-cleaning oven. And it doesn't matter whether you're on the daylight side or the nighttime side. The atmospheric blanket is so thick that Venus never cools off at night. So imagine being on the surface of this roasting place where the temperature is so high that the couple of spacecraft that were sent by the old Soviet Union to land on the surface didn't last much more than about half an hour after they got some fascinating pictures of the rock structures, which just look like volcanic plains going off to the horizon with very little in the way of other features. The clouds, by spectroscopic analysis from the Earth and by direct sampling as well, turn out to be not water. This beautiful planet is covered with sulfuric acid clouds. Compared to Earth, the clouds don't necessarily have to be of the same composition of the atmosphere. On the Earth, you have water clouds floating in basically a nitrogen atmosphere. On Venus, you've got sulfuric acid clouds floating in a carbon dioxide atmosphere. You want to approximate, it actually rains sulfuric acid in the clouds. Of course, it gets too hot. It never really hits the bottom. But you can sort of imagine replicating Venus by climbing into a self-cleaning oven. And don't do this at home. This is all sort of a thought experiment. Climbing into a self-cleaning oven, having somebody turn on and spraying yourself with oven cleaner. A really nice place. So much for the goddess of love and beauty. Thank you very much. Beautiful from Earth, not there. On the surface, of course, you're looking at a cloud deck very, very high in the sky. You would never see the stars. The sun would rise, if you could see it, would rise in the west and set in the east. Everything's backwards. By the time you get to the surface, the winds are blowing gently, only at a few miles per hour, very little erosion, very little soil to drift around, and it's relatively peaceful and quiet, except that imagine a weather report on Venus. Unlike what you have on Earth, it would be, well, today is going to be hot, slow winds. Tomorrow, hot, slow winds. Day after tomorrow, hot, slow winds. No storm team there, thank you very much. A very quiet place if you can take the heat and you can take the pressure. How do we examine the surface? Again, radar. The U.S. flew a mission to Venus to put a satellite in orbit about the planet, not just a simple flyby. This spacecraft, called Magellan, carried a side-looking radar that could beam radar waves or radio waves down toward the planet and see the reflection. It mapped almost all of the planetary surface via radar, producing pictures made from radio waves that looked just like optical pictures, just as if you were flying above the planet's surface, taking pictures from your very hot airplane, hopefully an air-conditioned airplane. And what do we see? Everywhere we look, volcanoes. Over 1,000 shield volcanoes on the planet's surface. Shield volcanoes being similar to the Hawaiian volcanoes. Some big, some small. Volcanic structures that are unlike anything we've ever seen on Earth. It is a wildly volcanic planet. It's not known whether it's still volcanically active. There's some evidence that maybe some of the volcanoes are still going off. But it's mostly chemical evidence. There's no direct, visible plumes coming out of anything. The Venusian surface is all volcanic. The whole thing is volcanic. Radar beams do show what appear to be sort of continent-like structures, but there's no plate motion that we can see. Maybe it tried to have a little plate motion, but these continent-like structures are volcanic bulges that have simply lifted the surface up and kind of cracked the surface, produced faults, produced canyons that are kind of like what we see on the Earth, but really in structure very different from what we have here. There are no continents really to speak of. There's only one really large mountain range, and that's in a sort of one of these volcanic bulges up toward the North Pole, but we don't see any mountains as we see them on Earth. A very different kind of structure, which is kind of odd, isn't it, for a body that is very much in size and mass like the Earth. It's called a sister planet sometimes, but it's only externally a sister planet. Physically, it is a terribly different kind of body. We also observe impact craters, surprisingly enough. The impact craters on the Earth have been wiped away by continental drift. They've been wiped away by erosion, fierce winds, and water, but there's no water on Venus. It doesn't rain water on the surface, and as a result, the amount of erosion is really very small. So we keep track of the impact craters. We find about 1,000 impact craters all the way around the planetary surface, rather uniformly distributed. And from the number of impact craters compared to the number on the Moon, whose absolute age we know as a result of the Apollo spacecraft landings. This gives us a chance to measure the impact rate per million years, let's say, or per billion years. From the number of craters on Venus, we can tell the age of the Venusian surface, and it's roughly between 500 million and 1 billion years old. That is the entire planetary surface. This is very unlike the Earth. The ocean basins are brand new crust, basically zero age near the mid-Atlantic ridges, for example, and where the new crust is coming out, whereas the most ancient of rocks on the Earth go back well before 3 billion years, not on Venus. On Venus, the whole planetary surface is about 500 million to 1 billion years old, and it seems that at that time, 500 million to 1 billion years, the whole planet underwent sort of a global overturning of volcanic action that erased away all the features that were there before, leaving a clean slate upon which to produce yet more impact craters. So we have no record of what happened beyond roughly 1 billion years ago, before 1 billion years ago. Now, how could something like that have happened? Well, we think it's because Venus is a little bit closer to the sun than we are. As a result, you can't get liquid water on the surface. It would boil away. If Venus ever had oceans, it would have cooked away. As a result, the water goes into the atmosphere. Water is a greenhouse gas, which makes the surface hotter. Now, when you don't have water, you also can't plant carbon atoms into the rocks, into the soil. Venus and the Earth have the same amount of carbon. On the Earth, it's in the rocks. It's in carbonate rocks. It's in coal. It's in oil. Very little of it is in the atmosphere. On Venus, it's in the air. Consequently, Venus developed this carbon dioxide atmosphere. The water floats up. It gets broken down by sunlight. The hydrogen from the water escapes into space. The oxygen atoms can combine with the carbon to produce the carbon dioxide. And can combine with it. In addition, the sulfur gets baked out of the rocks. The sulfur can combine with the hydrogen and the oxygen, can produce the sulfuric acid. And you have this runaway greenhouse effect where you can't get the carbon in the rocks anymore. Carbon dioxide is a tremendous greenhouse gas and the temperature just goes shooting up. So it's like you took the Earth and cooked all the water, all the carbon out of the Earth, you would have another Venus. You don't have that on the Earth because the Earth is a little too far away for that to have happened. You can keep liquid water on the Earth and have a stable atmosphere without the greenhouse effect running away with itself. Push it 7/10 of an AU in, and the planet just ran away. That softens the rocks. If the rocks are a little bit soft, you can have a greater overturn of volcanic action. That is, the volcanism is enhanced as well. If you enhance the volcanism, there's a good chance that the heat from the interior of the planet can escape. Venus has no magnetic field. That sort of implies that the core is frozen. Well, it kind of makes sense. If you have all this volcanic activity going on, you could have released much of the heat from the interior and possibly have frozen the core. So you wind up with a terribly different planet. Just shove the Earth in by 0.3 of an AU, you'll probably get another Venus and a very different kind of body. Well, the Earth we've looked at already, this big terrestrial planet, very stable, water on the surface, not a lot of water compared with the mass of the planet, a lot of water compared with a human being, far more than we're ever going to need, of course, oceans being a couple of miles deep. No water on Venus, tiny, tiny bit in the atmosphere, tiny, tiny bit of ice on Mercury. And you go out to Mars. Now you have a somewhat smaller planet again. It's about 10% or so the rate. It's about half the radius of the Earth, about 10% the mass of the Earth. So it's not all that much bigger than the planet Mercury. You see, having kind of an envelope distribution. You start with Mercury small, Venus bigger, Earth bigger yet, and then you squeeze down to Mars. And as we'll see in a lecture down the line, then you go out to the asteroids, which you could assemble presumably into a planet, which would be then smaller than Mars. So you have a complete envelope pointing toward Jupiter, for good reasons, which we'll talk about in the last lecture. Mars has a marvelous history to it. It is, in many ways, much more Earth-like than bigger Venus. We can see the surface. We see a few clouds in the atmosphere, dust storms that occasionally obliterate the surface, but you can see down to the surface from the Earth. And what do you see? Polar caps that look very much like the Earth. Tilt of the axis, about 24 degrees. The obliquity of the ecliptic is very similar to that of the Earth. A rotation period, a little over 24 hours. If you lived on Mars, the sun would rise and set. You'd have days very much like the Earth. It'd be a little colder. You're half again as far from the sun. Surface rocks can, at the equator, roughly hit the freezing point of water. And, of course, everywhere else it's much colder than that. But still a very Earth-like kind of environment. The tilt of the axis means Mars will have seasons very much like the Earth. And as winter comes on in the northern hemisphere, so for example, we see a polar cap extend, a temporary polar cap extend down toward roughly half the equator. You see the same thing on Earth. The permanent polar cap on Earth is ice. It's always there. And as winter comes on, snow grows a polar cap down to about the mid-40 latitudes or so. And the same thing happens in the southern hemisphere winter. The same thing happens on Mars. The difference involves the Martian atmosphere. There's no oxygen in the Martian atmosphere. It is very much like the Venusian atmosphere. It's carbon dioxide. It is, however, only 1%, roughly, the pressure of the Earth's atmosphere. So you're going from a factor of 100 times greater than Earth on Venus to 1/100th of Earth at Mars. Quite a range. The rest of it is nitrogen. It's mostly carbon dioxide. And at those temperatures, the carbon dioxide freezes out and forms a dry ice snow, frozen carbon dioxide. The same stuff that's used to fog theater sets. Part of the polar cap is, however, water. There really is frozen water on Mars. No question at all. Now, the Martian history is a checkered one. Back in the 19th century, an Italian astronomer looked at Mars and thought he saw fine lines on the planet's surface that he called canali, meaning basically fine lines on the planet's surface. This was picked up in English as canals. Canals are built by people. There must be Martians. Why the Martians build canals? Well, it's pretty dry there in spite of the little bit of water there is. Most of it is at the poles. Clearly, they are using the Martian water at the poles, and they bring the water down to canals to irrigate their corn and soybeans down in the oases near the equator. This was picked up by the newspapers, mostly in the United States, that gave glowing pictures of what the Martians must look like. Various astronomers described the canals, drew great maps of the canals and the oases and the dark areas that come and go with the seasons. And it's all an illusion. When the Mariner spacecraft passed by Mars, what did it see? It went over the South Pole, not the South Pole, went over under the southern hemisphere of Mars. Craters, craters, craters everywhere. What a boring sight for the public. Public immediately lost it. No canals, craters, looks like the moon, looks like Mercury. Let's forget Mars. Another spacecraft went past the northern hemisphere of Mars during the time of a dust storm. Couldn't see anything. Public lost even more interest. But then the dust settled. The global dust storms can be pretty fierce. The winds, which are normally gentle, can kick up into the hundreds of miles per hour and have a global dust storm, like a sandstorm in the Sahara, except that it fills the whole planet, keeping you from seeing the surface. And as the dust settled down, this immense volcano appeared, popping up through the dust. And then another one, and a huge bulge with 3 volcanoes, 2.5 times the height of Everest. Huge things. The biggest volcano on Mars is so large, if you took it off Mars, it would cover the state of New Mexico. You could put the entire Hawaiian Island chain in the depression, the caldera at the top that collapsed in to fill a lava basin down below. The whole northern hemisphere appears to be wonderfully volcanic, whereas the southern hemisphere is cratered. Nobody knows why this difference exists. One thing we did learn, though, there are no canals, and there are, unfortunately, no Martians. We do, however, see river valleys. If you look in the southern hemisphere, you see tributary valleys, much like you would see flying over the western part of the United States. They're dry now, but it looks for all the world like water once flowed on the planet. If you look in the northern hemisphere, you see tremendous outwash valleys, huge channels in which water catastrophically flowed that reminds you an awful lot of the western United States, where there was once a huge lake in Montana dammed by a glacier. And within a couple of days, a lake the size of Lake Erie flowed all the way to the Pacific Ocean, scouring the land. It looks just like what we see on Mars. Now, the air pressure on Mars now is not great enough to allow liquid water. As anybody knows who's tried to cook in, say, Denver, it requires longer to cook an egg up there because the air pressure is lower and the boiling point of water is lower. When you drop the air pressure, the boiling point goes down, and eventually, if you get it down far enough, the boiling point hits the freezing point, and you can no longer have liquid water. That's why you can't have liquid carbon dioxide on the Earth. It goes from the solid state right into the gaseous state. The same would be true on Mars. You cannot keep liquid water, but those channels show that water once flowed in the liquid state, and there are many, many other pieces of evidence. Flow channels off crater rims, softened craters that look like they're almost produced by an impact in what amounts to mud. We think that there's a lot of water underneath the surface soil, which is itself very, very dry. We don't see water lying on the surface. You can't have liquid water, but it once flowed. And if it once flowed, this implies that Mars once did, in fact, have a thick atmosphere. And it lost it. As cold as it is, turning into this runaway refrigerator, it lost its atmosphere. Because it's simply not massive enough to hold it. And even if we were to, quote, terraform Mars, if we could go there to produce a thick atmosphere and make it a real Earth-like planet, it would lose it again. There's no way Mars can keep an atmosphere. Its gravity simply isn't strong enough. But there was once water there. And some scientists think that the water in these outflow channels formed an actual ocean in the northern hemisphere. There's evidence of glaciation here and there. It's all gone now. Mars cannot keep an atmosphere. Its heat dissipated a long time ago. It's a one-plate planet. There's no continental drift. There's an enormous channel called sometimes the Grand Canyon of Mars, but it wasn't carved by water. It's actually technically called Valles Marineris, the Mariner Valley after the spacecraft, probably caused by the rising of the bulge on which we find these volcanoes, and it put a crack in the crust that would stretch literally from New York to Los Angeles, an enormous fault canyon. We find all of this geologic activity, probably ancient, probably goes back a few billion years. It's unlikely to have much of it anymore. But Mars was once apparently quite Earth-like. Now, there's good evidence for life on Earth shortly after the planet solidified, shortly after it was born. The oldest fossils go back 3 billion years or more, although it's somewhat arguable. It goes back a long, long ways. If this happened on the Earth, did it happen on an Earth like Mars? Is there life on Mars? Was there life on Mars? There are no Martians. We've landed spacecraft on the planet. We've looked around. There's no critters running around. We have done chemical experiments on the soil. There's no significant evidence for biologic activity, even current or past biologic activity, although it cannot entirely be ruled out. We have no evidence for it. The best evidence we have, which is highly controversial, for life on Mars are Mars rocks. Mars rocks, nobody's ever gone to Mars. How do you get a Mars rock? You have a giant impact on the planet. Some of those rocks are kicked to such high velocities that they're blown off the planet altogether. They go into orbit about the sun. A few million years later, the Earth sweeps them up. They land on the terrestrial surface as meteorites. We have rocks from the moon for much the same reason, lunar meteorites. We have a dozen or so rocks from Mars. Can we prove it? Sure. We look at isotope ratios of the chemical elements in the rocks. They're similar to what the robotic spacecraft have found on Mars. We look at trapped gases. The trapped gases in these meteorites have the composition of the Martian atmosphere. There's no question at all. One of them, which was found in Antarctica, was sliced open, and there were some scientists who thought, gee, these little tiny things look like they might be microfossils of some sort. The argument has raged now for years. It may rage for years into the future. The only way we will really know whether there's life on Mars is someday either to go there in person or send very sophisticated robotic craft to drill deep into the soil, see where the water is, look in the basement rocks, really look down, bring samples back to us for real analysis, pristine samples, dated where we know where we're taking them from. Either way, we sort of win, you know. If there's life on Mars, if there was ever life on Mars, it will tell us something about, eventually, about how life forms on planets. If there isn't life on Mars, or never was life on Mars, we wonder why not. And we probably treasure ourselves all the more. So as far as we know, we're the only planet that has it anywhere in the universe. To conclude it all, look at them all again, together as a unit. Little Mercury, big iron ball in the middle, dirt on the outside. Venus, kind of like the Earth, iron core similar to that of the Earth, but a runaway oven, a hot body that was in which the greenhouse effect simply ran away with itself. The Earth, with its liquid water and its wonderful atmosphere, its breathable atmosphere, and then a little bit out to Mars, a runaway refrigerator. And we see here a marvelous thing called the Goldilocks effect. Venus is too hot. Mars is too cold, too far away. And here we are, the Earth, right in the middle. We're in a little strip around the sun where we can have liquid water, which seems, so far as we know, to be what is truly necessary for life. We can then ask the question, do other stars have planets like our own? There are other stars, which we can tell from this Doppler shift, that do have Jupiter-like planets. 100 of them or so have been found. Do they have Earths? Maybe, maybe not. We haven't found any yet. Do they have Earths in a water-type zone? That is, Earths in a zone in which you can have liquid water? We don't know. We don't know whether there's life anywhere else. The only place we have found it is in the third planet out from the sun, our beautiful, precious Earth.
After listening to Lecture 10, a student posed this question to Professor Kaler. Do we have any evidence of past life on Mars? Let's listen to the professor's response.
We have no evidence at all for past life on Mars. The so-called microfossils found in the Martian meteorite could, so far as many scientists are concerned, have been produced by simple geologic activity. If there had been life on Mars, we have no idea what form it might have taken. It might have been something completely alien from what we find here. We don't know. This is the fascination of looking for life on another planet.
This ends Lecture 10. Remember to visit this course's webpage at www.modernscholar.com, where you'll find additional information about the lectures that you just heard. Astronomy, Earth, Sky, and the Planets. Lecture 11. Monsters of the Midway, Jupiter and Saturn.
The last lecture we looked at the terrestrial planets, these balls of rock and iron, planets made of dense, heavy stuff. Now we take the giant jump out to the monsters of the Midway, to Jupiter, to Saturn, to the big guys of the planetary system, huge planets that dominate everything. Jupiter having more mass in it than all the other planets rolled together. We'll take a look at the external characteristics of these two planets, compare them. We'll look at the internal characteristics, see what they're like when we dive down deep inside, then take a look at their enormous number of moons, and finally at their rings, especially Saturn's magnificent ring, the one that's known to everybody, and that, if anything else, almost defines astronomy. These planets are really large. The Earth is the largest of the terrestrial planets. Jupiter has over 300 times the mass of the Earth. It's 11 times the diameter of the Earth. Saturn is almost as big, about 100 times the mass of the Earth, almost 10 times the diameter of the Earth. These are truly giant bodies. They're characterized by cloudy surfaces. Let's look at Jupiter first, because pretty much what you say about Jupiter is true about Saturn. It's really more a matter of degree than anything else. Jupiter is lined with stripes of cloud belts. It's a rapidly spinning planet. In spite of the fact that it's so much larger than the Earth, it spins around in the normal direction, the same way that the Earth rotates, in only 9 hours and 55 or so minutes. It's a very rapid spin. Given that the planet is 10 times the diameter of the Earth, roughly speaking, its equator is spinning around at about 20 times the speed of the Earth, or at around 20,000 miles per hour. What has happened then is to take these clouds and to spin them out into zones that are parallel to the equator, very different from the cloud bands that we see on the Earth, where there are these more rotating systems that bring pressure fronts across the United States and other parts of the world. Very different. The winds at the equator blow at an exceedingly high speed. In Jupiter's case, up to about 300 to 400 kilometers per hour. They are really moving along, which gives the equator of the planet actually a faster rotation speed than the body of the planet itself. Embedded within the beautiful cloud belts are colorful swirls and eddies, some of which come and go, and some of which are at least semi-permanent. Now in the southern hemisphere of Jupiter, there is a large red spot that astronomers in all their imagination call the Great Red Spot that is about twice the size of the Earth. It's a high-pressure kind of storm system that's been there since at least 1670 and probably before. We don't have any idea when it's going to go away or even if it's ever going to go away. It's unique in the planetary system. There are other storm systems on other planets like this, but they come and go. Nothing seems to be quite as permanent out there as this Great Red Spot. Its origin is not understood. The planet is made largely of hydrogen and helium. One of the things that characterizes both Jupiter and Saturn is that the chemical composition is very similar to that of the Sun. On the average and gross product, 90% hydrogen, 10% helium, and roughly 0.1% of everything else. And remember, it's that 0.1% out of which the Earth is made, making our terrestrial planets really quite special indeed. The clouds, however, are made of ammonia crystals. It's sort of the same idea we developed with the terrestrial planets. In the Earth, you have water clouds floating in a nitrogen atmosphere. On Venus, you have sulfuric acid clouds floating in a carbon dioxide atmosphere. On Mars, you have a few wispy water and carbon dioxide clouds in a carbon dioxide atmosphere. On Jupiter, you have ammonia clouds floating in a hydrogen and a little bit of helium atmosphere. The colors are not very well understood. It's a very colorful planet with kind of browns and reds, and they are probably produced by some kind of sulfur compound in the atmosphere that is yet to be identified. But it is a really noxious place to be, because not only have we found the ammonia crystal clouds, but all manner of hydrocarbons as well. Methane, propane, acetylene, all manner of stuff that your local oil company would really like to get their hands on if they could, but it's a long piping job, and we're unlikely ever to mine a planet like this. Below the ammonia clouds are other cloud decks that may even include a water cloud deck, although that's a little bit uncertain at this point. When we dive into the clouds, we find that the cloud belts and the atmosphere, the gaseous atmosphere of the planet, is roughly 1,000 kilometers deep, much, much deeper than we have on the Earth. You never get to a solid surface. You'll occasionally hear people say, how much would you weigh on Jupiter? Well, in a sense, you'd weigh nothing, because you drop right into the clouds and fall and never find a solid surface within there anywhere. Jupiter and Saturn are sometimes called the gas giants, which is partly true because there's a lot of gas there in the atmosphere, but really they should probably be called the liquid giants, because the theory, at least, shows that as you go into the planet, the temperature and the pressure both go up, but the pressure eventually dominates and turns that hydrogen into a liquid mush. The hydrogen, like the oxygen of the Earth, is in its molecular form. It's H2. That's H sub 2, molecular hydrogen. We're not dealing with the isotope here. Molecular hydrogen in the atmosphere that turns into liquid molecular hydrogen about 1,000 kilometers down. Probably in kind of a gradual way. It's nothing like an ocean that you could, if you were, you don't want to even think about swimming in it. Deeper in, not terribly far in, the liquid molecular hydrogen turns into a metallic state. A metal is sort of loosely defined as a substance that can conduct electricity, a transfer of electrons from one atom to the next, and electricity will flow. This means you have an electrically conducting medium. We have never been that far inside of Jupiter. In fact, the best we've done is to drop a probe into the cloud belts, and the probe immediately disappeared and was crushed. There was no way of getting deep inside. So we have to rely on theory to understand what is deep inside these planets. Inside is this liquid molecular hydrogen. Jupiter is spinning so fast that the electrically conducting fluid then generates a very powerful magnetic field. Jupiter has a magnetic field over 10 times greater than that of the Earth, a truly powerful field that has some interesting ramifications when we start looking at going back to the external part of the planet and looking at the satellites. Deep down inside is probably an Earth-like core. Not really like the Earth, but made of kind of the same chemicals as the Earth. Rock, silicon, silicates, heavy stuff, iron, nickel, that kind of thing, of probably about 15 times the mass of the Earth. So around that Earth-like core, and we can't carry that analogy too far, we have this huge ball of hydrogen and helium in the liquid state, topped by a gaseous atmosphere, which is topped by ammonia clouds. Jupiter has a curious radiation pattern. All planets shine in the optical part of the spectrum that you can see with the eyes by reflected light. But Jupiter is also a powerful radio source. It's one of the strongest radio sources in the sky. There are 3 sources of radio emission from the planet. One is what we call thermal radiation. That is, the planet simply radiates energy because it's hot. Well, hot. It's not very hot. The temperature is only a little bit above 100 degrees Kelvin. But it's warm enough to emit considerable amount of infrared and certainly radio radiation. We'll get to the other components of it later. We can measure the temperature of Jupiter from the amount of radiation that it emits. You can also calculate the temperature that Jupiter should have on the basis of solar heating. The remarkable thing is that the temperature is about 15 degrees Kelvin higher than it ought to be, which shows us that Jupiter is actually self-luminous. It's actually emitting some of its own radiation. Sure, the Earth does too, to a tiny degree in terms of heat vented from volcanoes, but it is a terribly small amount. Jupiter, on the other hand, is emitting somewhere around half as much radiation as it gets from the half as much radiation again as it gets from the sun. It's self-luminous in the radio part of the spectrum. If you could switch the sun off, Jupiter would disappear optically. You couldn't see it anymore, but it would still glow in the dark as an infrared and radio emitter. How can this be so? What is causing the radiation? It's a big body. It's still contracting from the time of its formation 4.5 billion years ago and trading gravitational energy for heat, which then leaks out of the planet. And as long as it's slightly shrinking down, it'll keep radiating. 4.5 billion years after its formation, it's still a cooling body and still radiating itself away. Surrounding the planet is an enormous magnetosphere. Magnetosphere is the magnetic field that is filled with particles from the solar wind, that is shaped by particles slamming in from the solar wind. It is a powerful belt of particle energy, lethal to a human being. Our astronauts, when they went to the moon, passed through the Earth's Van Allen belts, which are similar to what Jupiter has, but they went through them so fast that it didn't affect them. You don't want to live in them for any period of time, but you can pass through them with little difficulty. Jupiter's, you probably couldn't. The radiation field within Jupiter's magnetic field is certainly lethal to a human for almost any level of exposure. No astronaut is going to visit close up to Jupiter. Even the robotic craft that have gotten too close have been partially damaged by the radiation field of Jupiter. This radiation field, that is, this magnetosphere that's filled with the particles, produces another kind of powerful radio radiation. It's called synchrotron energy, synchrotron radiation, because it's similar to the kind of radiation that might be produced on some kind of atomic accelerator. You have magnetic field lines and electrons that are trapped in them, spiral around like crazy at near the speed of light, and they emit radiation as they go. It's a very different kind of radiation than you observe from a hot body. So we have two kinds of radiation now, the hot body radiation, or thermal radiation, the synchrotron radiation, and in addition, Jupiter's inner satellite, Io, is so close that it orbits inside Jupiter's radiation belts, and there is a powerful electric current that actually passes between Jupiter and its innermost satellite that produces sudden and powerful radio bursts, almost like lightning bursts that you would get on a standard radio when listening to your music from the Earth. All three of these are picked up from Earth, and making Jupiter one of the brightest radio sources in the entire sky. Saturn is similar. Jump ahead just a little bit, and we'll kind of go back and forth between the two. It's kind of fun to compare them. Saturn has a mass that is about 1/3 of that of Jupiter, yet it's almost the size of Jupiter. An interesting thing happens when you make a transition from the big planet to the smaller one that gives us a powerful lesson for when we begin to talk about the next two planets out, Uranus and Neptune. What would happen if you could strip mass off of Jupiter? It would seem as if you'd get a smaller planet. The radius would go down, and to some degree that's true, but you're also diminishing the gravitational field of the planet, which is what holds the planet together, and a lower gravitational field allows the planet to puff back up some. So the result in going from Jupiter to Saturn is a lowering of the density of the planet rather than much lowering the radius of the planet. Saturn then becomes the least dense planet in the solar system. Jupiter's average density is a little bit greater than that of water, showing that it's largely made out of light stuff. Saturn's is only 7/10 that of water. As the saying goes, if you could get a bathtub big enough, you could put Saturn in it and it would float. And it's just simply a result of the fact that Jupiter and Saturn are made out of the same thing. Saturn's smaller mass instead gives it a lower density rather than a much smaller radius. The cloud belts of Saturn are there, but they're nowhere near as strong as the ones we see on Jupiter. We again have ammonia crystal clouds floating in a hydrogen and helium atmosphere, and the internal structure of the planet is about the same as that of Jupiter, but it's farther from the sun, the magnetic field is weaker, the magnetosphere is weaker, everything seems to be somewhat diminished when it comes to this next largest of the planets of the solar system. The cloud belts are partially hidden by a methane haze, which makes them a little bit more difficult to see. Now, we don't see the storm system so much, certainly no permanent storm system, but seasonally, Saturn takes about 30 years to go around the sun, Jupiter about 12. Seasonally, a white storm system develops on Saturn called, as astronomers can only call it, the Great White Spot, instead, of course, the Great Red Spot, which strips itself around the planet. Saturn, oddly enough, has equatorial winds that blow considerably faster than Jupiter's for reasons that are not understood. They're blowing at the order of somewhere over 1,000 kilometers per second, much higher than that of Jupiter. We do not know why. Come back to Jupiter now. Both of these planets have extensive satellite systems, what we sometimes call natural satellite systems. Now, the inner planets do not have satellite systems like that. The Earth has a satellite, and you don't want to call it an unnatural satellite, but it wasn't formed with the Earth. We think our moon was formed in a giant collision between a almost planetary-sized body and the Earth in the primitive days, something we'll talk about at the last lecture. Mars has two small satellites that are probably captured asteroids, and then you go out to the giant planets, and they have enormous numbers of satellites that orbit in the planet's equatorial belt. That is, they orbit parallel to the planet's equator. There's no point in even telling how many there are. Classically, Jupiter's got 16 reasonably decent satellites that can be more or less seen from the Earth. 4 giant ones, and then a dozen smaller ones. But if you give any kind of number, which will number in the tens and eventually into the hundreds, it would be wrong, because we keep discovering new ones. And what do you call a satellite and what don't you call a satellite? Does something this big a satellite? Eventually we'll find basically rocks in orbit about the planet. So there's little point in talking about the number. It simply doesn't mean anything anymore. Galileo saw them for the first time, the 4 big ones. These are the ones we really need to concentrate on. They are roughly 500,000 to 2 million kilometers away from the planet and orbit in periods of about 2 days, roughly to 2 weeks. They can easily be seen not just in a small telescope, but even simple binoculars will show them to you. If Jupiter weren't there, they'd be visible to the naked eye. They're so bright. But Jupiter's glare simply blocks them from that kind of view. But if you steadily hold binoculars to Jupiter, you will see 1 or 2 or 3, maybe even 4 little points of light spreading out. And any small telescope of the cheapest variety will show the satellites. After all, Galileo saw them with this little 28-power telescope with a lens only about this big. They're fascinating to watch because you can actually see them orbit. Even over the course of a night, you can see them shift position. Sometimes they'll be on one side of the planet, sometimes they'll be split, sometimes they'll be on the other side of the planet. They go in order outward: Io, spelled I-O, simple enough, Europa, Ganymede, and Callisto, all 4 having something to do with the mythology of the god Jupiter. The innermost and the second one out, Io and Europa, are large bodies. They're approximately the size of the Earth's moon. Ganymede and Callisto are truly planetary-sized bodies. They're roughly the size of the planet Mercury, which gives you a sense of just how large Jupiter really is to have Mercury-sized bodies as satellites in orbit around it. All 4 of these have unique properties. The densities drop from the inside out. They are, in a sense, Jupiter's little planets. They are to Jupiter as the planets are to the Sun, and may have been formed in very much the same way. One of the oddest bodies of the entire planetary system is the innermost satellite, Io. If there is any vision of Dante's hell in the solar system, it is Io, filled with hot, sulfur-filled volcanoes. It is the most volcanic body that we know of, a remarkable, remarkable satellite. The volcanoes are active even as we look at them. Hubble Space Telescope has seen them pop off. The Voyager, the Galileo spacecraft that has been in orbit around Jupiter, has seen them pop off. Very dangerous place. No astronaut is ever going to think of landing on Io. Not only are you going to be in Jupiter's intense radiation bath, but a volcano could literally erupt beneath your feet at any moment. They're silicate volcanoes, kind of like they are on the Earth, but they seem to be loaded with sulfur, which gives Io kind of a yellowish color. Why should that be so intensely volcanic? There is a curious relationship in the orbital periods between Io, Europa, and Ganymede. For every time Io goes around 4 times, Europa goes around 2 times, and Ganymede goes around once. And it is a perfect locking. This is an example in planetary dynamics of what is called a resonance. Go on out and push somebody on a swing. Your little brother, perhaps, or your son or your daughter. Push on the swing. Now, the swing has a natural period to it. If you push erratically, you can't get the swing going, and you're certainly going to annoy the person who's on the swing. If you really want to get the swing going, you push with the rhythm of the swing, and you can bring the swing up to very, very high proportions. That's what's going on here. Each satellite has a gravitational effect on the other satellites, but if they're in this synchronous kind of rotation, in this resonant orbital revolution, rather, you build up gravitational perturbations on each of the satellites. Io has, if left alone, would have a circular orbit about the planet, but the resonance allows the orbit of Io to change a little bit. It's so close to Jupiter that Jupiter raises intense tides on Io. Now, if the tide were left alone, that's fine. It would just cause a misshapen satellite. But the satellite is being pulled back and forth, which changes the strength of the tide. Go to a grocery store. You want to buy an orange? What do? You want a good orange? You give it a little squeeze. When you squeeze the orange, you actually heat it up a little bit. Now, it's not terribly noticeable in the grocery store, but if you had magic hands and went to the grocery store and picked up the orange and squeezed it at a megahertz, 1,000,000 times per second, you would pump so much energy into that orange that the orange juice would boil and pop through the surface as an orange juice volcano. And that's exactly what is happening on Io because of the intense squeezing that is caused by the tidal forces. That was actually predicted before it was seen by the Voyager spacecraft, and what a stir it caused with all of these volcanoes erupting. Pools, what appear to be almost pools of liquid sulfur, lakes of liquid stuff before it finally solidifies. The deadliest place in the planetary system, outside, of course, of landing on the sun itself. You move out to Europa. Things have quieted down a little bit, although it's still an active body because it's being squeezed a little bit too, but nowhere near as much as Io. Io is basically a rocky body. It has something of the natures of the interior planets. Europa also somewhat, but more watery. It's cold out in the outer part of the planetary system. Ice can form, vast amounts of water in the form of ice. Europa seems to have a deep liquid ocean on top of a rocky core surrounded by an icy crust. If you look at the surface of it, and we've seen these very close up, especially with the Galileo spacecraft, it looks very much like ice that's rafted upon itself and is constantly shifting position. Now, the magnetic field also implies that there is a saline kind of ocean underneath there. Aha, an ocean, liquid water, it's got to be warm. Suddenly, what pops into mind? Where did life maybe form on the Earth? Maybe in the oceans? Does Europa have life? Is this one possibility in the solar system that we haven't really examined? A lot of scientists are interested in drilling through that ice and seeing what's in the water below. It's at least one small, certainly small, but one small possibility as a reservoir of life. So maybe we have the Earth, maybe we have Mars, maybe not, maybe we have Europa, maybe not. It is one of the smoother bodies in the planetary system as well. It's all, the ice is simply, the heat from the inside has produced kind of a smooth surface on it. Ganymede and Callisto, farther out, bear the scars of this heavy bombardment, the same thing that caused the craters on the Moon, the craters on the southern part of Mars, the craters on Mercury. They're heavily cratered, but what do we see but giant skating rinks? These satellites are roughly half water ice. Their densities are quite low. There doesn't seem to be, there may be an iron core in some of these, but it's really the ice that counts, and they're glazed with an icy surface, and we see craters in the ice from billions of years ago. Ice is very strong at these temperatures when you're only dealing with temperatures of maybe 100 degrees above, 100 Kelvin degrees above absolute zero. And the craters last literally forever. A little soft, perhaps, but huge basins created and carved out of the ice. Jupiter's also got 4 medium-sized satellites that orbit inside Io, a yet deadlier place. And then way, way out there is another quartet of satellites and yet another quartet of satellites that orbit in the backward direction. They're probably captured asteroids. Nobody knows. And then dozens of little things that we are discovering. The closer we look, the more satellites we find. It's the big 4, however, that count. In the inside, little particles are always hitting the inner satellites and knocking pieces off them, which generates a debris ring around Jupiter. Yes, Jupiter has rings. You can't see them from Earth very well. In fact, it's extremely difficult to see them from Earth. They were discovered with the Voyager spacecraft. The real rings, however, belong to the next one out, to Saturn, making the planet one of the most beautiful objects in the planetary system. I have known students to look through modest-sized telescopes at Saturn and then look at the professor and say, "Oh, you're kidding. You've painted that on, haven't you? I'm looking at a slide, aren't I?" No. It really does look like it's pictures in a telescope. It's well worth finding some with a telescope. Run it up to reasonably high power and look at those beautiful rings. They are extraordinary. Rings, yes, it's not one ring. There are multiple rings in orbit about the planet. Yes, in orbit. They have to be, otherwise, of course, they would fall inward. And they follow Kepler's laws. The outer part of the ring is going around with a longer period than the inner parts of the rings, showing that they are not solid, something known as long ago as the 19th century. They consist of countless numbers, trillions, if not more, of ice-coated rocks, probably not much bigger than this, up to maybe meter-wide boulders, all in orbit about the planet, all colliding with one another, of course, all the time, perhaps consolidating, perhaps grinding themselves down. Very bright. These rings are over twice the radius of Saturn itself. And when they are fully open and more or less pointed at the Earth, they make Saturn twice as bright as it would be without the rings. Now, Saturn has an obliquity of its ecliptic of around 25 degrees or so, rounding it off. And that means that as Saturn goes around the Sun, it first presents the southern part of the rings to the viewer, and then later the northern part of the rings to the viewer. And twice in that 30-year period, the rings are exactly edge-on. And when the rings are edge-on, they disappear. They're gone. You can't see them. The rings are the thinnest things we know of. If you went to your average football field and you laid a piece of paper, kept stitching pieces of paper and lay it out over the entire field, that would roughly approximate the thinness of Saturn's rings. They're probably no more than a couple of 100 meters thick, and yet twice the diameter of Saturn itself. It's kind of frustrating, in fact. If you want to show someone or a student or a friend Saturn's rings, you point the telescope at Saturn and you hit it at that period when the rings are edge-on. Kind of embarrassing. Oh, Saturn doesn't have any rings tonight. Let me tell you how unusual and how odd that is, and you try to get out of the situation as fast as you can. Come back a year later, there are the rings again. There are multiple rings. They're called, logically, the A, B, and the C ring. They're divided by gaps. The A and the B ring are divided by what is called the Cassini division. It's a very dark band where there are none of these tiny moonlets. They're simply absent, or at least diminished within that ring. Another example of a resonance. Within that Cassini division, where there are fewer particles, the orbital period is a simple fraction that of one or two of the satellites, and the satellite's gravitational field simply clears it out. There's another division farther out where there is a satellite, and the satellite, as it orbits about the planet, simply cleans the ring particles out like a vacuum cleaner. It just sweeps them up. Looking at the rings very close up, you see multiple ringlets, dozens, hundreds of individual ringlets, all of which are hardly explained. Some of them are due to resonances. Some of them are probably due to large moonlets that are embedded. The rings are very stable because if a particle strays out, it'll go up in an inclined orbit and then pass through the rings again. It'll collide with a ring particle and stick back in the rings again. So the rings maintain their stability. We don't entirely know what made them, but the best idea is probably that an inner satellite got hit by something large and got broken up, and then additional collisions simply ground it down literally into a powder, producing these bright ice-coated rocks that we see as the Saturnian rings. Saturn also has multiple satellites, too many to count. Any number you give would eventually be wrong. There's no point to it. But an easy dozen or 18 that can be reasonably well considered as decent-sized satellites. And what a zoo it is. The biggest is called Titan. It's the second largest satellite in the planetary system, just a little bit in back of Ganymede, approximately the size of Mercury. And to make it unique, it's the only satellite with a thick atmosphere. We see a little bit of an atmosphere around some of the Jovian satellites, but this one has an atmosphere that's 1.5 times the pressure of the Earth's. It's largely nitrogen, but filled with methane and all kinds of other hydrocarbons, and there is some sense that on Titan it rains methane or even ethane, and some theoreticians have even predicted a hydrocarbon ocean on the surface of the satellite. We can't tell because of the methane haze. The hydrocarbons, under the action of sunlight, produce a smog very much like the one that hangs over a large city like Los Angeles. You fly above LA at some point, it's kind of hard to see the mountains or maybe even the ground. The same thing happens on Titan, where the ground is entirely hidden because of the thick smog. We'll know eventually because the Cassini spacecraft will drop a probe onto the surface of the satellite, and we will finally see what is on it in a few years. We have seen these planets close up by means of the Voyager spacecraft. We have sent the Galileo spacecraft as well to Jupiter. They have all taken close-up images, far better than anything we can see from our own planet. We will eventually send more orbiting craft around these planets and get to know them better and better. Why do we want to know them? Well, we now only have 2 giant planets with a strange meteorology. Now, if we can begin to understand something of the meteorology and the climate patterns on Jupiter and Saturn, that will eventually lead us back into understanding the climate patterns on our own planet. As everybody knows, weather forecasting is as much of an art as it is a science. It's a difficult thing to do because there's still many things we don't understand about our own atmosphere and our own atmospheric circulation. Studies of the outer planets are natural experiments which will help us do so. And not only do we have Jupiter and Saturn, but we've got these 5 large satellites and many, many smaller ones. And Saturn has just got such a weird set. There is one that has no rotation period. It just sort of randomly spins in a chaotic fashion. There's one that's half bright, half dark. There's one that looks like it's right out of Star Wars, a monster satellite that looks like this Death Star in the movie. It's just an amazing thing to look at. They're all different, as opposed to Jupiter satellites, which are at least have some kind of coherence to them. Saturn's doesn't, for reasons that we really don't understand. We're taking ourselves out now to 10 astronomical units away from the sun. We're going farther and farther away into depths of the planetary system where sunlight is dropping off more and more. Our next visit is going to be Uranus and Neptune, where we will begin to put Jupiter and Saturn and the terrestrial planets into a little bit better context, and finally work our way out to the very end in the next lecture to mysterious Pluto. Is it a planet? Isn't it a planet or not? Wait and find out.
After listening to Lecture 11, a student posed this question to Professor Kaler. How is it that the rings of Saturn hold their shape? Let's listen to the professor's response.
They are dynamically stable as thin systems. They automatically pull themselves into this thin pattern. In part, it's due to the collisions among the particles, I believe. That if they are thick, then the particles are coming in at an angle and they hit other particles, and that flattens the whole thing out. So it's a dynamically very stable system. When you get farther away from Saturn, the rings actually extend out far beyond what we see with a telescope. There are additional dusty rings farther out, and they're much thicker than the inner rings. They're dangerous places, these rings. We have to be very careful with spacecraft. They are so thin, that is, they're so thickly spread with particles that no spacecraft could actually pass through Saturn's rings. And we had to be careful about taking the Voyager spacecraft that visited Saturn back in the 1970s and make sure they went through the ring plane way outside the apparent rings. And even then they got dinged a little bit by some of the dust particles way out there.
This ends Lecture 11. Astronomy, Earth, Sky, and the Planets. Lecture 12. Distant Outposts. Uranus, Neptune, and Pluto.
In the last lecture, we looked at the giant planets of the solar system, the ones in the middle of the distribution of the whole thing. Toward the sun, the planets get much smaller, toward the terrestrial planets, and the same thing happens when we go to the outer part of the planetary system and now visit the smaller planets, the smaller, sometimes called Jovian planets, but not quite Jovian, Uranus, Neptune, and Pluto. Uranus and Neptune are very similar, Pluto very different. We'll look at the structures of these bodies, at their moons, and what they all have to do with each other, and finally at Pluto as a marvelous transition object that takes us far out beyond the planetary system into the distant reaches of the solar system, the two not really being quite the same. Remember when we looked at Jupiter and Saturn, and we remove matter from Jupiter? As we remove matter from Jupiter, instead of getting smaller, you decrease the gravitational field and the body puffs up again to almost the size of Jupiter. If you added mass onto Jupiter, you wouldn't really increase the radius very much. What you would do is by dumping more mass into it, increasing the gravitational field, you increase the density. Jupiter is almost as large as you can possibly make a Jovian-type planet, actually. Well, if you now took Saturn and stripped away the mass of Saturn down to the mass of Uranus and Neptune, which are about 15 times that of the Earth. Smaller bodies, only about 4 times the radius of the Earth. Notably different. If you strip mass away from Saturn to get down to Uranus and Neptune, if they were made out of the same stuff, hydrogen and helium, you would again lessen the gravitational field, the planet would puff back up again, and Uranus and Neptune would be approximately the size of Saturn, a little bit smaller, but not all that much smaller. Instead, they're much smaller. Their densities are much higher than you would expect if they were made out of hydrogen and helium. Therefore, they must be made out of denser stuff. They are very different kinds of bodies. About, as I said, 15 times or so the mass of the Earth, about 4 times the radius of the Earth. Neptune, a little bit smaller than Uranus, but its mass a little bit higher, giving it a slightly higher density. But rather, as you could say about Jupiter and Saturn, what's true about Jupiter is true about Saturn and vice versa. More or less the same thing is true about Uranus and Neptune. What you can say about the planet Uranus is somewhat similar that you could say about Neptune. The colors are different than they are from Jupiter and Saturn. Jupiter and Saturn are kind of a yellow-white color. You can see the creamy nature of the planets with the naked eye. Uranus is actually visible to the naked eye, but you could never see the color. But with a telescope, it becomes bright enough to see that these two planets, Uranus and Neptune, take on kind of a greenish to bluish-green cast. Even the colors are different as a result of methane haze in the atmosphere. We're not looking at ammonia clouds anymore. We're looking at methane clouds floating in the same hydrogen and helium atmosphere, but as you plunge inside the planet, the hydrogen and helium probably stops rather well down, and we don't really know what's inside these planets, but it probably turns into some kind of a mush of methane, ammonia, and finally loosely defined rock, iron, and the rest. Much denser stuff. So in that sense, Uranus and Neptune are kind of intermediate between the terrestrial planets and the Jovian planets, except not in position. In position, they're much farther out. It's rather hard to describe the distances when you get to these outer planets. Jupiter's 5 astronomical units. The AU, remember, being the distance between the Earth and the Sun. Jupiter's 5 astronomical units away from the Sun. Saturn is not quite 10, and then we make a giant jump to 19. We almost double the distance out to Uranus. And then we go from Uranus to Neptune to 30 astronomical units. Neptune is a faint planet. It shines well under naked eye vision. With large binoculars, you can pick it up. With a small telescope, it's not too difficult to see. If you were standing on the planet Uranus, looking at Neptune, it would barely be visible to the naked eye. It's not like these two planets are right together. The distances simply increase in relative proportion the farther away you get. How Uranus and Neptune turned out to be so similar isn't really known, except that it seems to be that Neptune may have been formed a little bit closer to Uranus and then gravitationally moved farther out. We can address this problem in the last lecture when we look at the creation of the solar system and of the planetary system. Uranus has one outstandingly odd characteristic. Even Neptune has an obliquity of its ecliptic, a tilt to its axis, something like this. Most of the planets are tipped more or less perpendicular to their orbital planes. Venus, of course, entirely upside down. Nevertheless, the axis is perpendicular, not Uranus. Very weird. It's tipped over like this, at a 98-degree angle from the perpendicular, technically making it the second planet of the solar system to rotate backwards. It has the most extreme weather conditions, climate conditions of any planet in the solar system, because at one point in its orbit, the South Pole is practically pointing at the Sun, and then 42 years later, half the orbital period, the North Pole is pointing at the Sun. Remember when we talked about the Earth and the tropics and the Arctics? The Tropic of Capricorn and the Tropic of Cancer are at latitudes of 23.5 degrees, the same as the tilt of the axis of the Earth's orbit, rather the axis of the Earth's rotation. The Arctic and Antarctic circles are 90 minus 23.5. You get the idea. Well, at 98-degree tilt, the Arctic circle on Uranus would be at 8 degrees latitude, and the tropics would be up at 82 degrees. They actually cross over, so you get the most extreme possible seasons. The only more extreme you could get is if the tilt were exactly 90 degrees, and it's very close to that. Nobody knows why this is true. Nobody knows what happened. It's not just that the planet alone is tipped over at 98 degrees, but the entire satellite system is tipped over. All of this somehow happened as everything was forming at the same time, including the satellite system. When we encounter odd things like this, we often invoke collision of some sort. Nobody can go back that far and figure out really what happened, but we think the moon formed in a gigantic collision between the Earth and probably a Mars-sized body. A collision may have stripped much of the outer mantle away from Mercury, producing this huge iron core in the planet, relatively speaking anyway. And this is substantiated by some of the huge impact basins we see, impact basins that are hundreds of kilometers across, 10 kilometers or more deep. Sometimes these impacts, with a little imagination, you can almost see it breaking the planet in half. A large collision could have somehow produced this tilt. How that would have happened, we really don't know. We can't go back that far in the past. So it'll probably remain a mystery for a long time to come. Jupiter produces its own internal heat. Considerable amount of energy comes out from simple gravitational contraction. Saturn does the same thing. Saturn actually produces relatively a bit more heat than Jupiter does, in part as a result of gravitational contraction, but also as a part of the helium inside being converted from the dissolved gaseous state into a liquid state. It's sort of raining helium down in the deep core, and that releases energy as well, much as a thunderstorm releases energy on the Earth. Neptune, the farthest planet out, actually produces relatively more heat than any of them. And here's Uranus looking so similar to Neptune. Here is yet another of these large planets. Uranus produces no heat at all of its own. We have no idea why. Whether this has something to do with the tilt of the axis, that's another odd thing about it, is simply unknown. It remains a mystery. We've only visited these two planets once by spacecraft each, by the Voyager 2 spacecraft, which went by Jupiter, which went by Saturn, and then finally visited Uranus and finally visited Neptune on its way out of the solar system altogether. And that's all we know about them close up. Although with the Hubble Space Telescope and with even some of the telescopes from the ground, we can get reasonably decent ideas of what's going on the planetary surfaces, especially with the Hubble. When the Voyager 2 first examined the planet Uranus, it was I guess the word was boring. There were no surface features. The cloud belts were gone. Only with the most extreme enhancement of contrast could you see any cloud belt at all. And finally, one little wisp of cloud was seen and one tiny cloud belt. Now, curiously, the Voyager passed by the planet Uranus when the South Pole was practically pointing at the Sun. That is, the Sun was practically overhead at the South Pole of the planet. As the planet has moved around, we have now watched the development of more and more storm systems and cloud belts. They're beginning to pop up, probably as a result of seasonal effects. Neptune, on the other hand, has a reasonable tilt to its axis. It's not so unusual. It's 20-some degrees. Neptune behaves atmospherically a little more like Jupiter and Saturn. The color of both of these planets is coming from a methane haze. Methane absorbs red light very well, so it takes the red light out of the spectrum, allowing only the bluish component of light and the blue-green component of light to be reflected back to the Earth. In addition, Neptune has some other kind of chemical in it that enhances the reflectivity and turns it into an almost deep blue marble. It's just a glorious sight as seen on the Voyager spacecraft pictures. When the Voyager passed by Neptune, there was a large dark storm system circulating around on the planet. And again, with the imagination of astronomers, it was called not the Great Red Spot, remember, the Great White Spot on Saturn. This was the Great Dark Spot. And down below it was another dark spot, Dark Spot 2. Really romantic names. We thought for a while that these dark spots were going to be like Jupiter's Great Red Spot, but the Hubble showed it just disappeared. And then others come and go. They come and go. A very active atmosphere. They seem to be methane plumes of some sort that come from below, but nobody is entirely sure. We need to send more spacecraft to the outer part of the solar system, and at the moment there are no plans to do so. And even if we do develop plans to do so, it is a very, very long trip, taking the order of a decade or more to get out there to the farthest reaches of the planetary system. Both Uranus and Neptune have ring systems. The rings of the planet Uranus were found in a curious fashion. Occasionally, a planet will pass in front of a distant star, and you can see the star dimming out through the atmosphere. It's a nice way of studying planetary atmospherics, in fact, by the effect that the planet has on the star as the planet passes over the distant body. As the planet approached the star started to wink in and out, flash in and out, disappear, then it'd come back, disappear, and then it'd come back. And it was obvious at the time that there must be dark rings around the planet that were periodically passing in front of the star. And then when the planet cleared the star, the rings on the other side made the star pop in and out. All the Jovian planets, all the big ones, Jupiter, Saturn, and then I guess you should call them the Uranian planets, since they're so similar and so different from Jupiter and Saturn, they have their own ring systems as well. Ring systems seem to be a natural part of planets that have extensive satellite systems. The ring systems in the outer part of the solar system are almost black. It's said that if you were in the Voyager spacecraft passing by the satellite, you wouldn't even be able to see them looking out the window. They're almost as dark as black velvet. But with great enhancement of the cameras, there they are. You can also see their effect looking back and seeing them pass in front of other stars and get the information this way. They're, as opposed to the Saturnian ring system, which are broad rings separated by narrow gaps, we have just the opposite with Uranus. They are large, skinny, for the most part, dark rings separated by broad gaps. They are way stations for smashed up moons. The moons don't even have to be smashed up. You have a satellite in orbit about the planet. Some rock particle hits it. The moons aren't very big. It kicks off dust and debris from the satellite, and this debris is naturally shepherded into ring systems that are largely controlled by the satellites themselves. The rings are gradually cleared out by the extensive atmospheres of these planets, but they are then replaced by more smashed up particles. That is at least the way the Jupiter's ring works. It's the way Uranus's ring works. It's the way Neptune's rings work. Neptune has these rings as well, although they're kind of odd. They're in partial arcs. You see a section of ring, and then there's a bit of a gap, then there's another section of a ring over here that are probably controlled as well by the satellites. Uranus has an extensive natural satellite system, the likes of Jupiter's and Saturn's. It doesn't have any big ones, however. It has 5 or so modest moons, then a whole bunch of really tiny ones. The moons don't seem to have any coherent pattern to them. The smaller one, Miranda, is, however, clearly, or at least had been, geologically active, something that you don't expect in the dark, dim, cold regions of distant outer space like this. The surface is carved into an enormous sections of ridges, almost looked fractured. For a while it was thought that Miranda had been smashed up and restitched back together, and now we're pretty much sure that it's convective motions, ancient ones probably, in some kind of icy mantle. All of these satellites are made largely of ice, or at least half ice. Saturn's are made out of 70% ice, at least the smaller ones are. Ice seems to dominate everything out there. Neptune has an odd family of satellites. It doesn't have anywhere near the number, at least that we know of, that Uranus, that Jupiter, and Saturn have. Instead, it has a number of small ones and one pretty good-sized one named Triton. Triton, after all, after Neptune. That is, there's a mythological relationship here in the names again. Triton is not as big as the the Galilean satellites of Jupiter, Io, Europa, Ganymede, and Callisto. It's about the size of Pluto, which we will talk about shortly, which is roughly half the size of the Earth's moon. It goes around Neptune in the wrong direction. It goes around backwards. It's the only largish satellite of the solar system that does that. And when you see a satellite that's going around in the wrong direction, you immediately think, aha, capture. That is, Neptune is rotating in one way, the satellite is going around in the wrong direction. It was probably a captured body. We have close-up images of Triton from Voyager 2, and a strange-looking body it is. It's a solid surface, as you'd expect, of an icy moon, and there seems to be a polar cap on it, and what appear to be almost geologically active regions. Plumes were seen coming out of it. Icy volcanoes of some sort. Actually, a volcano made out of hot water coming out of the interior. And a snow that is probably made of nitrogen, has a very thin atmosphere, nitrogen, carbon monoxide, carbon dioxide, and perhaps a whole bunch of other stuff. It's a captured body. How does one body capture another? If you have one body here and another one comes in, it will go right back out on a hyperbolic orbit, as pointed out by Isaac Newton. One body all by itself cannot capture another body. You'll have a hyperbolic orbit instead, in and back out again. Now, tidal forces can slow one down. That's a possibility. But what may have happened is that Triton was an independent body in interplanetary space, passed too close to Neptune, wiped out many of the Neptunian satellites. Maybe that's why Neptune doesn't have many satellites, and got itself caught in a wrong way orbit. And then we go to the most distant body of the planetary system. Everybody's favorite. If you lecture to a bunch of kids and you ask them, what's your favorite planet? There are 2 that really jump out. One is Venus, because the little kids have often seen Venus as the morning or the evening star. But everybody loves Pluto. Even if it's not their famous, even if it's not their favorite, they all love Pluto. It's probably due to the Disney dog, but they all love Pluto. Pluto was discovered accidentally in 1930. There was a deliberate search on for it because we thought at the time that there was a distant planet that was perturbing the orbit of the planet Uranus. Turned out to be an accident. Clyde Tombaugh was hired at the Lowell Observatory around shortly before 1930 to examine the sky and the ecliptic, the zodiac, to see if there was a more distant planet. And it took him a couple of years to find this little blip of a body orbiting in a 250-year period around the sun. And it turned out that Pluto was just a dot against the sky. We couldn't even resolve it into a disk until the Hubble Space Telescope was able to see it. It has a moon about half its size. It's more of a double planet than anything else in the planetary system, even more so than the Earth-Moon system. The two orbit like this. Remember, the moon keeps one face pointed toward the Earth at all times. In Pluto and Charon's case, the two keep pointing toward each other like this in perfect synchrony. That is a synchronously locked orbit, tidally produced through both bodies. If you were standing on Pluto, you would always see Charon in a particular point in the sky going through its dim phases, the sun only a bright star off in the great distance. Standing on Charon, Pluto would appear the same way going through its phases. The odd thing about the planet, the other odd thing about it is that it too is tipped over at about 127 or so degree angle. So technically Pluto rotates backwards too, and the whole system rotates backwards. No one knows why. No one knows where Charon came from. We don't know why it was tipped over. Again, we invoke, well, if we don't understand it, it must have something to do with a gigantic collision. We can't prove it, but who knows? Pluto has a very thin atmosphere, just millionths or less than that of the Earth. Nothing that would be breathable, but one that's detectable. Made largely out of nitrogen, but all kinds of other things, carbon monoxide, carbon dioxide, methane, the usual stuff that you find in the outer part of the planetary system. But Pluto has a very strange orbit as well. Most of the orbits are reasonably circular. Mercury's is a little offset. Mars's orbit is reasonably elliptical, but still, a circle is at least a decent approximation. Not Pluto. Pluto goes from 30 astronomical units out to 50. For a period of 20 years, in fact, it is closer to us than Neptune. It comes inside the orbit of Neptune. A collision is not possible between the two because of the fact that Neptune and Pluto are synchronously locked together, that in a minute. Also, Pluto's orbit is tilted at a very steep angle that actually takes it entirely out of the constellations of the zodiac when it is at its maximum. So here we have the orbits of the planets, most of the planets like this, and here's Pluto going way out here and coming way up here like this. A very strange orbit that is very different from any of the other planets of the solar system. This began to lead us to think that, is Pluto a planet? Is it maybe some other kind of odd body? Not only that, Pluto is very similar to Triton in form, in structure, in size, in density, and we think that looking at Triton actually gives us a view of looking at Pluto. We don't know. It's the only planet we have never visited by spacecraft. There have been many plans. They have been scratched. Maybe someday, over the next few decades, we'll finally visit Pluto, but it's a long, long trip, and the plans are not even firm, and they won't be for some time. The oddest thing, I suppose, about Pluto, however, is that it is, again, in resonant orbit with Neptune. Neptune goes around the Sun 3 times for every time Pluto goes around twice. Now, if you take the periods of these planets, the exact orbital periods, and divide one by the other, you see it's not quite a 3-to-2 ratio. But if you average them out over, say, a million-year period, it's exactly so. That is, Neptune has trapped Pluto. Pluto is a caught planet, if you want to call it a planet at all, which I'm certainly happy to do. Neptune, therefore, has grabbed 2 bodies that are very similar. It's caught Triton in a backward orbit around itself, and it's caught Pluto in a resonant orbit that actually protects Neptune entirely against collisions. Because if Pluto's here, Neptune is always someplace else. The two can't get very close together. And where there's 2, perhaps there are others. Now, as we'll see in the next lecture, we have a whole set of comets that come in from a belt surrounding the orbit of Pluto. This belt came to be known as the Kuiper belt after Gerard Kuiper, who was one of the first people to postulate it. Could Pluto be more like a comet than a planet? We started to look for other bodies that were similar to Pluto, and we began to find them. 10, 20, 30, 40, 100, 200, 300. The number just keeps going up and up and up. Huge numbers of icy bodies far beyond the orbit of Pluto, intersecting the orbit of Pluto, and I should really say beyond the orbit of Neptune, Pluto being one of them. About a third of these bodies are called Plutinos because they, isn't that an awful word, called Plutinos because they share the orbit of Pluto. They're in a 3-to-2 locking orbit. Neptune's grabbed a whole bunch of these things. Pluto seems to be simply the largest of them. In other words, it's a Kuiper Belt object, and Clyde Tombaugh, before his death, was said to have said, and even if he didn't say it, he should have said it, that if I hadn't discovered the last planet, I discovered the first body of the Kuiper Belt, which is a stunning thing to find when you go back all the way to 1930, and the next ones weren't found until into the 1990s. Pluto seems to be a transition object of some sort between these icy comets. It's not a comet. Don't even think about calling it that. Between these icy cometary bodies and the real planets, as if it's some kind of planetary core that started to grow into some kind of Uranus and Neptune, but simply ran out of raw material and never quite made it. So now we've looked at them all. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, and Pluto with its wacky orbit. 30 astronomical units all the way up to 50. Talk about extreme weather. As Pluto gets farther away from the sun, all of its atmosphere will freeze as snow and fall on the ground, and all the atmosphere will disappear. And then 100 years to 150 years hence, as Pluto begins to approach the sun, the atmosphere will warm, the ice will warm, and Pluto will develop an atmosphere again. Imagine in wintertime all the air falling onto the ground as snow, as a nitrogen snow. Very, very odd place. The coldest places we know of out there. The temperature of Triton, the temperature of Pluto, hangs around 38 degrees above absolute zero. A dreadful place to be. One that's going to be very difficult to visit by robotic spacecraft sometime in the future just because of the intense cold and getting things to move out there. So let's go back and look at sort of an overview of this system. We've got the 4 inner planets, Mercury, Venus, Earth, and Mars. Rocky planets with iron cores. Jupiter and Saturn farther out. Hydrogen, helium planets with tiny rocky cores. Even the word rock is a bad term, of heavy material on the inside. Uranus and Neptune, which are probably kind of slushy things with a lot of hydrogen and helium, but mostly, certainly a large quantity of heavy stuff, including water ice. And then funny little Pluto out beyond the orbit of Neptune. And with many other bodies, the largest one of which is about half the size of Pluto. We've now looked at the whole planetary system. In the next lecture, we're going to start looking at the little stuff, at the junk, so to speak, as we will find out the leftovers of the creation process, which will include the comets. We'll go back to the Kuiper Belt. We'll even revisit Pluto here. The asteroids, which could have been collectively termed an additional terrestrial planet. And then at the comets that occasionally sweep past the Earth, which will set the stage, finally, for looking at the whole creation of the planetary system, how it was all put together.
After listening to Lecture 12, a student posed this question to Professor Kaler. In the final analysis, is Pluto a planet? Let's listen to the professor's response.
So now we come to the question again, what is it? Is Pluto a planet? Is Pluto not a planet? And then you get into arguments of semantics. In a way, who really cares what you call it? A planet is what you define to be a planet. There's no firm definition. Some people will define a planet as a body that is massive enough to squeeze itself into a spherical shape. If you get enough mass together, remember rock is not infinitely strong, gravity will make it spherical. If a body is small enough, however, there's not enough gravity to squeeze it into a spherical shape. Maybe that should be the definition. But if you're going to use that as a definition, then the largest asteroids also come out as planets, and then you've got a lot more planets as named planets that you probably want to deal with rather than minor planets as the asteroids are called. So Pluto is so odd that for a while the International Astronomical Union, the organization of professional research astronomers, decided to remove Pluto from planethood. It's gone. It's a Kuiper Belt object. Well, the school kids of the country didn't like that, nor did the hometown of Clyde Tombaugh, who discovered Pluto, and they lobbied the International Astronomical Union, who finally gave up and said, okay, it's a planet. It can be both, can't it? That's what makes the body so intensely fascinating. It's a transition body between one kind and another kind, the reasonably large planets at least.
Another student then posed this question to Professor Kaler. How many planets in our solar system have magnetic fields? Let's listen to the professor's response.
Most planets of the solar system have magnetic fields that are reasonably well understood. Mercury's got a little one. It shouldn't, because we think the core should be frozen, but apparently it's not. Venus doesn't have any at all. The Earth has a modest magnetic field that leads compasses, of course, to point to the north magnetic pole, which, while it's not at the geographic pole, is not very far away. All magnetic fields are slightly tilted relative to the rotation. Here's the rotation axis relative to the rotation axis. It's a natural part of the circulation of the stuff in the interior that is generating the magnetic field. Mars seems to have, well, there's a bit of an argument as to whether it actually has one. Jupiter has a powerful magnetic field. Saturn is a good one. Uranus and Neptune have magnetic fields as well, but they are as strange as the rest of the planet. They're certainly as strange as the Uranian tilt. Here is the planet. The magnetic field axis, here's the rotation axis. The magnetic field axis is tilted at a wild angle. Not only that, it doesn't even go through the center of the planet. It's offset roughly halfway out. No one has any idea how a planet can generate a wacky magnetic field like this. The other aspects that separate Uranus and Neptune from Jupiter and Saturn are their winds. The winds of Jupiter and Saturn blow in the same direction as the planet's rotation. Uranus and Neptune have longer rotation periods than Jupiter and Saturn, around 16 or 17 hours, but the winds blow in the opposite direction, making them again quite different from Jupiter and Saturn. The winds blow in the direction, the equatorial winds at least, blow in the direction opposite the planet's rotation. Nobody knows why.
This ends Lecture 12, Astronomy, Earth, Sky, and the Planets. Lecture 13, Leftovers of Creation, Comets, Asteroids, and Meteors.
The last lectures have focused on the major bodies of the solar system, excluding the sun, of course, on the planets. Now we're going to take a look at, I guess we could only call it the junk, the leftover stuff, the little stuff. It's not unimportant. Never confuse size with significance. It's the little stuff that taught us how all the planets were put together. We're going to look at comets, how they work, where they are, why we see them. We're going to look at rocky asteroids, all the little stuff that hangs out mostly in the spaces between Mars and Jupiter, and at the things that hit the Earth. The meteors, the meteorites, the things that land here that we can actually pick up and bring into the laboratory and examine, which further tells us how all of this was put together, a subject we will address finally in the last lecture of this course. There's very little that is more beautiful and to the superstitious more frightening than a great comet. Comets are often confused with meteors. The meteor whooshes across the sky. It's an atmospheric object. It's a rock that hits the Earth's atmosphere. Whereas a comet is an interplanetary body. It orbits the sun much like a planet, except on a very long, skinny, elliptical orbit that can bring it very close to the sun and then back out far beyond the planetary system. Many are the comets in the sky. New ones are discovered every year. Dozens of new ones are found. Most of them are far below naked eye vision. Perhaps once a generation or so, a great comet will make an appearance. A comet like Halley's Comet, one that comes back every 75, every 76 years, way out from the orbit of Pluto, all the way in toward the inner part of the solar system and back out again, over and over and over. It was named after Edmund Halley, who looked at a variety of comets and found that to explain repetition of orbits, there must be one that kept coming back over and over and over again. A comet in the sky, they're called comets from the word coma, Latin for hair. They're called comets because there's a bright central region, the head of the comet, sometimes with a little nucleus in the center, and then a long streaming tail that hangs out in back of it that can actually go across a good fraction of the celestial sphere. And then night to night, you see it slowly move against the background of the stars until maybe a year or two later, it disappears into the blackness to be followed only by a telescope. We can name Halley's Comet that came around in 1910 and again in the 1980s. We'll come back again in the middle part of our own century. We can name the Great Comet of 1810, Comet Ikea-Secchi of 1963. The list goes on and on and on of these beautiful naked eye comets. There will be another one in your lifetime. They come and go every 10 or 20 years. The great ones, the really big ones. Watch out for the next one. Find a dark sky and look at it. It is one of the true icons of astronomy. If Saturn is one, surely a comet is another one. How do they work? The idea of a comet is that basically of a dirty snowball. You can go off into, say, a New York City street sometime in February when the buses have been rolling by and the slush and the dirt and the sludge is in the gutter, and you pick up a handful of this awful-looking ice filled with dirt and tar and all the nasty stuff. That's kind of like the head of a comet, like the nucleus of a comet. It is an ice ball or a snowball filled with dirt. That is the dirt and the dust, not dirt like we find on the Earth, with organics, but little rocks, dust, fragile stuff, all stitched together by ice. When the comet is way out in the outer part of the planetary system, where it generally hangs out, it's completely frozen and almost impossible to see. But as the comet's head, the nucleus, comes close to the sun, sunlight begins to melt away the ices, not into liquid, but turn it from a solid into a gas directly. This begins to happen as the comet approaches the orbit of Jupiter and then approaches the orbit of Mars. The comet's nucleus is not terribly large. Something the size of Chicago, something the size of Manhattan would be a fairly good-sized comet. They range in size from perhaps a few tens or hundreds of meters up to a few tens of kilometers. They're not terribly big bodies. They're little things. They are, as we will see, primitive bodies out of which the outer planets were actually formed. They're the leftovers of the creation of the solar system, and there's still an awful lot out there. One approaches the sun. Here's the sun in this long, skinny orbit. The closer it gets to the sun, the more the ices melt away. The gas from the comet's nucleus expands away. Sunlight ionizes the gas. That is, it strips the electrons away from mostly light molecules, hydrogen atoms, turning it into an electrified gas. The solar wind, this flow of matter that is continuously streaming off the sun, then hits the gas and blows a gas tail away from the comet. The comet's tail, therefore, always points away from the sun. The gas tail is going to be illuminated by sunlight. It's an ionized gas. It will create its own light very efficiently. So this gas tail can stream as a skinny blue light far away from the nucleus of the comet. At the same time the ices are melting away, the embedded rocks and dust are being released. So the comet becomes surrounded then by a cloud of dust and rocks. The pressure of sunlight alone, light actually has a pressure when it's absorbed by something. The pressure of sunlight alone then pushes the tiny dust grains away from the comet. But the dust grains have significant mass to them, so that's a little bit influenced by the orbit of the comet. Nevertheless, the dust tail more or less still curves away from the sun. So the tail can precede the comet in the orbit, rather like this. It's not like a rock on a string. A ribbon on a rock, where you tie a ribbon around a rock and throw it in the air and the ribbon streams in back of the rock. The tail can precede the comet in orbit. It always points away from the sun, although the dust tail can do some strange things depending upon the mass out of which the tail is made. The closer it gets to the sun, the greater the size of the tail. And finally, when the comet passes around the sun and goes off into the great distance, the tail diminishes, and finally the whole thing turns back into a dirty snowball again. The whole thing to happen all over again some years hence, depending upon the orbital period of the comet. In Halley's case, every 76 years it comes back in, goes back out again. Comets are therefore destined to die. Every time they pass close to the sun, they get a little bit melted away from them. We think Halley's Comet loses approximately 1% of its mass every time it goes around. We have traced Halley's Comet back to times BC, from ancient Chinese records. It's been coming around for at least the past 2,000 years and probably before that, and it will keep going for many hundreds, if not thousands of years into the future. Eventually to be broken apart, separated in half. Spacecraft images show the actual nucleus to be kind of a peanut-shaped thing, the order of 10 kilometers across, and eventually a break in half, and two comets, one back of the other, will orbit the sun. There's been a series of great comets orbiting the sun over the last couple of hundred years. They are called sun grazers because they come very close to the sun before going back out again, one following the other after the other after the other, which were apparently part of one enormous comet from long time past that got broken up into many pieces after being melted away by the sun, and now the pieces are coming all back like little ducks in a row, one after the other after the other. Comets break down into two broad groups. Short-period comets and, not surprisingly, long-period comets. The division is around a couple of hundred years. It's not very hard and fast. These comets have different kinds of orbits. The short-period comets tend more or less to stick to the plane of the ecliptic. That is, they tend to be found kind of in the constellations of the zodiac. This means they're coming from a part of space that is not terribly far away. Because they're short period, Kepler's laws, they can't be more than a few tens of astronomical units out, 40, 50, 60, somewhere in that general neighborhood, which is why we began to postulate the existence of this Kuiper belt, a reservoir of maybe 100 million cometary bodies, most of which stay out there forever, but the gravity fields of Neptune and Uranus, of the outer planets, gradually move them in, and we can see even a few of them moving in between the orbits of Jupiter and Saturn. Gradually they will move into the inner solar system and be seen as short-period comets. These can't last very long because the periods are so terribly short. They melt down very quickly. So for the most part, short-period comets, Halley's being an exception, which was probably a long-period comet that somehow got captured into the inner solar system. Most of these short-period comets tend to be kind of faint and not very well known to the public. The long-period comets are a different matter altogether. These things have periods which can be thousands, if not hundreds of thousands of years long. Some of them appear to come in on almost parabolic trajectories, which implies that they are open-ended. They're not. They're really long, skinny ellipses that may take the comets out thousands of astronomical units, if not tens of thousands of astronomical units away from the Earth and Sun. It was postulated by an astronomer of the middle 20th century named Jan Oort that if comets are continuously falling apart, there must be an enormous reservoir of them, such that 4.5 billion years after the solar system was formed, we still see them coming in. And the long periods, and these comets, or the long period comets, don't stick to the plane of the solar system. They can be found all over the place. I've seen them crossing the sky near the Little Dipper, far from the plane of the ecliptic. They're sort of randomly oriented. The implication is there must be an enormous reservoir of maybe 10 trillion comets that may extend almost halfway to the nearest star as part of the sun's overall gravitational influence. Most of them will exist out there effectively forever, but in this Oort comet cloud, where the inner planetary system is not much bigger than this, here's a comet in a long, almost circular orbit, never to be seen, but a nearby passing star comes close to it, disturbs the orbit of the comet, and sends it into the inner solar system where it is seen as the long-period comets. These are the ones that make the truly great comets, the ones that the tail can stretch a good fraction of the way across the sky. Comets are complex bodies. They have a very complex chemistry. The ices in them are not just water ice. There's methane ice. There's alcohol ices. There's all manner of complex chemicals that have been frozen, dominantly water. In 1910, the chemical compound cyanogen was discovered in comet tails. Cyanogen is a deadly gas. The Earth passed through the tail of Halley's Comet in 1910 to the horror of people who thought they were going to be gassed to death. People laid wet towels underneath their doors to keep the gases out. It was said that people in New York City had rooftop parties celebrating the end of the world because they were going to die soon. Nothing happened at all. The sky didn't even get minimally brighter. We passed through that tail and nobody saw a thing because the tails of comets are so incredibly vacuous. It's just that they are very efficient converters of sunlight into energy. So the tail becomes almost the dominant part of the comet to the human eye, certainly the most beautiful part, and yet it is a mere tiny fraction of the mass of the comet itself. The short period comets are coming in from the Kuiper belt. We can look out into the Kuiper belt and we have now found hundreds of these bodies, most of which will stay out there before being perturbed to come back into the inner solar system as short period comets. They range from things that are only probably almost rocks you could hold in your hand to bodies that we're now discovering that are a few tens of kilometers across, up to bodies like Pluto, which is the largest body of the Kuiper belt, and a transition between the real comets and the planets. Pluto is a body that kind of in its way tried to be a planet but failed. It became kind of a planetary core and never gathered around it the heavy stuff, the large stuff, the hydrogen, the helium, and many of the ices that the planets like Jupiter, Saturn, Uranus, and Neptune are made of. This is one of the things that makes Pluto so intensely fascinating because it's the transition between the planets and the comets, which are some of the original bodies out of which the planets were ultimately formed, as we'll see in the final lecture of this course. The other set of junk in the solar system, an awful word for this stuff, isn't it? Debris, perhaps is a better term, are the asteroids. Science fiction story. The astronaut bravely plows through the asteroid belt, this belt of rocks that exists between the orbits of Mars and Jupiter. Asteroids banging off the spacecraft until blessedly the astronaut is through it. Doesn't work like that. There are probably billions of asteroids, but the distances between them are enormous. They're at 3-4 astronomical units out. So they're not all that densely passed. We have passed several spacecraft right through the asteroid belt with nary a ding. No problems at all. Perfectly safe. The only problem that we would get to is, of course, once we're in the planetary environment out there where it can get dangerous around inner space near Jupiter, passing through Saturn's rings, but not through the asteroid belt. There's a curious numerical relationship in the distances of the planets from the Sun. And in the later 1700s, a planet was predicted to be in the space between Mars and Jupiter. The numerical relationship said there should be one there, but there wasn't. We went from Mars all the way to 5 astronomical units out to Jupiter. But because of the prediction, astronomers began to look for the possibility of a planet in there, and on the first day of 1801, one was finally found, not even visible to the naked eye. Just a little bit below it. You could see it with a modest telescope. The first minor planet, the first asteroid, which acquired the name Sirius, number one Sirius. Before long, however, roughly 2.7 astronomical units away, pretty much fitting in the space between Mars and Jupiter. Before long, another one was found, then another one, and then another one, all acquiring the names of mythological characters along with numbers. The discoverer of an asteroid has, or at least had, the capability, the right to name the asteroid after a mythological character. Finally, we ran out of mythological characters. Then some of them were named after cities. Then you could name it after your sister, your mother, your brother, your dog, anybody you wanted to name it after at all, until we got to the point there were so many of them found, we simply sort of gave up and gave them numbers. There are so many occupying the zodiac that it's difficult to take a photograph, a long-term exposure of the zodiac without finding some darned asteroid in it. At one point they were called the vermin of the skies because they were even messing up some images that we wanted to take of more distant bodies. We now know of tens of thousands of these asteroids. Most of the orbits are known. They cluster around the orbit of Sirius, roughly from 2 to 3 astronomical units away, which is known as the main belt of the asteroids. Sirius being the largest, about 500 miles, about 800 kilometers roughly across. Quite small, significantly smaller than the Moon, significantly smaller even than Pluto. But a nice round body, and if you want, I suppose you could call that a planet too, although it's simply not visible to the naked eye, even though it's closer than Jupiter. Rather than call these things planets, we have long called them minor planets. There is even a minor planet center that keeps track of all these critters because there are so darned many of them. Unlike comets, asteroids are more made out of rock and iron. They're made more out of the stuff that the Earth, Mars, Venus, and Mercury are made of. Although there's certainly some transitions. There may be some transition bodies to icy things that are perhaps more like comets, but the two are considered to be pretty distinct. The comets are dirty ice balls, whereas the asteroids may be somewhat wet rock balls, and some of them relatively dry. From their spectra, from the quality of their reflected light, we can tell that some of them are metallic and that some of them are true rocks. Some of them cluster in families. The asteroids are simply grinding themselves down. Although it doesn't happen frequently, the solar system is 4.5 billion years old. Given all that time, the asteroids are going to collide with each other. And when they collide, you get a bunch of smaller asteroids out of the collision, all of which have pretty much the same quality. So we see families of asteroids orbiting the Sun, all of which have the same sort of chemical character. The collisions can, of course, send a few of them scattering around and spread things out in the asteroid belt. It's not a thin plane. It's rather thick. They actually occupy sort of a thick donut around the Sun. Within the asteroid belt, we also find a good example of these resonances. Jupiter does quite a number of them, number on the asteroids. There are zones in which there are simple fractions of the orbital period of Jupiter where Jupiter can either concentrate the asteroids or kick them out altogether, producing gaps. Jupiter has a powerful influence on the asteroid belt. As a result, Jupiter can throw a few asteroids close to the Earth, or it can scatter a few asteroids outside of its orbit. So the asteroids are not all confined to the orbit, to the main belt. They spread out gradually until some of them go past the orbit of Mars, a few of them have orbits past the orbit of the Earth, and a few of them can even approach the orbit of Mercury. These are the ones that are considered a little bit on the dangerous side. They're called near-Earth asteroids sometimes, or potentially hazardous asteroids, because if one big one hits the Earth, it can produce a major impact crater, change the climate of the Earth temporarily, put a huge amount of dust and steam in the upper atmosphere, and kill off species on the Earth. This certainly happened. Well, almost everybody agrees that this happened 65 million years ago when a rock somewhere around 10 kilometers across hit off the coast of what is now considered the Yucatan Peninsula, creating a crater a couple of 100 miles wide, raising so much stuff in the air that it killed off a good fraction of the species alive at the time, including the dinosaurs, which is why you don't have dinosaurs stomping in the streets out there today. They lived for a long time, and an asteroid apparently did them in. How do we know? Well, we know because we can pick up pieces of asteroids off the ground. An asteroid, a bigger one, can get through the Earth's atmosphere and land on the surface of the Earth. And if it's not too big, it won't even produce a crater. It'll simply land on the ground for somebody to pick up. When it hits the ground, as it goes through the Earth's atmosphere, and we'll touch upon these later, it produces a streak of light in the air called a meteor. And when it hits the ground, it becomes a meteorite. They come in two broad forms. Irons. It's an iron meteorite. It's part of the Gibeon meteorite found in Africa. On the outside is a fusion crust. This is the stuff, the part of the asteroid that went through the Earth's atmosphere and got slightly melted away. It's been cut, sliced, polished, etched with acid. Inside, you can see beautiful, large nickel-iron crystals. This is about 92% iron, about 8% nickel, and a couple of minor inclusions here of silica. The crystals are so large as to require about a 1,000,000-year cooling time from the liquid state. This is apparently the iron core of what was once a differentiated asteroid. That is, an asteroid that had a rocky mantle and an iron core, very much like the Earth. This is very good evidence that the Earth scientists are right, that the Earth has an iron core. This must have come out from a larger asteroid that smashed itself up. This pattern cannot be replicated on Earth. You cannot make iron crystals because we don't have a 1,000,000-year cooling time to make them this big. So you can't fake a meteorite like this. It's impossible. Some of these are quite large. In the Rose Center in New York, there's a meteorite so big they practically had to build the building around it. It's huge. I've seen pictures from the 1930s with kids sitting inside the curves, the carved out sections of the meteorite. You don't want to get hit with something that big. 1,000 meteorites a day fall on the Earth. Most of them are little things. And of course, the Earth is fairly large. Not in terms of course, the giant planets, but there's still a lot of surface area. The vast majority fall in the oceans or in uninhabited areas. Nobody has ever been killed by one of these, although there have been people that have been hit by them. I've seen a few damaged cars from them too, so just sort of watch it out there. Your chances of getting hit by a rampaging bus running through your home is probably much, much greater than getting hit by a meteorite. So you can relax. You're not in any terrible danger with them. If an asteroid breaks up, you're going to get the iron core producing the iron meteorite. You will also get a piece of the rocky mantle. So the majority of meteorites are actually small rocks. This is much less attractive in its way than the iron meteorite. Stony meteorites come in quite a variety of forms. There are just dozens, if not hundreds, of different kinds of meteorites. This is a very special kind called a chondrite because it contains chondrules. Chondrules are little circular inclusions in the rock that have all the evidence of being flash heated, then suddenly frozen again. Sometime back in the early stages of the solar system. We have no idea why, but it does point to some very serious violence that took place in the early days of the system. This is a special kind of chondrite called a carbonaceous chondrite because it has a very high carbon content. It's part of what is called the Allende meteorite fall that took place in Allende, Mexico many, many years ago. This rock has been dated at 4.5 billion years old. It is the oldest thing known. We look for the oldest thing known, and we say that must be very close to the age of the solar system, the age of the planetary system, and the age of the sun, because as we'll see, there's excellent evidence that all of this system was formed all at the same time. This beautiful rock looks lovelier as you know what is in it. Contains amino acids. It contains complex chemicals that were formed in the dusty gases of interplanetary space before the rock itself was actually formed. Hitting the Earth, it deposits these complex chemicals. There are people who speculate that these bodies hitting the Earth deposited the seeds of life. Not life itself, but the complex chemicals out of which life perhaps ultimately formed. We can even go back to the comets and see what happens to these. These things are hitting the Earth all the time too, except that they're so fragile that they can entirely break up. Comets are filled with water. We think that in fact the oceans are filled with comet water, comet juice, so to speak. So these things have quite an impact upon us. And from them, we learn the age of the whole solar system. Now, as these meteorites pass through the Earth's atmosphere, they produce a meteor. Anything that hits the Earth's air is going to produce a streak like this. Everybody, I hope, has seen a meteor at some point. They're really very common. If you go out in the early morning hours, when you are on the side of the Earth facing in the direction of the Earth's motion in orbit, when the Earth is sweeping these little rock particles up, not just asteroids, but in the majority of cases, the dust that has been flaked off of comets, you'll see typically 3 or so meteors per hour. They're not at all uncommon. In the evening, the meteoroids, really, the particles in interplanetary space, have to catch up with the Earth. And they tend to be long and lazy streaks of light. When a body hits the Earth that fast, it's going at orbital speed, it produces a tremendous shock wave, kind of a sonic boom. This is converted to heat that begins to melt the meteoric particle away and can completely dissipate it long before it hits the ground. The meteors take place, they occur 50, 60, 70 miles above the surface of the Earth. They are entering in and burning up on their way to the ground. The big ones, the pieces of asteroid, can be strong enough to get through. Some of them explode before they land, sending showers of stones down onto the ground. The irons can get all the way through and clunk on the ground, and the big ones can produce impact craters. The stuff that flakes off comets will, for a long time, stick to the orbit of the comet. The Earth is always passing the orbits of comets, whether the comet is there or not. As you get close to the orbit of a comet, you will pick up more and more meteors. And if you go through the orbit of the comet and the debris, you will pick up a vast number of meteors and get a shower. The meteoric particles, the meteoroids, which are called before they hit the atmosphere, are on parallel tracks around the sun. The Earth is plowing through them, and much as railroad tracks converge to a point in a distance as a result of perspective, the meteors in a shower will appear to come out of a radiant point in the sky. The meteor showers are therefore named after their constellation of origin. The most popular of them is the Perseid shower that hits us on the morning, at least it maximizes on the morning of August 12th. You can go out and lie on your back, nice summer night, moonless night, out in the country, and simply watch them zip across the sky, about 1 or 2 meteors per minute. It's quite a show. Now, they can get better than that. Probably the best one of all is the Leonid shower that hits us on the morning of November 17th. The Leonid shower comes from a comet that has a 33-year period, a short period comet, well, only 33-year period around the sun. In back of the comet, there are ribbons, intense ribbons of meteoric particles that also have a 33-year period. Now, on the average, the Leonid shower is pretty poor, 1 or 2 meteors an hour, perhaps. Not very much. But every 33 years, if the conditions are right, the Earth will plow through the major part of the stream, and we will get a meteor storm, hundreds, if not thousands of meteors per hour. The great meteor storm of 1833 from the Leonids is said to have produced 100,000 meteors per hour. They said it was like a snowfall. It was like the sky coming apart. It must have been terrifying to the people of the time who didn't know what was happening. And yet, during these meteor showers, there is never an increase in the number of meteorites hitting the Earth. All of the stuff burns up in the air before it gets down to the ground. So the meteors can be produced both by asteroids and by comet debris, but it's only the asteroidal stuff that is strong enough to get to us. The cometary fluff all dissipates. It's all so fragile, it all dissipates before it reaches the ground. Go on out and watch sometime. They are truly wonderful things to look at. There are dozens of these showers that take place every year, 3 or 4 that are well worth getting out at 3 o'clock in the morning and just gazing up in the sky and looking at them. All of this dust pervades the plane of the solar system. If you're in a good location where it's really dark, especially on northern hemisphere spring evenings or northern hemisphere fall mornings, watch after sunset in the evening. After twilight ends and the sky darkens, you can see a cone of light standing up from the horizon. In the best cases, that cone of light will actually not diminish. It will go through all of the constellations, the zodiac, and will be seen rising again in the morning sky. It's called the zodiacal light. It looks like a faint additional Milky Way going across the sky. And it's sunlight being scattered off the debris, the finely divided debris of smashed up asteroids and comet fluff. In the morning, it's sometimes called the false dawn, and you can see it any clear morning if you have a perfectly dark sky, or any clear evening depending upon the season when the ecliptic is more or less standing perpendicular to the horizon. The best thing to do, of course, is go on out and see these things for yourselves, not just the planets that inhabit the sky, but the comets, the zodiacal light, and all of the debris that hits us, the meteors. We've now brought the whole solar system together, starting with the sun, the 9, 10, 8, however you want to define them, planets of the solar system, and finally all of the debris, all of the little stuff that make the solar system much larger in extent than the planetary system. We don't know how far out the Kuiper belt goes, maybe 50, maybe 60 astronomical units. We don't know whether it extends farther than that even. It may. The Oort cloud, on the other hand, extends pretty close, halfway to the nearest star. It goes out many tens of thousands of astronomical units. Everything is now in place. We can take the planets, look at the conditions of the planets, how they orbit the sun, look at all the debris, and begin to put together a picture of how this marvelous system was formed 4.5 billion years ago.
After listening to Lecture 13, a student posed this question to Professor Kaler. Why do comet ices go directly from a solid to a gas? Let's listen to the professor's response.
We talked about that in an earlier lecture, but it's probably a good thing to do now. The comet ices, technically sublime. It's like dry ice in a theater set. You don't get liquid carbon dioxide from the dry ice. It goes directly from a solid to a gas. In order to get liquid dry ice, you have to have the gas, not liquid dry ice. In order to have liquid carbon dioxide, you have to compress the gas into a liquid form. What has happened is that the boiling point of of carbon dioxide is comparable to the freezing point, so you can't get the liquid stuff. The same thing happens with water on Mars. If you lower the air pressure, you lower the boiling point. You keep dropping it down until it reaches the freezing point, at which point you can't get liquid water anymore. So you go directly from the solid state into the gaseous state. The air pressure or the gas pressure surrounding a comet is so low that you can't get liquid anything. It goes directly from the ice into the gas.
Another student then posed this question to Professor Kaler. Could a major comet hit the Earth? Let's listen to the professor's response.
We think that an asteroid did in the dinosaurs because these meteorites, which are from the asteroid belt, contain a rather high level of a chemical element called iridium. Iridium is relatively rare on Earth, but it is relatively rich in meteorites. There is a layer all the way around the Earth that's been dated at 65 million years ago, when the dinosaurs roughly disappeared, that is rich in iridium. And we think the only way it could have been deposited is by a major asteroid, one several kilometers across, striking the Earth, destroying itself, and then spreading itself out in the form of dust that finally settled down and worked its way into sediments around the Earth. This is the first evidence that we had of major extinctions on the Earth by an asteroidal impact. One of the common questions I get is this going to happen again? What are the chances of it happening again? And you smile and say, 100%. It will happen again, because there are a lot of asteroids working their way in. That's why they're called potentially hazardous asteroids. And various offices at NASA and others are trying to track down all the Earth-crossing asteroids of a given size, at least, as far as we can, and tell where they are. Eventually, we may have, before one of them hits, big ones only hit every few millions or every tens of millions of years, so we're relatively safe for a short period of time. But if we do see one whose orbit crosses the Earth and is potentially dangerous and is likely to hit the Earth, eventually we will probably have the ability to do something about it. And it doesn't take much just to shift the orbit slightly so that 100 years hence it's going to miss us. Comets, on the other hand, are a little bit more dangerous. The problem right now with the asteroids is that it's usually in a not here it comes, it's usually there it goes. That is, we miss it coming in, we see it going away. They're not found till they get very close, which is why we've got to track down the critters. Comets are a different matter. We might only have a couple of years warning for a major comet coming in to the inner solar system, taking a beat on the Earth. On the other hand, comets come in once, they go around back, and they go out, and the long period ones don't come back for sometimes hundreds of thousands, if not millions of years. So it's a one-time affair, unlike an inner asteroid that keeps orbiting the sun until it finally crosses the Earth and smashes into us. So in that sense, perhaps comets are a little bit less dangerous. On the other hand, you have less of a warning from them.
This ends Lecture 13. Astronomy, Earth, Sky, and the Planets. Lecture 14. Creation.
We've now looked at everything from the Earth all the way to the outer fringes of the solar system. We've looked at the planets, we've looked at the asteroids, at the comets, at the debris that hits the Earth. Now it's time to put it all together and see where it came from. The clues are in the planets themselves. Look at the solar system and look at the beautiful symmetry of the whole thing. All the planets orbit the sun, looking down from the north. All the planets orbit the sun in the counterclockwise direction. All in more or less circular orbits. Even Pluto, with its relatively elliptical orbit, is still not that far out of line. Most of the spin axes are more or less perpendicular as well. And most of the planets, at least with the exception of 3 of them, Venus, Uranus, and Pluto, spin in the same direction in which they orbit the sun. This can hardly be accidental. In addition, the general plane of the solar system lies pretty close to the equatorial rotation plane of the sun, and the axis of the sun is more or less perpendicular as well to the plane of the solar system, and the sun rotates in the same counterclockwise direction as the planets go about it, rather nicely linking the orbits of the planets to the sun, giving us some pretty good evidence that this system formed all at the same time, and that the planets are, in a very strong sense, the satellites of the sun. Many more are the symmetries. Look at the sizes of the inner planets. They start off small at Mercury, get bigger at Venus, bigger yet at the Earth, then squeeze down to little Mars, and then if you accumulate all of the asteroids, they're smaller yet. So you have this beautiful envelope distribution with one massive body, the Sun, on this end, and another massive body, Jupiter, on this end. This doesn't look accidental either. And then we start with Jupiter, the big body of the solar system. Go to Saturn, a little bit smaller. Go out here to Uranus, a little bit smaller yet. We come out to Neptune, about the same size, and then squeeze down to Pluto and the little bodies of the Kuiper Belt, smaller yet. So the sizes squeeze down as we go to the outer parts of the solar system. Again, more symmetry for us. Look at the compositions of the planets. The inner ones, including the asteroids, are all really quite similar to each other. We have iron cores surrounded by rocky mantles, and we can even include the moon perhaps in that, if it's got an iron core, which it probably does to a small degree. And then you go to the outer planets, Jupiter, hydrogen and helium, Saturn, hydrogen and helium, then heavier stuff in Uranus and Neptune, and then heavier stuff yet with ice in Pluto. The inner planets are dry, in spite of the fact that the Earth has a relatively deep ocean for a human being. The amount of water on the Earth is really relatively small. It only averages a couple of miles deep over a body that's 8,000 miles wide. The Earth is still, with all of its water, still fairly dry, as are all of the inner planets, some of them almost absolutely bone dry. Once you get out to Jupiter, however, the situation changes. In the inner core of Jupiter, you probably have a great deal of ice, probably water ice, in a very strange form, of course, because the temperature is very high near the core. But if you go to the satellites, some of the satellites of Jupiter are probably 50% water ice, and some of the satellites of Saturn may be as much as 70% water ice. Water and ice continue all the way out in the outer part of the planetary system, where, of course, it's cold. The original idea, the basic idea of how the solar system formed goes back to some of the philosophers of the 1700s, particularly to Immanuel Kant and others who followed him. The idea is that the early sun, and they had no idea how old the planetary system was. They didn't think it was all that old back then. The age is kind of irrelevant to the idea that the early sun was surrounded by a disk of spinning gas, and that the planets condensed out of the gas over a fairly short time scale, leaving little gas, but leaving planets all in orbit in the direction in which the original disk was spinning. The basic idea was fundamentally correct. The details were wrong, not too surprisingly, because there is so much that we have learned over this several hundred years since the original idea was instituted. Let's take a look at how, from start to finish, we are pretty sure that the planets and our own Earth came to be. Go on out on a clear night, out in the dark countryside, say in a northern hemisphere August evening, and look at the Milky Way over your head. It's a beautiful sight. The Milky Way, however, is not a smooth band. The Milky Way is broken up by a ridge that runs right down the middle. In the northern hemisphere, it's called the Great Rift. The Incas of Peru and Chile gave other names to it. It's broken up with small blobs of dust clouds. These are clouds of interstellar gas and dust. And the dark dust particles block the light of the background stars. You can see these with the naked eye. Now, most of the interstellar gas is heated by starlight to temperatures as high as 10,000 degrees or so, Kelvin, above absolute zero. Exploding stars can heat the interstellar gas to even higher temperatures, into the hundreds of thousands of degrees. However, where you get, by accident, thick knots of this dusty gas, the dust blocks the light of the stars. And consequently, it gets chilled. The dust acts as a natural refrigerator to chill the gas. Now, when you heat a gas is naturally going to expand. This is how automobiles work, after all. You explode an air-gas mixture, and you drive a piston, and you drive your car down the road. If you chill a gas, the gas is going to condense instead. So you will get natural blobs of gas and dust forming within these dark dust clouds, and if they can become thick enough, if they can become dense enough, they can begin to contract under the force of their own gravity. And a star is beginning to be born. Now, anything out there is going to rotate. Why is it going to rotate? You can't stop things from rotating. These gas clouds bump into each other. They're like bumper cars. They set themselves spinning. Everything is rotating to one degree or another. Planets, stars, the sun, the galaxy, everything is spinning to some degree. You're starting off with a blob that is very large, vastly larger than the planetary system. And as it contracts, it spins faster and faster and faster as a result of the conservation of angular momentum. The same thing in Kepler's second law that makes a planet move faster as it gets closer to the sun. The Earth is spinning. As a result, it throws itself out at the equator. As this blob of gas spins faster and faster, most of it goes into the star in the middle. The stuff that doesn't go into the star gets spun out into a disk that surrounds the forming star. In fact, we have a problem in theory with these forming stars, that they are spinning so fast by the time they form stars that you can show that they spin themselves apart and stars can't form at all. We have to have some way of actually slowing the contracting blob down, and there are ways of doing it. The magnetic field of the whole galaxy, in fact, acts to help slow these blobs down as they contract and finally release themselves from the magnetic field of the galaxy, and the star forms in the middle. At the same time, this disk is forming around the star that is being born in the middle. All of this is happening at the same time. When the density and temperature of the forming star get high enough at the core, then thermonuclear reactions are initiated. Hydrogen begins to form, to produce, 4 hydrogen atoms get together to form helium. That releases energy, and that stops the contraction. It's sort of a controlled hydrogen bomb reaction, entirely controlled. The sun and stars like this in their forming stages cannot explode at all, and the sun can never explode. There's no way it can do it. Massive stars can, but we're not talking about that. We're talking about the initiation of thermonuclear reactions that stop the contraction. The energy pushes outward from the center of the star. Gravity tries to push inward, and the star entirely stabilizes itself at a constant radius. As the star and our early sun stabilized, it was then surrounded by this thin spinning disk, all the gas and dust rotating in the same direction, and we wind up with Kant's disk. However, what Kant got wrong, not that he could possibly know, is that it wasn't the gas that did it, it's the dust grains in the disk. Think of an individual dust grain, maybe several astronomical units out, orbiting the sun all on its own. It hits another dust grain. It sticks by electrical forces, perhaps, or maybe melds together if it sticks hard enough. So you grow a bigger dust grain. That one hits yet another dust grain, which grows bigger. Hits another one, which grows bigger. These dust grains, when they start, are very small. You couldn't even see them with the human eye. But before long, they become visible if you were in the cloud. And then the bigger dust grains gang together, and before long, they're a millimeter across. They sweep up more. They sweep up all of the dust. Then they're growing to centimeter size, and then meter size. They're getting bigger and bigger and bigger as a result of continuous accumulation of the dust grains. Finally, they're growing into kilometer size, and we give them a name. We call them planetesimals. The word means basically infinitesimal planet. It's kind of a bad word, but it does get the idea that these are the primitive bodies out of which the solar system and the planets began to form. Now, in the inner part of the solar system, where we have the sun, it's hot. These growing planetesimals can accumulate more dust grains and more solids, but they can't accumulate ices. Water is not going to condense on them because it's too hot in there for water to turn into ice and condense on the grains. There's a lot that you can't accumulate. So all you can accumulate is the heavy stuff that boils away at very high temperatures, metals and the like. So you begin to grow bigger and bigger planetesimals that are dry in the inner part of the planetary system. Once you get beyond about 4.5 astronomical units, however, the temperature of this gaseous, dusty disk drops to the point at which the growing planetesimals can accumulate water. And they grow icy rather than dry. The farther out you get, the more ice, until finally you're out there where these things become a good fraction ice. Not just water ice, but all manner of volatiles that form ices upon the dusty, dirty planetesimals. And think of what you're getting in here. These planetesimals are beginning to, in the inner part of the planetary system, are beginning to replicate the asteroids. Those in the outer part of the planetary system are beginning to replicate comets. That is the distinction. The ones that form in here, close, are going to be dry. The ones that form out here are going to be wet in the sense of ice. Now, when they get big enough, maybe 10, 100 kilometers across, then they have a significant gravitational field, and the big ones start to gobble up the small ones. The big ones grow at the expense of the little ones, and gradually they grow bigger and bigger and bigger, farther and farther apart, until, before you know it, you've got 4 or 5 rocky bodies in the inner part of the solar system that will become Mercury, Venus, the Earth, and Mars. In the outer part of the planetary system, however, these planetary cores that are growing to the size of the terrestrial planets get big enough that they can begin to accumulate the hydrogen gas that pervades the planetary system. Because it's cold out there. Hydrogen is a very volatile element, but the growing Jupiter can accumulate it. It can accumulate helium as well. So the planet around Jupiter, where Jupiter lies, can grow big and fat. Just keep growing and growing and growing until it's used up all the hydrogen in its region. Saturn, a little bit farther out, is growing where there is less gas because the disk is gradually fading away as you get to the outer part of the planetary system. So Saturn comes out smaller. By the time you get out to Uranus and Neptune, you've got a planetary core, sure, but the amount of hydrogen is less and less. By the time these planets can grow big, the growing sun is beginning to sweep the gas away from the disk of the solar system, removing the raw material, and Uranus and Neptune are bound to come up fairly small. Get out to Pluto, here's a planetary core growing from accumulation of comets, but there's no raw material left out of which to grow a big planet, and it gets stuck as a Pluto. And you get out into the Kuiper Belt, there are too few of them out there to accumulate into a planet at all, and you still have hundreds of millions of cometary bodies left over that may go out to 50, 60 astronomical units, and we're really not sure how far this disk actually goes. All explains away very nicely. You wind up now with rocky bodies, metallic bodies in the inside, wet, hydrogen-filled bodies, wet in the sense of ice, on the outside of the solar system. Now, the last collisions are really big. If you have a primitive Earth and you deposit in it a 100-kilometer wide planetesimal, you're going to deposit an awful lot of heat into the Earth. Every time it gets hit by a big one like that, you begin to melt the Earth. So the last collisions should produce, if not a liquid planet, certainly a partially molten planet in which the heavy stuff can sink to the inside. So you have a natural blast furnace, in a sense. The iron and the nickel, the most common metals of all, sink to the middle where they will eventually produce the planetary core, and the lighter rock floats to the outside to produce the planetary mantle. And across the top, everything solidifies into this crust that we see here today. Now, there must have been some interesting competition among these growing planets. We think that in the early days of the planetary system, a body approximately the size of Mars hit the Earth hard enough to incorporate part of itself into the Earth. The debris then went into orbit around the Earth, lost much of its iron to the Earth, and the debris solidified into the rocky moon. It's the only viable theory we have for why the moon has the chemical composition that it does. It's not without controversy, but it's the only theory that seems to hold up with time and to fit how the moon was formed. There's good basis for realizing these giant collisions. All you need to do is look at the Maria on the moon. All you need to do is look at the giant impact craters on Mercury, on Mars, and you can see how much energy must have been deposited into these planets, enough to have melted them down. All of this should have happened in somewhere around 10 million years. It should be, the computer simulations show that this is a very quick process. The sun was born 5.5 billion years ago. How do we know? Well, we simply look at our carbonaceous chondrite meteorite. We do radioactive dating in the meteorite, and it comes up to 4.56 or so billion years. The oldest thing we can find. It's part of the asteroid belt. The asteroid belt was a growing planet that tried to accumulate. However, it was too close to Jupiter. Jupiter's gravity kept the asteroid belt stirred up and kept the velocities